It's not active yet. Can you hear me? 1, 2, 3. Yes, now it works. Please take your seats. We start in about 2 minutes. Well, I think it's time to start the day 2 of this Planetary Defense Conference. And I hope you all enjoyed the nice events yesterday, the interesting panel discussions, and of course also the reception with a lot of very good food. And before we start with the presentations, I would like to make a few announcements. So first of all, today we have, let's say, normal conference presentations of various length, quite a few of them. And at the end of the day, starting at 18:15, but I would say as soon as the session ends, there is a poster viewing event. And you have already seen the poster area. There will be some cheese and wine served with it. I guess you already noticed by now there is never a shortage of food here. And some additional information, all presentations will be live streamed. So we assume your consent that this is being done. And they also will later be recorded so you can view it again. If you have an objection to that, then you should not come up to the stage to give your presentation. It's very important to keep the time, and session chairs have been instructed to be quite strict because we have quite a few presentations. We also have some online virtual presentations in between, so it's important to stick to the time. Then I would like to remind you that for the gala dinner, I hope you can all make it to that, you have to pick up a ticket at the reception desk. So they have your name in a list, and if you have not done so, please go there and pick up your ticket. That it's mandatory to get inside. And also, you might have seen there are some scannable logo signs on the wall today to register for the trip tomorrow to the waterfront. It's an IMAX showing, also it's partly for the public, but also for the delegates. And you have to, or you should at least register, even if you do not want to go to the IMAX show, because they have to know how many buses they have to order. So please scan it, and there you can fill in your name and also tick if you want to participate in the IMAX show or not. But you probably will not be thrown off the bus if you didn't register. It would be very good if you could do so. So on the outside today, it's on the walls, I've seen. Just scan it if you have not done so. Also, I should remind you to use this Event Mobi app. And a lot of people already used it yesterday. There you see, again, it displayed. Just scan it, and then you are in. You have to define the password yourself. Also, there were some polls made yesterday on various events. If you click on agenda and go to some agenda items, you still can fill in the polls of yesterday, at least most of them. So in the end, we will look at the statistics, what your reaction is. And you are welcome really to do so today. Okay, I think that is the main the main things. Also a reminder is all the presentations. So if you have PDF or other material, it will be archived later. As I said, the same will be true for the videos, for the recording that is being made. I think having said this, we should just start. I see the clock is ticking, but I know all the presenters can see the clock here. I think there will be a bell ringing and you get instructions from the session chairs to keep your time. So please be careful there. So having said this, I think we start session 1, and I invite, I see the first speaker is already getting ready, the session chair of session 1, I think it's Ashley. Please take over.
Good morning. So we're going to start with the hypothetical exercise session. We're going to build on what we saw in our panels discussed yesterday, but get into some of the more technical details here with these talks. We've split it up into 2 groups, and so this morning we're going to start with a space mission planning theme. We will have question and answer sessions at the end of each group. We're getting on your app in the question and answer discussion section, we're getting it added where you can add questions there, so they'll all be in one spot when we get all of our panelists or all of our presenters up here at the end. And now I think we can start with our first speaker, Detlef Koschny, who with his talk, The International Response of Space Agencies to the PDC 2025 Exercise, the Same Page Exercise, Lessons Learned.
All right. Good morning, everybody. Who was not in this room yesterday? Okay. So I guess I can skip the talk because you all... All right, now let me go on. I just give you an overview here. This I can skip. This hopefully you know now, the task of Same Page and I1. But I'm going to give you the sort of lessons that we learned in terms of the organizational part of this exercise. And then the rest of the session, you will hear a lot of the technical presentations. So I'm not going to go over that. But here is the reminder. 2 groups, International Asteroid Warning Network on the left, Same Page on the right. Same Page task is to coordinate and propose international space-based response to an asteroid impact threat. And let me remind you of, or let me tell you, I think that wasn't really said yesterday, how we actually worked this exercise. So from Kelly's email address on the 1st of August last year, I received an email pointing me in my capacity as chair of Same Page to the notification that you all have seen yesterday, which said, okay, there is a probability of an impact of 1.6% for an asteroid, which we don't really know the size, but it's going to be larger than the 50-meter threshold. There was no discussion about that. That was very clear, so we did not have to address this point. What do we do if the asteroid is 49 meters in size, right? And we saw the impact corridor. We discussed this all at length yesterday. Basically, I immediately informed the heads of the delegations of Same Page and called for a telecon, and there was really a large attendance, even though we had only 2 days or 3 days until we had the time slot for the telecon. Okay, we knew, of course, in advance, so we prepared a bit, and everybody was ready to be there. In this first telecon, we basically decided that we will have every Friday at, I think it was 2 o'clock UTC in the afternoon, we would have a telecon or videocon to discuss this exercise. And we did that until, this doesn't work. All right. We did that until October, where we had an in-person meeting, and we generated these recommendations that you saw yesterday, the 5 recommendations, in this in-person meeting in Milano. Okay, unfortunately then we didn't have a long break because Paul and the colleagues were very active and prepared, based on our recommendations actually, an update of the exercise, what we call EPIC 2, which then is placed in 2028. One of the things we agreed on in the beginning was we defined different work packages and work package leaders. You see the work packages here, you can read them at your leisure later. I think in the end we found out that really we spent probably more than 80% of the time discussing work package 1. Juan was the work package leader. He will have the presentation after me, so you'll get all the details from him. We also realized that some of the other work packages didn't really make sense in the way we defined them in the beginning, like spacecraft and payload design. How do you combine this? Is there a difference between a reconnaissance mission or if it's a flyby mission? So in the end, work package 2 and 3 were grouped together. And well, the other ones we'll discuss a bit later. But, you know, at least we had a starting point. So that was good. And already there, I basically want to, I want to go back to one more thing, yeah, which I didn't discuss. It says it here. We started again then with the Epic 2 just before Christmas, again with our Friday meeting slots, every Friday. And then we stopped that mid-April and basically said, okay, now we have the recommendations in place, the 3 for Epic 2 that you also saw yesterday. So we did that a bit shorter, and in the end, I found it quite exhausting. If you do this regularly all the time, this is one of the things we have to realize. If this really happened, it's not going to be easy for the people. Yeah, there's a lot of work to be done in a short period of time. Here's what I want to give you as lessons learned. We found out that which makes sense, it's basically impossible to find an acceptable meeting time for people living around the globe. Sometimes I wish the Earth was flat. Because you could just say, okay, 2 in the afternoon is 2 in the afternoon, right? So, okay, but I think what I would be doing the next time is that we basically have alternating meeting slots. That you do it 1 week in the morning in Europe, and then it's good for the Asian part. If you do it then in the afternoon in Europe, then it's more good for the Western part on this planet. So I think that's one of the conclusions which needs to be thought about in the beginning, because if you agree on a slot and then you lose part of the audience there, because it would be in the middle of the night for them to participate. It might work in the real case, but at least for this exercise, I think that's something we should be doing better the next time. The second thing is called distribution lists. It turns out that we agreed on all sorts of stuff. We worked out, how to deal with nuclear explosive devices and things like that. But it was very difficult to get the right email addresses. So this is something where also we basically at the end said we need to do this in the structured way that the chair of same page informs the heads of the delegations. They have the responsibility to say, okay, this is my team. We tried it different in the beginning because we thought, okay, maybe it reduces a bit the workload of the people, but I think it's not the way we should be doing it in the future. We really need this structure in place so that the heads of the delegations, they have to take the responsibility to say, okay, this is my team, this is the people I want to have involved. I mentioned a bit the work package structure already, so let's go to the next point. We had a work package on decision strategy. There we basically concluded, well, it's not same page's task to decide anything. I keep emphasizing the A stands for advice. So that's basically, we discussed this only very shortly. And I think it would be good for the group to understand how decisions are being taken just to formulate the recommendations in a proper way. But that should be limited to that. That's it. In-person meetings and final recommendations, well, they're good. We spent some time after the in-person meeting to finalize the language, so that needs to be taken into account. We discussed the nuclear explosive device, where this is, of course, politically sensitive, but in the end, I think we also came up with good recommendations for that. And in terms of mission costs, I learned that you cannot provide mission costs in terms of US dollars or euros or yens. That doesn't make sense because every space agency has different approaches how to come up with a budget. See, there you go, that was the thing. And that's why we did what you saw yesterday, that we basically said, okay, let's scale the missions in terms of number of launches and the launch mass. And I think that was a good way of doing it. And that should be it. Thank you very much.
Our next speaker is Juan Luis Cano with the talk Overall Results of the Same Page Work Package on Mission Scenarios in Response to the 2025 Planetary Defense Conference Hypothetical Asteroid Impact Threat Scenario.
Thank you. Good morning. All right. So Detlef has already presented the work packages that were addressed during the exercise in the two epochs. And I would like to concentrate the discussion, this talk in the work package one, which was the one related to mission scenarios. And for that, I just wanted to point out that, to start with, that there has been a lot of people doing a fantastic work here within the different teams that contributed to this work package. And we decided not to, for economy, not to include everyone here, but just the leaders of the work packages. But keep in mind that there are really lots of people that have been contributed to this activity, and you will see that in the different presentations later. So I will go fast over the first one. I will divide the talk in two, in the contributions for the two epochs. And of course, you have already seen this. This is the framework of the first epoch for the scenarios. So you have there all the all the conditions that have been already presented, the trajectory, the cyanotic trajectory of the object, and the impact corridor. So I will not spend here a lot of time. Let me just go to the next slide where I'd like to point out that all the activity that we have been doing in the mission scenarios work package have hinged over a number of very relevant aspects that need to be considered. I mean, when we speak of deflection, many of these aspects have been discussed at length in previous occasions, but I would like to remind of those main aspects because they have clearly conditioned a lot the number and the type of solutions that we have that we had to consider and we have proposed for the consideration of the rest of the same page team. So in this case of this particular asteroid, given the large eccentricity of this object, the optimal deflection is achieved very close to the perihelion passes. So we have to always keep in mind that whenever we want to do that, we have to check and see where the perihelion passes are, and these are the dates where we would concentrate the action on those. Additionally, the deflection is cheaper the earlier you do it. So we clearly have to try to impart our deflection as soon as possible. And here I have some examples of what would it take as deflection if we waited for next perihelion passes. For example, if we did not start with 2032 deflection opportunity, we would need to invest 35% more in the next opportunity, or 95% more, so almost double in the occasion in 2037, or even 4 times in 2039. So this is very relevant. It was already stretched yesterday, but this is very relevant. It was very relevant for our analysis. And also the disruption. It's been taken into account very relevantly, the fact that we need to avoid possibilities of disruption. And we have used as proxy for this some empirical results that tells us that 10% of the escape velocity is a good proxy for disruption. So we have used that. And I wanted to let's say, graphically show that with these plots here. This is the delta V that could be imparted to a given asteroid of the size. These are points taken from the distribution provided by NASA Ames on the full population of possible asteroids for Epoch 1. And this is the imparted delta V by using this coefficient, which is the multiplication of the mass of the impactor, the velocity of impact, and the beta factor. So it's the momentum transferred to the object. And if you divide that by the mass of the object, you get the delta V imparted to the object. And of course, the smaller the object for a given impacting condition, the larger the deflection will be. And for example, this value of 10,000 kilograms per kilometers per second times kilometer per second, it's very similar to the case of DART. So if you do the math, it's very similar. If we multiply those effects by 5, we would be getting, of course, much larger deflection. But when we put in the plot also the disruption factor, which is linear with the size of the object, you see that it plots like that. So and if we are above those figures, we will be trespassing the limit of the escape velocity. So we would be in danger of disrupting the object. So we would need to keep below that let's say distribution, linear distribution there, in order to avoid the disruption. And this factor has been very relevant in all the exercise that we have carried out. So the work that we did in the work package during Epoch 1 concentrated in presenting at the plenary all these results that you will see later with the different contributions from the teams. NASA and several US institutions, Politecnico di Milano, University of Strathclyde, and ESA provided results in Epoch 1. Yesterday, we already discussed and saw from these results. I will not spend a lot of time, but you see how the possible missions concentrate in time and close to the perihelion passes in order to perform the needed deflection. The results you will see in the later talks, so we'll not enter into much detail there. But all this work allowed us to come down to the recommendations that you already saw yesterday. I will skim through them quickly. And because we already saw them, the possibility to start the importance of having a flyby reconnaissance mission as fast as possible, the possibility to use already flying spacecraft. They start the definition of the reconnaissance, flyby reconnaissance mission, the rendezvous reconnaissance mission. They start the definition phases for the deflection missions and the studies on impact deflection. So for the second epoch, again, these are the details. Just I kept them for the record. They were mentioned fully, and we discussed yesterday also the possibilities to perform southward and northward deflection and implications of a partial deflection in the southward direction. Sorry, you have already seen this. So we again redid all the calculations, read all the analysis with now the information provided by the flyby spacecraft, which of course you remind allowed us to get a much constrained size range and better knowledge of the impact area, possible impact area, and we decided to decouple a little bit from the plenary missions, from the plenary meetings. We were meeting regularly on Wednesdays and then reporting to the plenary on Fridays. And we got a fantastic set of results from the different contributors. You have them all there from the US colleagues, from the Politecnico di Milano and University of Strathclyde. And we also iterated on a mission interchange format where we could be able to provide the files with the emissions to the rest of the team. So this was also a very relevant result of our coordination activities. And we provided all this information to the plenary for discussion and agreement on the final recommendations. These are the results that you will see later, but we saw that between 4 and 7 spacecraft would be needed for the kinetic impact or deflection. For ion beam deflection, between 2 and 3 spacecraft for northward deflection, 4 and 5 for southward, and if partial was there, 2 spacecraft for partial southward deflection. And a single NED carrying different free flyers would be enough for the deflection. These were some other results of interest. And I'm finishing, so let me just, the recommendations we have already seen. Decide whether deflection will be northward or southward. Decide whether partial deflection would be an option. And select the deflection mission for the implementation. As a summary, this has been a great opportunity to gather the expertise of the different groups in assessing the threat. We have treated lots of possibilities and lots of conditions to the problem. And you have already seen the solutions. So I would just like to say thanks to the contributors to this work package, because it's been an amazing task and an amazing work done by all the members of the team. Thank you.
Our next speaker is Brent Barbie, giving the talk, NASA Analysis of Space Mission Options for the 2025 Planetary Defense Conference Hypothetical Asteroid Impact Threat Scenario.
Right. Thank you, Ashley. So today I'm going to be talking to you about the work done by our NASA-led U.S. team contributing to the same page work that Detlef and Juan have described. Juan did an excellent job of leading the overall set of same page teams. And Lindley Johnson and Kelly Fast were responsible for leading the NASA participation in same page, and reporting to them, we had the team shown here on the title slide, which consists of folks from NASA Goddard Space Flight Center, NASA Langley, NASA Ames, Lawrence Livermore National Labs, Los Alamos National Labs, JPL, and APL. So we had a lot of excellent help from multiple institutions on our US team for same page. Okay, let's see. Slide. All right, so we thought that this was a fairly challenging problem to solve, but what's actually going to be more challenging is to summarize 8 months worth of work in 8 minutes. So we'll see how well I do with that. You're already well familiar with the scenario, so I'm not going to spend a lot of time on this. Of course, you can ask questions about it at the end of this session. Happy to go back to it. But essentially, you're familiar with this asteroid that we have to deflect. And we also, as discussed yesterday, had a fast flyby reconnaissance mission, which significantly reduced the uncertainties in the object's size, but didn't move the needle a whole lot on density because the James Webb Space Telescope observations had already constrained that fairly well. So in the end, we essentially had a factor of 3 or so uncertainty in the asteroid's mass. And so we had to, for Epic 2, design the mission options to contend with that asteroid mass uncertainty. So here you can see in the plot on the right-hand panel, the lower right-hand side, the reduction in diameter and density uncertainty for the asteroid in consequence of the flyby. So that narrow blue strip of data points shows the residual uncertainty. And this object was nominally about 150 meters in size, give or take a bit, and elongated, as was shown in the simulated flyby imagery yesterday. We determined through B-plane analysis provided by CNEOS that we'd have to deflect it roughly twice as far to get it off the Earth in the southern direction as would be required deflecting it northwards. And that drives the requirements for all 3 of the deflection techniques which we studied, which included kinetic impactors, ion beam, and nuclear. The NASA Ames team also provided an assessment of the partial deflection option, identifying a point about halfway between the southern coast of Africa and Antarctica as a potential partial deflection point. Tsunami analysis didn't indicate any obvious, severe effects. It would certainly probably be safe for the southern coast of Africa, but exactly whether this would be acceptable for the Antarctic ice still would need some additional analysis. We employed a variety of different analysis methodologies. We had radiation transport codes and hydrocodes to address the standoff nuclear detonation deflection and the kinetic impactor deflection to constrain the behavior of the beta factor for the momentum imparted by the kinetic impactors. We had genetic algorithms that we employed for optimizing all of the trajectory options. We surveyed ballistic trajectories, including deep space maneuvers and multiple gravity assist flybys, as well as solar electric low thrust propulsion. We had optimization for multiple kinetic impactor trajectories, and we also had optimization for ion beam deflection as well. So we were able to combine all of that using a wide variety of techniques, as well as empirical models that provided heuristics that we use to constrain the designs. So we have engineering models that help us gauge how much, for example, kinetic impactor mass or nuclear yield we need to achieve a certain amount of delta V. And we also have heuristics that tell us how much delta V the asteroid can tolerate before the onset of unwanted fragmentation, or how much delta V needs to be imparted to achieve a robust disruption. So we were able to determine that robust disruption was questionable. This object might be something that could be robustly disrupted, but we couldn't be conclusive about that, so we decided to set robust disruption aside and focus on deflection. And at this object size, 150 meters, it turns out that that the heuristic that we have that you can impart more than 10% of the object's escape velocity per deflection delta V is actually a fairly limiting factor. It drives you to need multiple small nuclear devices and multiple kinetic impactors to get the job done. So for example, the optimized kinetic impactor trajectories that I generated, I found that when I deflected the object with a trajectory solution that minimized the applied delta V and was sufficient still to get the asteroid off the Earth, so it's essentially the most gentle hit you could apply to get it off the Earth in one go in the southern direction, which is the only direction that the kinetic impactors can go. It turns out that you're going to be imparting somewhere between, say, 15 to 30% of the asteroid's escape velocity is delta V, so that's as good as it gets. And so, that's the work to go. That's the frontier. We need to understand, is 15% okay? Is 20% okay? Is 30% okay? Because it makes a big difference. One 1,500 kilogram kinetic impactor could have gotten this asteroid all the way off the Earth in one shot. But we're not sure as of today as to whether that would have generated unacceptable fragments or disaggregated the two lobes of the contact binary. So that's the frontier. We need to get a better handle on the deflection versus disruption problem because it does drive mission design. So I'm going to flip through these charts quickly so I can make the points I want to make at the end, and then we can certainly go back to this during the question and answer. So essentially, we looked at how long does each method, kinetic, ion beam, nuclear, take to deflect the asteroid and how many spacecraft are required. Between 4 to 6 kinetic impactors unmargined would be required for deflection, completing between 2034 and 2037. Paul Chodas ran a large number of ion beam optimization cases, and the bottom line is that 1 to several ion beam spacecraft would be required, and it would take on the order of several years to complete the deflection, roughly speaking. For nuclear, only 1 spacecraft would be required, regardless of which launch opportunity you used, and nuclear also has the distinction of being able to complete the deflection at the final asteroid perihelion, which none of the other methods could do practically. So, summarizing all this, nuclear required 1 spacecraft to deliver multiple small devices to apply several detonations to deflect the object at perihelion. Kinetic, 4 to 6 spacecraft, and somewhere between, say, 2 and 5 ion beam spacecraft, depending on which deflection direction you want to take. This is the original version of the more understandable flowchart that Detlef showed yesterday that Tarek rendered. This has things numerically shown rather than with icons, but essentially you have to decide whether to deflect north or south, choose total or partial deflection, whether you want ion beam, kinetic, or nuclear, and then that determines the investment that would be required, the total number of spacecraft launches, let's see, I think that's the last chart. So before the gong sounds, I'll summarize that fragmentation versus disruption is a frontier. We need to understand that better. The team worked together really well, and I'm really grateful to all of our team members for all the good work. And now it's time to get off the stage. So thank you.
Our next speaker is Justin Atchison, presenting the talk, Retasking In-Flight Spacecraft for Rapid Response Reconnaissance in Planetary Defense Exercises.
Right, thank you. This is the thing here? All right. So I'm happy to present on behalf of the US team the NASA spacecraft that we looked at retasking. And when we say retasking, what we mean is an existing spacecraft that is already on orbit or potentially one that could soon be launched. In the case of the NASA spacecraft, the only upcoming one that could be launched was the Europa Clipper mission, a flagship. It was launching about 6 weeks later, and we thought that was probably not a viable option to consider for this. So we're at Epic 1 right now. It's August 1, and there is between a 2% at that moment up to a 10% over this Epic 1 time period of impact. And there are 3 spacecraft that NASA could consider retasking, but keeping in mind it's still a very low probability of impact at this point. The idea of retasking a spacecraft is that if it's already on orbit, then maybe it could be faster at reaching there. Maybe it could be cheaper, depending on how you think about it, and I'll come back to that. But the downside is that the hardware is not tailored to that particular threat, and there's no guarantee that the payload on board would give you the information you need, or that it could even survive some of the constraints that the new trajectory might require. So we looked at the OSIRIS Apophis Explorer extended mission, the Lucy spacecraft, and the Psyche spacecraft. So you saw in the same page recommendations that there was a task to look at retasking a spacecraft, and you may have seen in that big chart that the OSIRIS Apex spacecraft was one of the options that could do a fast flyby. So for quick context, OSIRIS was designed for a rendezvous and sample return from Bennu, and then after it completed that, it's now on its way to do a rendezvous with Apophis. So the premise here was, instead of rendezvousing with Apophis, can we get a fast flyby of 2024 PDC 25? And it turns out that you can retarget one of the upcoming Earth gravity assists and achieve a fast flyby, in this case, the 13.5 kilometers per second. And that raises the question, this is a rendezvous spacecraft, would it have the guidance, navigation, and control to be able to achieve this fast flyby? The only analysis we did was to say that we do believe it could detect the asteroid 3 to 4 days out so that a team could then begin to design maneuvers to do that close approach. But we didn't get much farther than that. And we did find that if you choose to do this, you would have to be giving up the Apophis extended mission. We could not, in this case, find even a flyby of coming back to Apophis anywhere near the time period of the Earth encounter. The second spacecraft we looked at was Lucy, and Lucy was built for fast flybys, or is built for fast flybys, and is going to be flying by the Jupiter Trojans. In this case, it also had an Earth gravity assist coming up, but it was much sooner, only a few months after Epic 1. So the task would be, would decision makers be willing to take this Discovery-class spacecraft that has been on flight for many years now and is on its way soon to the Jupiter Trojans, and instead of using the Earth gravity assist to push it way out to these Jovian distances, actually remove energy with this Earth gravity assist to bring it back down to do a flyby of this asteroid. It was certainly capable from a delta V perspective, and we could find a trajectory, but we would need to make the decision pretty much immediately when the probability of impact was still very low. And we were unable to then recover the Jupiter mission. So you would essentially be dedicating this Discovery-class mission to a fast flyby mission. And so earlier when I said that we would think of retasking as being cheaper, this does raise the question, if a Jovian flyby mission is a priority, would you then rebuild Lucy, in which case you would have actually spent more money overall than just a dedicated flyby. The third mission we looked at was Psyche. This is a very capable solar electric propulsion spacecraft that is on its way to do a Mars gravity assist and then rendezvous with the asteroid Psyche for a long period of time. In this case, what we found was that although Psyche has this great propulsive capability, it's already expended so much time raising its orbit to get out well beyond Earth towards this Mars gravity assist that we didn't have enough time to then cancel all of that to get back down to a place where it could do a flyby of the asteroid. So it turned out that we could not make Psyche work in this scenario. So that's why earlier in the chart that you saw from Juan, that OSIRIS Apex was the only option. And I forgot to mention earlier, I will note that in the case of OSIRIS Apex, it was getting there in summer of 2028, which was about the same time that a dedicated spacecraft would get there. And that's why our proposal was to send both, or at least consider sending both, because that allows you to have the tailored spacecraft that gets you the best science and has a high probability of working, but you have this backup option. In the event that something happens, and in the event you miss your launch period, there's still something that can get there to potentially get you some information. In the best case, if they both get there, maybe OSIRIS Apex gets you all the information you need from one particular viewing geometry, and then the OSIRIS Apex comes a few months later and catches it from a different viewing geometry to improve even further the shape model. So this has been focused on this particular hypothetical exercise. I will note we did look at this for two other cases, this idea of retasking. We looked at it a year ago for what was called the interagency tabletop exercise. And in that case, it was early enough in those three missions that there was still enough trajectory flexibility to reach it with any of those spacecraft. All of the same arguments would apply about whether it would be a good decision or not, but from a trajectory perspective, if you catch it early enough in the trajectories, we could reach that particular asteroid. And then for YR4, as we've heard, it's no longer hypothetical. But in that case, OSIRIS Apex was still the only option, and it was, again, using an Earth gravity assist. And in that case, the team was able to recover a flyby of Apophis afterwards, but not a rendezvous of Apophis. So the the conclusion still stands. You're effectively giving up your main mission if you want to retask. And so that's a question of whether that would be acceptable for your particular mission. So when this all started, I think it was an open question whether it would ever make sense to retask a spacecraft, whether it was even possible. I think our conclusion, and that is validated in the fact that it became a same-page recommendation, is that this is a viable approach that we should be considering as we go forward. And it probably only makes sense in a highly constrained timeline, but it's a useful tool to consider. Our observation is that Earth gravity assist were the most useful, or pretty much the way that we typically always reached the asteroid. And that's not particularly surprising, but it was good to see and to understand that. I'll continue the caveat that just because we could reach it from a trajectory perspective, it does mean that there's a lot more work to see, can that spacecraft achieve what we need it to do, and can it survive? And then the other conclusion is that if we retask the spacecraft, you are giving up its original mission. So these are all things that decision makers would have to weigh. And I've managed to save just enough time before the gong to say it was a great opportunity to work with the US team, and Brent did a great job coordinating us. And then with the international team, Juan did a fantastic job keeping a bunch of sometimes shy, sometimes grumpy engineers on task and keeping us focused. So thank you very much, and I appreciate your time.
Our final speakers for this portion of the session are Saverio Francisi and Elena Brazili, presenting the talk Analysis of Asteroid Deflection Mission Options for the 2025 Planetary Defense Conference Hypothetical Asteroid Impact Threat Scenario by the Italian Space Agency delegation at same page.
So good morning. Today we will present the Politecnico di Milano contribution to the hypothetical threat exercise as a part of the Italian Space Agency delegation at same page. So as we all know, at Epoch 1, the properties of the asteroid were quite uncertain, and therefore the first action to be taken into account was the development of a fast flyby reconnaissance mission. Our design was based on a grid search approach which allowed us to identify a solution flybying with the asteroid exploiting the 2028 pericenter of the asteroid. So after the simulation of the flyby reconnaissance mission issued by same page, an update of the asteroid physical properties was possible, and in particular also the identification of deflection requirements for the asteroid both in the northward and the southward direction. This allowed us to identify several deflection alternatives, which we then analyzed. And in particular, we considered the multiple kinetic impactor and the nuclear explosive devices as impulsive alternatives, while as low push-pull strategies, we considered the gravity tractor, the enhanced gravity tractor, and the laser ablation and ion beam deflection, both of them in a single and multiple configuration. The departure conditions were fixed for all the strategies which we considered, the launcher being selected as the Falcon 9, and the launch window first available launch date on the 1st of June 2029. All the models which we developed for the different strategies were integrated into an optimization framework which aims at maximizing deflection performance while minimizing the overall mass launched in space for completing the deflection campaign and the warning time. The optimization also leverages some constraints to avoid the asteroid fragmentation and ensure a feasible spacecraft design. So regarding the multiple kinetic impactor strategy, specifically, it only allows for a southward deflection of the asteroid, and our design was based on the mean physical properties of the asteroid with the momentum enhancement factor selected as the mean value of the distribution associated with the relationship between the momentum enhancement factor and the asteroid density, which was a result from the data gathered from the DART mission. So 3 spacecraft were found to be sufficient for ensuring the southward deflection requirement, exploiting the 2032 pericenter of the asteroid. And from the Pareto optimal set of solutions, the maximum deflection mission can be extracted, which will be referred to as the nominal solution. Then a sensitivity analysis to the variation of different kinematics and physical parameters was performed, applied to this solution, to assess the mission robustness in terms of deflection requirement and fragmentation avoidance requirement. So just the physical parameters were found to pose a threat on the mission robustness, and in particular we considered 5,000 different samples for the mass distribution combined with 200 different samples for the momentum enhancement factor, which led to solutions all compliant with the minimum impact parameter requirement. However, almost 40% of the samples will not comply with the fragmentation avoidance requirement for the identified solution. Therefore, modifications to the nominal solutions were applied to find a new solution employing a larger number of spacecraft, each of them imparting individually smaller variations of velocity to the asteroid. And this solution also exploits, as the C3 spacecraft one, the 2032 pericenter of the asteroid. And to this solution, a new sensitivity analysis is applied to find that this solution will perform robustly, at least with a 2 sigma confidence level to the variation of the different parameters.
Okay. So, differently from the multiple kinetic impactor strategy, all the other deflection techniques that we have analyzed in this work exploit a time-optimal low-thrust trajectory to rendezvous with the asteroid, while still ensuring the spacecraft design feasibility in terms of structural mass and amount of fuel stored on board. Given their high TRL and XC thrusters are mounted on board each of these mission designed, and the asteroid properties are considered the epoch 2, so extracting the most useful asteroid size realizations from the provided distribution, we see that there is a still uncertainty factor of about 3.5 in the asteroid mass that causes significant variation in terms of deflection performance. Now, any of the rendezvousing deflection strategies can deflect the asteroid either northward or southward. Since the southward deflection moves the asteroid through lower densely populated regions before completely missing Earth, initially a full southward deflection is attempted and is successful. The result in terms of deflection is highlighted in blue. If not, then a full northward deflection is attempted, which moves the asteroid through higher densely populated regions let's say, through before missing completely Earth. If also deviating northward cannot prevent the asteroid impact, then the result shows the corresponding partial southward deflection to redirect the asteroid towards the Southern Ocean. So these are the proposed deflection campaigns with the send-off nuclear explosive devices in a carrier configuration. So one spacecraft equipped with multiple nuclear explosive devices. Several campaigns are proposed, each exploiting a later asteroid perihelion to perform the detonation events, which are symmetrically spread around the asteroid perihelion with a time separation of 14 days to allow the asteroid to recompact itself after each explosion. Later campaigns require an increasing number of devices to ensure a full deflection of the asteroid at least northward, to which there is an associated decrease of the charge per device to ensure the spacecraft design feasibility. Decreasing the charge is not a problem, as the optimizer can adjust the send-off detonation distance to always apply an impulse to maximize the deflection. Moving to the ion beam deflection technique, early primary and secondary campaigns are proposed, and the approach here is to find what is the minimum number of spacecraft required to ensure a southward deflection of the asteroid. So later campaigns and higher asteroid size cases require an increasing number of spacecraft. For this strategy that uses a lot of fuel to accomplish the deflection, to avoid inefficient fuel expenditure, the deflection is performed in arcs around each asteroid perihelion, and it is suspended when moving towards the aphelion, where the deflection is less effective. Similar is the approach with laser ablation. Again, early primary and secondary campaigns are proposed. Later missions require higher number of spacecraft, but the maximum number of spacecraft is lower than the one of ion beam deflection, and this is mostly due to the high power level that was considered for the laser system. However, laser ablation suffers from a lower technology readiness level compared to ion beam deflection, and therefore it was discarded as a viable option to deflect asteroid 2024 PDC 25. The standard and enhanced gravity tractor techniques, only early and primary campaigns are proposed, as later missions do not have sufficient deflection time to achieve a significant deflection of the asteroid. And specifically among the proposed missions, only the early campaign of the enhanced gravity tractor is capable of fully avoiding an impact either northward or southward. So in conclusion, among the deflection techniques that we have analyzed and applied to this specific scenario, the most viable options to deflect this asteroid are for sure the multiple kinetic impactor strategy, which requires 6 spacecraft, but the deflection outcome strongly depends on the physical properties adopted at this stage for the asteroid. As an impulsive alternative, also nuclear explosive devices proved to be the most effective single spacecraft strategy, capable of delivering as many impulses as needed, specifically 13 impulses, to ensure a full deflection of the asteroid even when the detonation is performed at the last useful perihelion in 2039. Also, ion beam deflection is promising. The early campaign with 1 spacecraft would ensure a full deflection at least northward, but has a quite stringent development timeline. So the most promising mission is the primary, which launches in May 2031, 2 spacecraft or 3 to provide also some level of redundancy, while the secondary campaign remains as a backup or an alternative option. Thank you for your attention.
We'd now like to invite all of the speakers from this session back up on stage, and we'll do a Q&A session here. We're working on getting the question and answer on the app. So if people want to post questions in that when that opens up. While we're waiting for some more questions to come in, we have one question for Juan Luis. One of the most critical aspects of any mission is the time criticality. At the end, the spacecraft have to be designed, built, tested before launch by industry. Industry knows best what it needs to do this job in terms of supply chain, resources, schedule, et cetera. Is there a reason why industry is not involved in the exercise with their expertise in this specific domain?
Okay. The framework of the exercise has been within the same page delegations. So delegations were actually nominating some representatives to participate in the exercise. To that end, we also had to take assumptions on those development cycles. So and we actually did that. We counted with expertise of several of our experts in trying to assess what is the time needed, for example, for a phase A, phase B, phase CD. So we already took into account all those constraints in our assessments. So even if there were no industry people within the team, but we had the expertise in order to take into account those constraints.
All right, we're waiting for a few more questions to come in online. That question and answer section is open on the agenda now for you to post questions. The next question is for Elena and Severio. Would one kinetic impactor reduce physical parameters of the asteroid? Can this refine subsequent KI missions?
Yeah, for sure it could be an alternative, but then we'll need to wait some time to have the outcome of that single impactor, and therefore it could be too late then to develop as many impactors as we may need for a successive campaign, deflection campaign.
Can I? Just one thing to add up, for sure, it would reduce the uncertainty and it would probably give us an estimate of the momentum enhancement factor, which, however, could also change with structural variation of the asteroid after the first impact, but at least we could get a rough estimate of what could be the momentum enhancement factor. And the subsequent impactors, there were discussions about this to launch spacecraft multiple impactors which could shed some mass, so with scalable mass, such that they can adjust the impacting mass as we get the results from the first impact. Because the later impactors should be launched before the first impactor arrives and impacts. So it's important that they could be scaled down by releasing some mass.
Our next question, for scenarios requiring multiple launches, were the consequences of failure for a subset of the launches taken into consideration? Anybody interested? Brent?
Yeah, I can take that. So the two things I'll say about that are that in the results, we caveated them by saying that, we would plan to include, let's say several more spacecraft and launches than the baseline number shown to provide some redundancy in the event of failures. So that information was included in the material, although we probably skipped over that when we were talking quickly this morning. And the other thing I'll point out is that during the last calendar year, I think we had something on the order, at least in the US, of about 120 launches. So that's like a launch on, every 3 days on average without any, significant failures. That's a pretty low failure rate. So it's not to say that we would be dismissive of the possibility of failure. It's just that, it looks like it's been pretty robust. And then secondly, by planning for, several extra spacecraft launches, you can provide coverage for a failure.
If fragmentation does happen, and it would be in 2 or 3 pieces, has it been discussed what would be the next steps to be taken?
Well, so the other thing we glossed over is that one of the things that's emerged from studying this field is that there's fairly unanimous agreement that we would insist upon having a rendezvous reconnaissance spacecraft on station with the asteroid before we touch it for the very first time. Now, obviously, you can imagine some shorter warning situations where that's not practical, and then we'd have to just do best effort. But with a spacecraft in place to monitor what's happening, we would at least be able to track any significant fragments in situ. We'd have an opportunity to do that, where, of course, if you don't have a spacecraft there, then that's essentially impossible, or maybe very difficult, depends on how big the fragments are. So that rendezvous reconnaissance spacecraft would give us persistent situational awareness that would allow us to track fragments.
Maybe to add to that, as you have seen, we have taken special care in considering the fragmentation possibility. So, and of course, we cannot discard that maybe it could happen in the end. But given also the fact that there are lots of impactors needed in order to do the full deflection, and also in the case of the NED solution, there are several devices that would need to be, let's say, deployed and operated in order to achieve the deflection. If there are different fragments, we could even target differently the fragments in order to achieve the full deflection. So I guess that also gives us robustness in the case of fragmentation.
How long do you have to wait between individual kinetic impactors? Do you have to wait for debris or plume to settle?
Yes, there's several considerations. One is that you'd like to evaluate the effect on the asteroid's orbit. We have another talk, I believe it's today, by Rahil Makadia, who did analysis. He was working with Davide Farnokia at CNEOS, and essentially the finding was that you want to allow for about 2 weeks in between strikes so that the DSN tracking of the rendezvous reconnaissance spacecraft, which also has optical navigation on the asteroid, can then give you a good sense of how much delta V was applied, so then you can calibrate for the next strike. So the answer is roughly 14 days at minimum, which we did enforce in our simulations. So one of the great things about this same page team, Juan was organizing us, and we were all working together and exchanging data, so we were able to harmonize on these parameters between the different teams' analyses, which worked really nicely. So I'll take the opportunity to say that. But then the other thing is the debris, right? And so, you generate all this debris from the impact, and it's all going to be a power law distribution, right? And so the majority of the debris is small, has high area to mass ratio, and solar pressure will blow a lot of that away fairly promptly. We saw the tail form on Dimorphos after the DART impact, and so in practice, we'd probably include some Whipple shields to provide some debris protection for the spacecraft as they come in, but a lot of the smaller stuff would blow away, and the slower moving faster stuff would have plenty of time to drift out. So not to be dismissive of it, I mean, one of the next steps is to actually do those models. We haven't actually done the detailed modeling of that, and I look forward to running some models to sharpen the pencil, but that's our thought process as we analyze this.
All right. Could you please elaborate a bit on the capabilities of an enhanced gravity tractor? For instance, the magnitudes of deflection possible within a certain time frame.
Yes, so the enhanced gravity tractor concept collects additional mass from the asteroid surface. So it depends on the amount of mass that is collected. Now, these can range depending on the spacecraft mass and the spacecraft capability to collect mass, but also on the asteroid location where you collect the mass. So roughly it can vary from 10,000 to 100 tons kilograms. In our simulation, we selected 50 tons of additional mass collected from the asteroid surface. In terms of time frame, the gravity tractor requires a longer period to accomplish significant deflection. Tens of years would be required with a standard gravity tractor, so without collecting additional mass. And so the enhanced gravity tractor scales down this time frame, but still it depends on the asteroid properties, on the asteroid mass mostly, since it's gravitational attraction. So it would require at least 10, 15 years to accomplish significant deflection. In fact, the enhanced gravity tractor early campaign launching in early June 2029 roughly has the 10 years frame, and it in fact fully deflects the asteroid at least northward, which has a deflection that is approximately half. So roughly 10 years, in the tens of years onwards.
Thank you. Would a rendezvous spacecraft better constrain the impact point on Earth of the spacecraft? Would it be helpful to have a rendezvous spacecraft as an observer of the deflections?
Yes, one of the things I mentioned in my comments a few minutes ago is that as a sort of an operational best practice, we designed to have a rendezvous spacecraft in place before the first strike on the asteroid to provide that situational awareness. So the answer to that is yes. And yes, the rendezvous spacecraft does indeed better constrain the impact point on Earth. Davide could give a precise answer. I think, with a rendezvous spacecraft and that data, you can get the impact point down to like a few kilometers. So you can be very precise with, the impact point of the Earth of the rendezvous spacecraft.
Maybe we can also go back to what Davide mentioned yesterday. Already with the flyby reconnaissance mission, the area was already very much constrained. So we went down from a large impact corridor to a very constrained one. Of course, having had rendezvous with the asteroid would have improved that substantially. But as a first response, the flyby spacecraft would already provide, and as we saw, a fantastic result on the place where, more or less, would impact the asteroid.
In yesterday's panel discussions, we talked about our options for deflecting either north or south. So is it possible to deflect the asteroid sideways?
Well, in principle, the celestial mechanics are pretty clear here. So any effort that you do in order to deflect the asteroid will move the impact point along the corridor that we have already seen in the slides. So there is not much that we can do in order to move the impact zone out of the impact corridor that we already know. So that's pretty clear.
To that, I'll add the nuance there. Essentially, the way that we do it is we look at the partial derivatives of the B-plane coordinates of the asteroid with respect to delta velocity in each of three axes. And so to elaborate on what Juan was saying, as he said, if you deflect it in essentially the asteroid's velocity direction, then you move it along the corridor. And those partial derivatives are like, a couple of orders of magnitude larger than the partials associated with moving it orthogonal to that. So you can move it sideways. It's just that you can only move it, a relatively small distance sideways for a certain amount of effort compared to how far you can move it, in this case, north-south. So we would have some sideways steering capability, but, for smaller distances away from the main line.
All right, the next question is for Justin. Have you considered the option of retasking a spacecraft not for a flyby, but for a rendezvous?
Yeah, so this is something we certainly looked at. Unfortunately, so the downside of retasking is that you no longer have this very capable launch vehicle that's going to send you on a very specific trajectory, and that's typically what a rendezvous requires. When you think of a rendezvous, you have to match the orbit of the asteroid, and that is a great deal of delta V, and it's very hard to beat a launch vehicle for achieving that. And if you're already on orbit, you can use gravity assist, but in any of the cases we looked at, it just wasn't feasible. So you would have to settle for a flyby, I think, in most retasking cases, unless you were just incredibly lucky, I guess.
Okay, the next question is, was the availability of different launch vehicles considered for multi-launch campaigns?
Yes, in the sense that, as I said before, we did a survey of, actuals for launches in the prior calendar year. And as I said before, the average launch rate was a launch roughly every 3 days. Now, the nuance there is that most of those were Falcon 9s, and that during that year, only a total of 3 Falcon Heavies were launched. And some of our campaigns would in fact need Falcon Heavies, but some of the launches that we showed would fit on a Falcon 9, in fact. So if we were doing this for real, we would have done a deeper dive into the specifics of the launch vehicle procurement, but at the level that we did the exercise, we didn't take it quite that far. So it's a fair thing that we would consider more in actual case.
We've already talked a little bit about how long we need to wait between successive kinetic impactors. How confident are we in that? How well do we understand that?
Well, I already made some comments about that. Does anybody else have any? I mean, it's essentially debris clearing and estimating how much delta V you put in the asteroid. No, Severio said, maybe I'll elaborate on what Severio said, because Severio was talking about the idea that, and I think Elena talked about this also, about this idea that you would want to look at the results of the kinetic impact to essentially get some idea of the asteroid response, like what the beta factor was, and then you all pointed out that beta might change between subsequent impacts because the structure of the asteroid's affected. So it's not going to be an exact science, but I agree with the point you made, which is that you would at least learn something, right? So we would be able to dial things in a bit between impacts.
So final question here. It seems like a single nuclear mission makes the most sense. One mission, single explosion, cheapest, simplest, most likely to succeed. Should a big part of the focus not shift towards working towards a more acceptable use of nuclear technology in space?
Right, I'm going to take that. I think that's a question to the decision makers. I mean, same page has the task to put the facts on the table and advice. I think we did that. You saw that yesterday. We said, okay, these are the different options. And this is really outside the scope of at least same page. So it's a valid question, but I don't give an answer here. I think we need to address the question to other people.
Detlef's comment there is that on the decision to act session on Thursday, we'll have some presentations that delve into this more. But apart from that, I fully agree with Detlef.
Thank you to our speakers for the presentations, excellent jobs, and for answering our questions here today.
Yeah, thank you. So we reached the time of the first coffee break, and I think this impressive gong worked very well to keep the time. So we now have 25 minutes of coffee break. I guess you all know where to find coffee or tea, and please be back on time at 10:30. Seats again. Ja, ich habe jetzt gefragt, die geben uns eine Glocke. Habe ich gleich eine Glocke. Ja, der Gong wäre auch gut, aber Glocke ist dann nicht schlecht, glaube ich. Okay, I think let's continue with the second part of the session 1 on the threat exercise. And before we do so, I would like to remind you to look at the text, or it used to be displayed down there, maybe, yeah, there you could see it. Because for this second part of session 1, we should have all presentations available for display. But for the afternoon, some are still missing, and of course for the following days. So please take a note down here, and if you have not done so, send an email at the address given there with your presentation. So for this afternoon, a few are still missing. Please don't forget it, and obviously also for the coming days. If you have not done so, please send it by email, and if it's not possible to send it by email, then please provide them to those experts here in the back, maybe on a USB stick or however, but this can only be done during breaks, not while the presentation is running. Okay, thank you. I hand over again to the chairs.
All right, welcome back. So just a couple reminders, speakers have 8 minutes, and then there is an amazing gong reminding them the time's up. That's gonna cause a massive unemployment problem for session chairs, I think. And then questions, there is a Q&A discussion at the end. Please submit your questions right there so that we don't have to go flip through the different speakers to combine them together. Okay, let's get started. The first speaker is Marco Fenucci, who's going to give us the perspective from the ESA Annual Coordination Center on the impact exercise.
Thank you, Davide, for the introduction. So in this talk, I'm going to show you what we did at the ESA Annual Coordination Center about this hypothetical impact threat scenario 2024 PDC 25. And what you're going to see is kind of complementary to what JPL, to what Davide showed yesterday from JPL. So at the beginning, we wanted to try to understand what happens before Epoch 1. How do we reach Epoch 1? So we started from the very beginning, and here in the left plot, you can see how the impact probability evolved towards Epoch 1. At the beginning, at discovery, the impact probability was very low, of the order of 10 to the minus 7. And it stayed quite low for a couple of weeks. And after a couple of weeks, actually, the impact probability goes up to 1 over 1,000, and Torino scale becomes 1. And this is when the community really gets involved into this. It gets notified. And it took about a month to reach Torino scale 3, similar to what happened for wire 4. And the other plot on the left, I really like it. I think it's really comprehensive. It's basically the theoretical impact probability as a function of the uncertainty on the target plane for different close approaches. So these curves, these black curves, correspond to different close approaches, and you can see that the uncertainty is consistently shrinking as we get more data, and the impact probability is going up, which is what we want to see. This is similar to something that Davide showed yesterday. It's the the close approach in 2041 with the data we have at Epoch 1. It's really similar to what JPL obtained. We compared these results. And this you saw many times these days. It's the impact corridor that we computed. It's our version of the impact corridor, which crosses Eastern Europe, crosses the whole African continent, and goes down south towards Antarctica. So I can skip fast for this. Another thing that we were asked by same page was an analysis of the keyhole. In fact, PDC 25 didn't have only one impact in 2041. It had a lot more virtual impactors farther in the future. And same page asked about these keyholes. And here you can see this Z parameter on the x-axis, which is a parameter on the B plane that basically parameterizes the uncertainty region. There is a PDF of the virtual asteroids, which is quite Gaussian. And all these vertical lines are the different keyholes for future impactors. And the location on Z, it tells you how distant is from the nominal. While the height of the vertical line tells you the width of this keyhole. And there's also the epoch of the future impact. What same page was interested into was keyholes at negative Z values, because as we saw these days, if we are to deflect the asteroid, we would deflect it south along the impact corridor, which means moving it towards negative Z values. And to be sure that we did not deflect the asteroid into one of these keyholes, we needed this map. And as you can see, the keyholes are very narrow, of the order of maximum 10 kilometers. Another thing that we did was analyzing how the impact probability would evolve before PDC. So the asteroid was visible until December. So now we will be in a situation where the impact probabilities kept growing up to 37%, still at Torino scale 3. And the uncertainty will be as small as 3 Earth radii, more or less, with a close approach smaller than 2 Earth radii. But still, it wouldn't reach 100% at the PDC, let's say. So another thing that we were asked by same page was when we would be able to tell for sure whether the asteroid was going to impact or not. So we saw that if we arrived to this epoch, we wouldn't be able to tell this. So we have to keep going for looking farther away. And we could go fully Monte Carlo and explore how the probability would evolve, but we tried to do something different. So the next apparition of PDC 25 will be October this year, let's say September, October this year. And the object will be recoverable by, for example, So what we did is computing the sky print, the uncertainty in the sky of the asteroid, which is this blue region that you see in the plot. And this uncertainty region is long about 4 arc minutes. On the other hand, you can also compute where the VI is going to be along this region, the 2041 VI. And we found out that we computed that this region where the VI is along the uncertainty region is about 2.5 arc-second long. On the other hand, if we get astrometry with VLT, we can get astrometric position with a precision of 0.1 arc-second. So at this point, there are basically 3 possibilities. The first one is that we find the asteroid inside this red region of the VI sky print. And at that point, the impact probability will be 1 for sure. We either find it outside the VI skyprint within, of course, still, let's say 0.1 arc-second precision. And at that point, the probability of impact will be 0. Or there's still a very remote chance that we measure it at the border between the red and the blue region. And in this case, the orbit is almost grazing, and we would need more observation for that. But let's say what was released later at Epoch 2 during the exercise, it was saying that in September we would know, we would have a 100% probability of impact. So it was nice to see that this approach was consistent with what was released for the exercise later. And with this, I finished my presentation, and it was important, to exercise so that when real cases happen, we're ready. So thank you for your attention.
Thank you, Marco. Next up is Jessie Dotson, and she's going to talk about the effect of prior knowledge on planetary defense scenarios risk assessments.
Okay. When we're doing the risk assessments or the mission planning that you guys have heard so much about, there's some really key inputs, and we just heard about the orbital inputs and understanding where the impact corridor is. We also need to understand about the physical properties, and very often in the scenarios early on, we don't have JWST measurements. We haven't had months to do all the characterization, but yet we still want to start doing initial assessments. We want to start doing initial risk assessments. We want to start getting a head start on mission planning and mission designs. And so to kind of fulfill that need, I've developed a physical property inference network where you leverage the information you have about either the particular object or the population so that you can come up with what are plausible ranges. Because you don't want to just do the nominal. You can fool yourself if you just do the nominal. And if you don't take advantage of the information you have, you're being overly pessimistic. And so the goal of this network is such that the distribution of the values are plausible and appropriate for the scenario, and that the combination of any of these properties for any of these individual virtual impactors is physically plausible. So you don't end up with things that are very, very dense and very, very light, for instance. I've given talks about this before, but just to orient you on where I'm going to go with this, the way I've set this up is this is a combination of, you can think of it as nodes, where you have nodes for which you don't have parent information. Those are kind of starting nodes. You've got nodes that you can calculate, like if you have H and albedo, we know how to calculate diameter. You've got nodes where you do probabilistic inference. For instance, if you have the albedo, you have an idea of what the taxonomy could be, but you don't know. And so you want to have those relationships in a way that don't emphasize the information you have, but they don't underemphasize it either. And so where do the priors come in? Well, the priors come in with what is our information, what do we know about the population that's out there? And here in a discovery epoch, what usually happens is we have a measured brightness and we have nothing else. And we use this network to figure all the rest of it out. And in particular for the albedo and the porosity, we base those on the priors based on our knowledge of the population out there. And so studies of the population are super important in these early phases. And I'm going to dig into what priors we have in here and what they mean. And so here, I'm just going to show you 6 different possible prior distributions for albedos. Okay, the one we use that is on all the behind all the charts that Lorian shows you is the first one, the base one, and that is basically just we took the NeoWise cold albedo measurements from Mainzer 2011 and just said, what's the distribution of those albedos? The minimum albedo is a little bit lower than the minimum measured albedo to kind of say there's some measurement error in here. The real value might be a little bit lower than what was measured. And so that's what we use for everything. But for this exercise, what I did is let's vary that minimum albedo, because it's always like, how dark do you really think things can be? The second one, I set the minimum albedo to be equal to the minimum measurement. The third one is the minimum albedo is equal to the minimum measurement plus a couple sigma. So saying I really don't believe that low measurement, I'm going to move it up. The bottom row, the first prior, Wright et al. Had a paper where they basically took the same data and fit two Raleigh distributions to it, so it's an analytical representation. So slightly different shape, but again, I set the minimum to be the same as the lowest measurement. And then I also took a look at what happens with two completely uninformative priors, a flat one that does the whole range, and then a flat prior that kind of spans the most likely albedo, which is a common thing that people do. Oh, we think it's probably between here and here because most albedos are between here and here. So if we put these different priors in, what kind of results do you get out? Well, let me orient you a little bit on a box plot. That big horizontal line is your median. The box itself, the bottom is your 25th percentile, the top is your 75th percentile. And then you can see I added a couple points to get you higher percentiles, lower percentiles, and then the light gray dots are outliers. And really the conclusion here is I hope you can kind of see that if what your, the central portion of the distribution depends on the shape of the prior, but not so much on the limits. But if you want to start really understanding what are your worst cases, those limits and the shape become really important. And that was in diameter space. Here it is in mass space. And you come to a very similar conclusion, which is the extremes depend on both the limits and the shape of the priors. And the central portion really just depends on the shape of the priors. And here's just one slide to make the point even bigger, which is these are the maximum values in this run. And basically, you never want to use a maximum value. It is very susceptible to like the details of your priors, the details of your assumptions, and your sampling noise. So, I think I'm not a big, even if you want to understand your full range, I don't believe maxes or mins are really informative. You're probably fooling yourself if that's what you do. So kind of to summarize, so then now that I've bored you guys with distributions and histograms, what's the answer? What's the correct prior? And this is one of my answers I always give is it actually depends. And so if what you're trying to understand is just what's the central distribution, that's really easy. We know how to do that. If you're trying to understand the bulk of the distribution, the shape of the prior is important and the limits are less important. And we know how to do that. We have great data from NeoWise. We know how to do that. But if you want to start to get to where you understand the extremes of your distribution, it gets really, really hard. And so when you're looking at the extremes, you have to really think, do I believe this? Do I believe my assumptions? Now I can go through a similar exercise with the porosities, and I'm not going to step through these in quite as much detail because I know the gong's going to ring on me. But you can see I've tried different truncated Gaussians, changing the mins, changing the maxes, doing a flat distribution. And with porosity, you can see it does vary a little bit, but not nearly as much as with the albedo, because the porosity does not have as big of an effect as the albedo does on the inferred properties. And so then what's the correct porosity prior? Well, again, it's actually pretty easy if you're looking at the center. If you really want to look at the extremes, it becomes hard. And this is one of those things where we don't have the data on what the real porosity distribution is in terms of the limits. And if you add any data at all in here, as soon as you get like a taxonomy measurement, the priors become much less important. And this is all for the PDC 2025 case. And you can see as soon as you get a taxonomy measurement, those box plots for the diameters doesn't depend a whole lot on your priors. So as the gongs ring, I'm going to say that your priors matter more or less depending on what the value is and what your use case is. And so this is a scenario where if you're trying to, the right statistic depends on the question you're asking. So as you're trying to use these distributions, ask a question of your favorite statistics nerd. All right, there we go.
Thank you very much, Jesse. Next up is Mark, who's gonna scare all of us. Simulation of the PDC 2025 asteroid entry, terrestrial impacts, hazard and consequences, with emphasis on South Africa's Stellenbosch and False Bay communities. Sorry. Yeah, I got that wrong. There should be a gong for incorrect announcements. Ashley.
All right, I'm going to be talking about the effects of uncertainty on our pair model results and the value of gaining additional information. So this is going to build on what Jesse just talked about. We have multiple sources of uncertainty in NASA's pair model, but today we're going to focus just on inputs that we can improve with additional information. The goal here is to understand the expected benefit to our risk knowledge from gaining additional sources of information. We're going to use the PDC 25 hypothetical scenario sort of as a case study here. We'll highlight pair model input refinements, evaluate the effect on outputs, and then analyze our overall knowledge gain from JWST and flyby observations that we had in this scenario. We're going to focus on diameter, latitude, and entry angle for our inputs. With those, we can determine energy and burst altitude ranges, which are the inputs to our local blast damage model. We're going to focus on blast here because, as we learned yesterday, blast is the primary local hazard. We can also determine population density ranges, and together with damage radius are the inputs to affected population, which are going to be our two outputs of interest there, damage radius and affected population. Everyone should be familiar with the exercise. In this work, we're going to use 3 different asteroid property sets, 2 different entry parameter sets, and we'll use these in different combinations to understand the effects of uncertainty. This timeline is going to help us keep track of which sets we're looking at where. So this is corresponds to the PDC timeline here. We get property updates at epoch 1 and 2, and then entry updates are ongoing as we continue to get more observations. We're going to jump straight to the outputs for the sake of time, starting with damage radius. These are results for the serious damage severity level. On the left, we have a histogram there showing the probability of a given damage radius. Down below, we have some bar graphs that are highlighting the min and max values of that range. The median value is that vertical line, and then the most likely ranges are the dashed boxes there. So uncertainty refinement we're going to take today as how much this overall range changed, so the difference between the min and the max here. There's a lot of numbers on the right, mostly for reference later if you're looking at it. We're not going to get to all of them. On the top, we have some information about the inputs. Then in the middle, we're really trying to understand what we're going to gain as far as output refinements from each of the input refinements. So we're seeing asteroid properties, about an 80% return, entry properties, about a 30% return. Overall, we're seeing about 82% refinement by the time we get to epoch 2 relative to our original baseline case. Back to our timeline, we're now going to think about what happened if decision makers decided we don't need flyby. What if we just had the original property update from James Webb? Our returns are pretty similar, 60%, 30% here, so that was pretty similar to the previous chart. Our light green color here is the one that we've added, and we do get some refinement from epoch 1 because of those entry updates, but we don't make it all the way to epoch 2 refinement levels without that property update. We're forfeiting about 20% of our refinement by foregoing flyby. So we looked at no flyby. What if we also didn't have access to the JWST updates? So what if we only had entry updates throughout the whole scenario? This case, we saw about 40% return. Again, that's pretty similar to what we were seeing in the other cases. You see we get some refinement, but still forfeiting about 43% in this case by foregoing both. Affected population is our second output of interest, so we'll look at those same things, but now for affected population, back to the PDC scenario where we have both of those property updates. Here we see sort of the opposite result of what we saw with damage radius. We're now getting returns of about 30% for asteroid properties, 60% for entry parameters. And again, about 81% refinement all the way through EPIC 2. So if we go back to the case where there's no flyby, similar returns here. Again, you see the light green. On these log scales, it really looks a lot more like EPIC 1, but if you start looking at those most likely ranges or on the histogram, we really are shifting towards EPIC 2 and are forfeiting only about 10% in this case. And then the final look at this timeline, going back to the case where we don't have JWST or the flyby. Here, we're seeing only a 4% return on those entry parameters. Again, we're seeing some shifting towards EPIC 2 with the most likely type ranges, but without the diameter refinements from the 2 property updates, then we're retaining some of those larger air bursting cases in the distribution, and that's really causing our affected population range to remain high, forfeiting quite a bit at 77%. So talked about at the beginning that we really wanted to understand the expected benefit to our risk knowledge from gaining additional sources of information. We did that here for this very specific case, just for PDC 25 scenario. And so going forward, we'd really like to conduct a more general study to map out some of these expected benefits across different size regimes from additional information sources so that we can hopefully create a resource or rules of thumb for our decision makers to be able to help them think about what information they need, when they need it, and in context of what information they could expect to get from these different information sources. This could have implications on some of the other efforts going on at the same time, mitigation efforts or evacuation efforts, to think about what we're gaining on the risk side also. So as I'm finishing up here, as we were thinking about this work, we were really trying to understand would this be helpful to decision makers? Would this information change their mind at all? So for the decision makers in the room or everyone else, think like a decision maker. If you knew some of this information ahead of time about what we could expect from flybys or from JWST, like would that change how you made your decisions? Would that have made a difference in what you were suggesting to do? And then just a quick thing at the end here, some other relevant talks for this. Lorraine is coming up in a couple days, and of course we just heard Jesse. And then a thank you to the PDCO for funding this and for Ames Supercomputing for the compute resources.
Thank you, Ashley. So let's try this again. Mark, this time you're up for good, and you're going to talk about a simulation of the entry right here.
Okay, so I'm actually filling a gap, and I'm repurposing a talk I gave last September to talk about the tsunami risk. And in order to beat the gong, the only way I could think to do that is to put my main points up front, and this is a repurposed talk, so I don't have these points written down. And the first point is, those of us who do modeling in support of risk assessment have a tendency to believe our own models, but a model isn't really good until it's been validated somehow. And we don't have that many validation cases for impacts or airbursts. We had Tunguska in 1908, we had Chelyabinsk in 2013, and then we had another validation opportunity, and that is this volcanic eruption, explosive eruption in January of 2022, the Tonga eruption. And so that gave us an actual case of a tsunami generated by an airwave. And this is something that we've talked about in our community for a while. And we, in fact, had a big meeting only a few years before this at NOAA, where we tried to come up with a way of quantifying this, and we completely overlooked the process that created the global tsunami from the Tonga eruption, and that is a global land wave, a very high amplitude, long period, long duration atmospheric wave that swept around the entire planet. So we didn't even consider that a few years ago, a few years before this event. So that's the first point. The second point is one thing that this taught us that we didn't appreciate beforehand is that even airbursts or impacts on land can generate a tsunami. And it's counterintuitive. It's something that I think the panel up here yesterday didn't understand. And based on a lot of the questions from this group, people don't appreciate that. But even an impact in Central Africa isn't just Central Africa's problem. It can create a tsunami that is global and can be focused in certain locations, as was observed for this Tonga event. And that brings me to my next point. So a lot of our risk assessment just looks at the proximal immediate effects, the blast wave, localized at the point of impact, but some of the risk is associated, you can even consider it like a telehazard around the globe, tsunamis that happen in very different locations. And also, the next point is cascading hazards. What effects can those tsunamis create around the world that may affect people in the future? So it's not just distal in terms of distance, but distal in terms of time. So we have to, to properly do hazards, we have to consider all those. And then finally, and this is part of the point I made to begin with this unexpected land wave generated tsunami, there is an epistemic or a lack of knowledge part of uncertainty that we often fail to consider, and we fail to consider it because it's it's a lack of knowledge, it's unknowns and unknown unknowns. So these are hard things to anticipate, as we discovered in our tsunami workshop. When this happened, we had completely overlooked something. So so there are these events that had been observed in Lake Michigan, and there was one in 1954. So these were thought of as rogue waves, and they weren't really explained until after this 1954 event, where there was a weather front, so a pressure wave moving very slowly across Lake Michigan. And Lake Michigan is shallow, and so it has a very slow wave velocity. But when the velocity of the driving wave, the pressure wave, which is a weather front in Lake Michigan, matches the speed of the wave it's driving, that can create what is effectively a tsunami. And in this case, it reflected off the coast of Michigan, went towards Chicago. There were a bunch of people on a pier. 8 people died in this event. And eventually it was understood these are called meteotsunami because they're generated by weather fronts, but we can generalize the idea of meteotsunami to land wave-driven tsunamis. And here is, this is the coast of Michigan. This is a weather cam that actually caught one of these. Now you see the weather front coming in. There's a lot of wind that's being brought with that, but it's really the pressure, the increase in the pressure that's matching the velocity of the wave in Lake Michigan. So you can get this very damaging tsunami that came ashore. This is very small compared to the global land wave tsunami. It's a much shorter period, much milder effect. These are also common in other shallow bodies of water, in this case, the Mediterranean. So these happen in Spanish islands and also in Croatia. And these are barometric pressure measurements, time resolved, showing that these are very small. Even a very small pressure change, if it's moving at a speed that matches the speed of the wave that it's pushing in the water, can be very damaging. And when they match, that's called a Proudman resonance. So here are a couple of examples. On the right is the Tonga tsunami, and you can see that they're kind of like fingers. And the reason there are fingers is because of bathymetry. So where that Lamb wave, which is actually counterintuitively slightly subsonic, where it matches the tsunami speed in deep water, where there's a trench, you get an amplification, and then once it gets into shallower water, the tsunami slows down, the atmospheric wave passes it, so it overtakes it, and it can go over the continents and hit the next ocean basin and start another one in the next ocean basin. You can see that there's one of those on the right-hand side, one of those high amplitude arms that radiate out hits northern Peru. There were 2 people who were not warned about a pending tsunami that were actually killed by the tsunami that hit northern Peru, and this simulation is consistent with that. Now, my co-author, Vasily Titov, the tsunami modeler, decided to go back and look at Krakatau, the 1883 explosion, and that's on the left here. And you can see that there are very large tsunamis. Some of them you can see hitting South Africa. And one of so this is an example of cascading hazard that we also, was kind of an epistemic surprise, and epistemic in the sense that it's essentially a black swan. So there was a very large ice shelf that was broken, and I think I'm about to get my gong, so I better wrap up and go to our African event. And here is, okay, that is a Central African tsunami. This was from our previous scenario, but the risk corridors happened to cross in Central Africa, so this also applies to the current case, and you actually get one of those rays that hits the Weddell Sea, and where there could be an ice sheet that could be buttressing the West Antarctic ice sheet, and there you get a potential cascading hazard. Thank you.
Thank you, Mark. And we're moving to the last speaker of this session, Rudy Albrecht, multi-parameter monitoring of the potential impact of the exercise asteroid 2024 PDC 25.
Yeah, the lead author on this paper is Christian Köbel, and he is actually in South Africa, but not here. He is in Johannesburg at some high-level meeting where he represents the Austrian government and the Academy of Sciences. So the number 2 author gets to talk. We have given papers at PDCs before, Christian and I, on communications, but communications, as we know, has gotten very messy, and we decided to do something else. And something else that we decided on was, what if we do not succeed in mitigating our favorite asteroid 2024 PDC 25, and it were to impact? There are 2 ways to look at this. One way is it's the largest, or one of the largest natural disasters, and the other way to look at it is it's the largest geological experiment that's ever been done in the history of mankind, and by golly, we were going to observe that. So here is the, by now well-known footprint based on current knowledge. By the time we will be certain that it'll hit, we will know it much better to probably within 100 kilometers. And this thing is going to deposit a huge amount of energy on the surface, which we want to observe and register. So we suggest to populate the impact area with suitable sensors on the ground, definitely, but also 2 layers of drones in the air. So the question is, can we do that? And the answer is pretty much yes, because off-the-shelf technology is available. So on the ground, we suggest 100 by 100 kilometers with probes spaced about 10 kilometers apart. Doesn't really make too much difference. We can scale it depending on what we will know at that point in time. And it's pretty obvious what, here you see an all-sky camera. It's about 50 by 50 by 50 millimeters, fits in the palm of your hand, and it costs $200. So that's a reasonable price. Of course, we need 100 of them, and then even more in the air. So, but still, it's affordable. So on the sensor package, on the ground, we propose an all-sky camera, seismometer, and a geophone, microphone for infrared and ultrasound, a meteorology package to see what the atmosphere does, a radar to measure the impact effects, and obviously a communication package because this all needs to be communicated very quickly because most of the drones will not survive. So here is a possible implementation. In the atmosphere, the drones get launched at a suitable time before impact, take position up, ideally 5.5 kilometers up, that's half the atmospheric pressure. 11 kilometers up, it's a quarter of the atmospheric pressure, according to the IAA model, but we'll take any altitude in 2 layers. The airborne sensor package contains the instrumentation that's listed here. The drone that you see is a drone that's being used to monitor volcanic eruptions. It's not our drone. This is our drone. This drone was, the payload was developed. The drone probably comes from the Ukraine. The payload was developed by Otto Kudelka and Manfred Wittig. And the payload does cyber defense. It registered, analyzes, pinpoints electromagnetic radiation, and in that case, does something about it, or communicates with those people who can do something about this electromagnetic radiation. Some global considerations. We need a large number of drones, probes on the ground and in the air. So obviously things need to be off the shelf, easy to transport, communications ready, and we need to know the position of our probes very precisely. What you see here is a seismometer and a geophone, all very conveniently sized, a few centimeters across, and lightweight. So for the ground-based sensors, we also propose spectrometers. These are nifty devices. What you see here is called a fingertip spectrometer. It's like the tip of your finger, and light enters through an aperture, hits a grating which does the dispersing and the imaging, and the spectrum gets projected onto a CCD array, which is very compact and very nice, and the CCD array can be read out continuously. Again, a radar package, not in a sweep mode like at an airport, but continuous wave. so we can follow the object continuously. What we do is we imprint on the wave on the signal that goes out a pseudo noise signal, and when the signal comes back, we do a correlation, and we know the travel time and we know the distance. Otto says to an accuracy of centimeters, I'll take meters. Again, communications package. Specifications for the airborne sensor, also straightforward. Again, we need a radar, we need a camera, we need a communications package. We need to transmit the data pretty much in real time because many of the drones will not survive. The surviving drones can be looked for because they got the GPS ping and the buffers read out, but we want to use the satellites to continuously receive data. I don't want to go into details because the gong is going to stop me. What we want to do is build a digital model. The digital model that you see here is not ours. It's the model of the eruption of the Cumbre Vieja in La Palma. And it does exactly what we are proposing to do. It's possible to follow the evolution of what's happening in time and in space. In our case, it must be much faster than in their case. Now, there's a bunch of references. If you want to know more details, take a photograph of this QR code and the link. It will take you to the full paper that's available on this website, and it has all the details that I had to skip. Thank you very much.
Okay, so it's time for Q&A. So I would like to invite all the speakers back up on stage, and we will need mics, which are coming. And there is a very Gen Z way of asking questions using the app, but we can also ask questions, from the audience directly. And hopefully we can put those questions on the screen. All right, let's get going. There is a popular question here for Mark. Oh, it's just been passed, so we're going to switch. Mark, still Mark. Based on your analysis, what's your opinion on the partial deflection option?
Well, I guess I would leave that to the decision makers, but I would say that there is, because of this distal risk, you don't make the risk go away if there's a partial deflection. Even if you put it in the middle of the Sahara and evacuate the very sparse population that lives there, there is a risk. The risk doesn't go to zero.
Okay. So you're obviously in favor of pushing it all the way out?
Well, that's not my decision.
Okay.
I'm just saying the risk doesn't go to zero.
Okay.
But everything is a balance.
Okay, there is another question for you. Just making sure, was the simulation that predicted a 10-meter wave height the same code that was validated against Tonga and Karatau? If so, are there any estimates of casualties or other damage on the South America coastline?
Yeah, so I failed to say, and I think this question is regarding the last thing I showed. That was for a much larger impact. That was for the 2023 scenario, which was, if I recall, 10 gigatons, about a factor of 100 bigger. So that I didn't scale that. So that 10-meter wave height was associated with that. For 100 megaton class event, it's more like 10 centimeters. But I would point out that, a 10 centimeter wave doesn't seem like a big wave. but it's a very long period wave, and it's moving very fast, so there's an enormous amount of momentum associated with that, and that's why there was a lot of damage in northern Peru from Tonga. So it wasn't really a direct validation.
Okay. Okay, let's see if we can move down a little bit in the questions. Okay, Jesse. We heard yesterday that disaster managers plan for the worst case scenario. In your presentation, you said that we shouldn't trust the max values of an assumed distribution. So how should we select the worst case for these scenarios?
I love this question because I think there's actually a conversation to be had where when people say the worst case, I think there's often, do they really want us to be absolutely certain that there's zero possibility that there could be something worse? Or are they looking, or would they be comfortable with like knowing that we're giving them the ranges that's going to cover 95% of the cases or 87% of the cases? Because those are answerable questions. But I think that's a conversation that would be really helpful to have with emergency managers and decision makers. Because the worst case I would posit is unknowable, but I think we do have the tools to give you an idea of what's the 90% of the cases, or depending, there's a lot of room in there that I think we can hit, but there's a specific risk posture associated with it.
Mm-hmm. And maybe you don't want to double the worst case mass that should to capture the 0.00001% of the distribution.
Exactly. If you really go to the max case, you're so far out on the tail that it's extremely, it's even more unlikely than Mark's black swans, I would argue.
Okay, still Jesse, since we had a real situation to deal with, how has WIRE4 affected your thinking about use of priors and range of outcomes to report for cases with little information?
So I actually think WIRE4 instilled in me how important it is to be explicit about your priors. Because while we were in the heat of WIRE4 and we were all running calculations, very often there were different numbers running around. And when I tracked them down, it was not that the measurements were different, it's that people were using those measurements and using different prior assumptions and coming up with, like I know you had a different range and sizes than I did because we were using very different priors. And I think using different priors is fine if you are clear on what the purpose is of the stat you are quoting and using that prior for. But I do think we kind of we take our priors for granted sometimes, and WIRE4 kind of reiterated to me how important they are.
And sometimes we're not even explicit when you talk about uncertainty, whether that's a 1 sigma range or a 3 sigma. So that can lead to confusion. Ashley, does your study make the case for additional resources directed toward physical characterization?
Well, I think we showed that physical characterization, understanding that better can, improve our risk assessments, improve our knowledge of what, affected population or damage radius would be. But this study is really a value of information study. So trying to understand the value of different sources of information. And then once we know the value of those, then we can use that to advocate for one type or another of, observations or flybys, et cetera. But not specifically for physical characterization in general. We're really trying to get at what is the most valuable source of information for us in improving our risk knowledge.
Okay, this one is for Mark, but really the whole panel. I think a lot of people in this room are realizing for the first time that there is a non-zero risk even for an impact in the Sahara. I'm sure decision makers are completely unaware. How can we best inform them of these risks?
Well, I would just say, this is the type of thing, this meeting is a way to do that. The reports that we write are ways to do that. So, we do need to make sure that all of this is documented and passed to the right people.
Anybody else would like to comment on that? Okay, if not, let's move to the next one. I'm guilty for that one. Over the years, we've had a number of small impactors, and the question is whether it would make sense to collect measurements for those smaller impactors And if so, how much lead time would you need to set up all, the measurement sensors to collect the needed data?
It would definitely make sense, but it boils down to probably the issue of funding, because we would have to have all the equipment ready to go, people ready to go, and because the lead time would not be very long for small impactors. And we do not know where it's going to happen, so we need to deploy the equipment, airplanes, helicopters, people. It boils down to funding and political decision-making in the end.
And how much time would you need to be ready, in case you had the equipment ready to go? Is that something that you could pull off in 2 days, say?
Depending on the support that we get. If it's in an area of the globe where there's a good infrastructure, say in the United States, where there's a large area, but the same rules are valid for a large area. In Europe, it would be different, because it would be different from country to country to country. And it would require a lot of agreements, intergovernment agreements. So it's really not a technical issue. It's an issue of political decision-making, and funding.
Okay. All right, the next one is for Marco. Is there any intuition or conclusions we can reach from the keyhole map? And I love that people are asking about keyholes. Did it inform the necessary asteroid deflection distance, or does it limit how far you should deflect it?
Okay, I think it's a matter of orders of magnitude, because the keyhole map tells you how far the keyholes are from the Earth. So if you are to deflect the asteroid, you can understand, if you know how long, where you're going to deflect it, you're going to know if you're going to reach a part where keyholes are. And even if you reach that part, I guess you're going to have some uncertainty on the distance you deflect the asteroid. And if that uncertainty is significantly larger than the width of the keyhole, then there's still a low chance that you get the asteroid deflected into another keyhole, because we saw that typically these keyholes are really small, of the order of hundreds of meters.
I'll just follow up with another question on that. Do you think there is a particular deflection technique that is preferred in order to avoid keyholes?
Well, from yesterday's discussion, it seems that this ion beam method is very efficient also in deciding where you want the asteroid to go. So I'm not an expert on that, of course, but that's my impression.
Okay. Yeah. Thank you. Jesse, any insight into how to actually measure porosity remotely rather than relying on priors?
So I think with porosity, you're either relying on a prior or you're inferring it from other measurements. And you can certainly infer it if you have a mass, a volume, and some spectroscopy. And then you can get a pretty good inference of your porosity.
Okay, one for Ashley. Is the takeaway that if you have James Webb Space Telescope, a flyby adds 20% more information?
Okay, I think this was from talking about damage radius. And so this was looking at, I believe, if we had the flyby, then we would understand our damage radius range 20% better relative to our original knowledge than we would have if we skipped the flyby and just waited it out but continued to get some entry updates. But if we didn't have those property updates, we would understand our knowledge of the damage radius would be 20% less relative to what we knew originally.
Okay. It looks like there are 2 questions for Christian, but I don't think any of the speakers is named Christian, so I'm looking for a volunteer.
Pseudo-Christian.
Okay. Let's see. What about accelerometers for shock, arrival, and details? Anybody would like to take that?
Yes, because it pertains to what I've been talking about. Obviously, what I presented was our first guess, first ideas about such a monitoring network. If we were to do that for real, we would spend a lot more thinking, and we would probably seek input from the community and decide on the actual payload and the equipment that we use as probes to monitor this impact. Again, this is just what could be done with off-the-shelf technology within about 2 days of thinking about it.
And it looks like there is another question for you. At this point, you're our resident Christian. Have you considered how to adapt the monitoring system to potential ocean impact site after a partial deflection?
The answer is no, because we were sort of fixed on the current footprint, on the current impact site. But conceivably, especially for the drones, it doesn't make any difference whether they launch from the surface of the water or the surface of the earth. For the ground sensors, it would make a difference. It would require different hardware. It would have to float.
Okay, Ashley and Jesse. Although brightness is a challenge, what are the most valuable ground-based observations, especially when an object does not pass through the James Webb field of regard?
So in rough order of importance, and I reserve the right to change this order, the first thing is if you can get an accurate size measurement. And so even without JBST, someday, very soon, we'll have NAO Surveyor, and they get they are designed to get us sizes. So that is, those are where you start. If it comes close enough to get radar, you get a great size. So we have ways to get size, and we're going to have more ways to get size. If you don't have that, then we can learn a lot from spectroscopy, because that helps you put limits, or it lets you infer more likely albedos, which then gives you a better estimate of the size. And even if all we have is color photometry, that can even be leveraged to reduce the size. So those are kind of, and that order is really based on lessons learned from various IWAN observing exercises. We've been through enough of those. We've kind of seen how all those different pieces of information we can get remotely affect the outcomes. Do you want to add anything?
Okay. Anything to add?
Yeah, I think I totally agree with Jesse that, as we were looking at the value of different information sources, diameter continued to, size continued to come up and really be a dominant factor in all of the calculations we did. So anything that can get us a better estimate of the size early on is really helpful.
Okay. I think we have time for one last question before Gerhard kicks me out. For Mark, you said that the probability of a tsunami isn't 0 for the partial deflection, but what is the probability for PDC 2025? If it is 0 point, lots of zeros, 1, for example, that is important to understand.
I completely agree, and I think that, the whole sort of risk assessment, cost-benefit analysis is difficult and fraught when you have so few validation cases. The Tonga case, 2 people died from the distal tsunami. There were local, nearby deaths, but if we're talking about an impact in the Sahara, those are distant. Those deaths could probably be prevented by better modeling, better warning systems. I mean, this Pacific Tsunami Warning System does not account for this type of a tsunami. So the tsunami arrives at a different time than a tsunami would from a local source, from an earthquake or from the local explosion. So that was part of the problem. So, in terms of cost benefit for an impact as small as the this year's scenario, the resources would probably be better spent with the warning systems and the modeling and seeing where the tsunami would go.
All right, thank you. I would say let's thank our speakers again. And that concludes the session, and I'll hand it over to Gerhard.
Yeah, now we have another panel session, this time on international disaster management for planetary defense. And I would like the panelists and also the moderator or moderators to just come up to the stage here.
Thank you very much. So back to disaster management this morning. I will be co-moderating with our colleague LA who's online. So we will have first some presentation from our, let's say, moderator side, and then we will introduce the panelists, and we go through some questions. Of course, the questions are open for the audience as you know through the app, so we will also look at those at the end. So maybe without any further delay, I pass on the floor to you. LA, just also introduce yourself, and then we go through the slides first, and then we continue from here with the introductions. Thank you.
Thank you. Good morning, everyone. Can you hear me? Thumbs up?
Yes,
Can you guys hear me? Okay, great, great. Sorry I couldn't be there with you this year. I'm in a new status. As some of you may know, I retired from federal service this past December. So now I'm working on becoming the grandfather Uber for a lot of my time, but still want to stay engaged with this community. I think it's very important, and I really appreciate the opportunity to be with you this morning. So I have a few slides that I'd like to go over, and I'd like to just to introduce, just to go over what we're going to talk about. Even though a lot of things we'll discuss today were talked about yesterday, I think there's an important aspect that we should be leaning forward to. So if we can bring up the first slides. Next slide, please. Okay, so what we talked about here, what we're talking about here is disaster preparedness for asteroid impacts. And as my colleagues on the stage will talk about, this is not something that those of us in emergency management and disaster management think about as an everyday occurrence. One of our challenges is that we have things that are going on every day: earthquakes, volcanic eruptions, floods, hurricanes, wildfires. Asteroid impact, I mean, some of us are aware of it. In the United States, there's been a great movement aided by our colleagues at NASA and the Planetary Defense Coordination Office. We've had a series of exercises that talk about it. So, and depending on where you are, and I'm sure we've done some things with our European colleagues, depending on where you are, your disaster managers may or may not be totally familiar with, but from the day-to-day aspects, there's things that are happening every day that keep us very much occupied. Next slide, please. So this slide just gives you an idea of just using the United States as an example, because that's where most of my experience is. We talk about scenarios and what ifs and preparing for the worst things. So, but we also recognize there are also some very large hazards that exist in the U.S. that we need to perhaps take a little bit more time to prepare for. So in this case, Southern California is as vulnerable to a large fault zone. So that would be a very large area of the United States that would be affected all at once. You would have no warning to it. You might have some precursors, but for the most part, you will have no warning. We also have another area on the West Coast, the Cascadia Subduction Zone earthquake. We've had a couple of exercises, multi-state level exercises, where because that area is going to be so large, there's going to be so many people affected, that the only way to really wreck it is take a separate plan and work through all of with state and local regional officials, kind of work through what would be different from a disaster of that size, what we would have to do. And then our colleague Romana talked about the multi-hazard early warning systems. And we want to say that a lot of things are already in place. Some of them have been exercised, some of them have not been, but it's something that we need to pay attention to. And I think that planetary defense is such a unique scenario that we might have to do a little bit more to prepare for it in the future. So that's why there's a question mark on asteroid impact. And just for general knowledge, those of you who participated in the U.S. tabletop exercises sponsored by FEMA and NASA, we finally got the asteroid impact added to the president's list of domestic incidents. You know, space weather has been on there before: hurricanes, earthquakes, large wildfires. But we did get asteroid impact added to the list and identified which agencies are responsible for responding to it. So that's forward progress to us. And we also have a new national policy that Dr. Daniels talked about yesterday that explains what the U.S. strategy for planetary defense going forward is going to be. And we've been successful through multiple administrations, as my disaster colleagues have also mentioned. That would be a challenge, keeping that momentum going. And the world is a lot more complicated than it was even from between now and the last PDC that we had. So there are going to be some changes that affect all of us, including here in the U.S. Next slide, please. So one of the key things we talked about in our last exercise, we invited our international colleagues to join us. And here in the U.S., we've had 5 tabletop exercises. The last one we invited our colleagues from international colleagues to join us. And we also had some state and local participation. And one of the things we want to talk about here, I think it's time for us to shift from, in the previous PDCs, we've always talked about responding to what we would do in a hypothetical exercise. I think that we have some experience with that now, where now we need to shift focus into recognizing that this is a hazard. It's an international hazard. It will affect everyone no matter where the impact occurs. But it's so unique. The science for it is different. We don't need to explain wildfires. We don't need to explain earthquakes or tsunamis. Most people get that. In the United States, if you show one of our Gulf or East Coast citizens a hurricane chart, they understand what the categories mean. They understand that you don't follow the black line. It's all within the curve. So everybody understands that, understands what preparations made. I don't think we were at the same level for planetary defense. I mean, it took me several explanations by Lindley and Kelly and everybody else to explain to me what Monte Carlo points were and stuff. And, you know, that took me a while. So I don't think that's something that we could show that people would get until you get to the last part of information where it's concentrated and, you know, you designate that as the impact point. So one of the things I thought that we should talk about this morning is we have the same page, we have the IWAN. Should we start talking about a same type of organization for international disaster preparedness, an advisory group? So this is a slide I'm sure everybody's seen. In the gap we identified in our exercises, there's no analogy to the IWAN or same page for international emergency preparedness for a NEO disaster. So what we wanted to recommend was identify an appropriate forum. There may be something that already exists, as Romana talked about. Maybe we can already use something, maybe make some modification to it or add something to it that would make a special group that would get together and talk about forming an international disaster management planning group for asteroid impact because of the possibility of the size and scale and the number of our fellow citizens who can be impacted by an asteroid impact. So as you can see down in the bottom there, a disaster preparedness organization, convene. It would be kind of having the same mission as the others. It's an advisory. It has no real authority. It doesn't have its own money. Not even sure where it would be placed. So that's what we want to talk about this morning. Next slide, please. So Action Team 14 was mentioned by Lindley doing this overview of how planetary defense works. And one of the statements was that prepare for neo-impact to consider an impact disaster planning and advisory group should be established to link together existing national and international response agencies and make sure a response to a large event is coordinated. And that would include NGOs. We've done that in the United States. We've invited Red Cross. So we would think in this instance the International Federation of Red Cross and Red Crescent would be a very important part of any kind of disaster response organization that we might want to think of, or advisory group. Next slide. So I would think that a newly chartered IDPAG would have the same mission as outlined by Team 14, review lessons learned from other disasters, research opportunities, understanding long-term effect on humans, weather, environment, infrastructure, and economies. And today's environment, that's even much more complicated with global supply chains, the challenges to those global supply chains, international movement of people. How do you designate people who are moving from one area to another because of impending impact? What if they have to cross national borders? Do you identify the nations that are going to try to respond with mitigation efforts in space? During our California exercise, during the third exercise we did, we invited state representatives from California, and they admitted that this wasn't even on their list of things to think about. And one of the challenges was like, what do you do with insurance claims? Are you going to rebuild the area? Who's going to make the decision if you're going to rebuild it or not rebuild it? One question that was asked is like, hey, I like where I live. Are you going to replace my house if my insurance says, hey, we're canceling it because of natural events, whatever? There are very complicated questions on this, and my idea is that we need to start talking about this now and not later, because even with 13 years, now last exercise with 14 years for our science colleagues, our space science colleagues, 14 years they might have gotten it through, but in the exercise for the disaster guys, when we had that period of uncertainty of what the asteroid was doing, our senior leadership elected to actually wait until they got better information as to where the impact and what the possibilities might be. Because while they were doing that, we were still responding to hurricanes, earthquakes, fires, etc. So we had time, but depending on where it's going to be, how many people it's going to affect, what critical infrastructure in that area is going to have to be moved. Do you have a nuclear power plant that's going to need to be shut down? You have to reroute. Do you have major transportation hubs that's going to be rerouted? How long will it take you? And one of our exercises, the local authorities I talked about, another problem which is exacerbated would be for an asteroid impact. For hurricanes, we were actually used to moving people from assisted living facilities, from hospitals. But those of you who are medical professionals know that there are some conditions, if you move a patient who's in critical care in the hospital, that patient will not survive evacuation. So there are a lot of things that'll go on with that. And then the idea of the IDPAG would also, it's time for us to start thinking about exercises that for the disaster managers specifically, where we would actually go through what we kind of went through in this exercise, where we get the science information, we would monitor what's going on, the progress we're making, but we're not going to be the ones voting on which method you're going to use, et cetera, et cetera. We just want to know enough to be kept informed, so those decisions might affect how we are going to conduct the evacuation or whatever's required. Next slide, please. So this is just an idea of who could possibly do this, what regulations already exist. Next slide, please. I think our colleague Romana talked about this. This is something that maybe that already exists that we can integrate our warning network into. And there are a lot of things. As a former director of the FEMA National Response Coordination Center, we've had a lot of international guests come over, and one of the things is just basic communications of how you get the word out to everybody. And depending on where you live, that's either more complicated or not. Last year, we've had a couple exercises in the U.S. where we pinged everybody's cell phone with an alert message with mixed results, but almost everybody got it. So depending on where you are, that might be something you want to think about, but it's not going to come into effect till we get to the last phases of the years building up to that is important. So what are you going to communicate? Who is a trusted agent for getting the word out, et cetera, et cetera. Next slide. And next slide. So those are I'm gonna leave the questions up, but Laurent, that was basically my introduction to what I think we should be doing next, and I look forward to hearing what our panelists have to say about these ideas.
Thank you very much. Let's leave the questions up. And then maybe we can start with now introducing the panel members. And I also know, I think, Anderson, you have some slides. So maybe we can start with then you going through your slides to get that out of the way, and then we can go into a discussion, right? Good. So again, my name is Laurent Saran. I'm managing the UN SPIDER program within the Office for Outer Space Affairs, and also in charge of the space applications section currently, since some of us do 2-3 jobs in the current financial situation. The one thing I wanted to mention, using my advantage as a moderator, is how happy I was to see that presentation on the tsunami just before our session. And some of you might remember yesterday, those are exactly the points we were making, that these things you cannot be sure, and you can't say it's 15 centimeters or 1 meter only. It's exactly the kind of discussions we have to have. I was twice in Tonga last year. We helped the country, in a way, build resilience after what happened in 22, and we are building a digital twin for the main island Tongatapu, so that in the future you can simulate this kind of tsunami, sea level rise, and all these other things. And I can tell you that although they have a very able disaster management organization, you know, they have remote sensing experts, GIS experts, I was impressed by the team. They had no idea, there was no expectation that something like this can happen, and that eruption led to a 15-meter tsunami wave that hit the island, 15 meter. It's a miracle that only so few died, but that's because of the early warning kind of worked. And as I said, they have a very able organization there. They could evacuate, but there are a lot of other things, economic damage that could not be avoided. So we have to be quite good in how we make these kind of estimations and models and forecasts, I would say, before we can be more sure. Going to the panel, and I just go from my right here, so starting with Clement. Please, 30 seconds to introduce yourselves. Just say what you're doing, please, and then we'll take it from there.
Thank you, moderator. My name is Clement Kalonga, and I work for the UN OCHA. I'm a regional focal person for Africa for the emergency response section, which deals with UNDAC, a global response mechanism, INSARAG, which is a global coordination of search and rescue teams, and lastly, and not least, the Joint Environmental Unit, which deals with environmental emergencies. Thank you.
Thank you so much. My name is Anderson Banda. I'm director for the SADC Humanitarian and Emergency Operations Center. As you may be aware, SADC is a Southern African Development Community. So the SADC Humanitarian and Emergency Operations Center is based in Nacala, Mozambique. This is an institution of SADC which is just being operationalized. I think we are just going into the second year in terms of when we reported, and the objective of the shock is to ensure that there's a coordinated approach to preparedness and response and recovery in the SADC region, which consists of 16 member states in relation to disasters and humanitarian situations. Thank you.
Yeah, thank you. My name is Jörg Schasinski. I'm wearing two hats. On the one side, I'm professor with the United Nations University Institute for Environment and Human Security. I'm based in Bonn, in Germany, and my research and education focuses on geospatial applications for disaster management and emergency response, early warning systems, and humanitarian relief. And the second hat is that being an active UNDAC member under the OCHA mechanism that Clement has just described. Thank you.
Thank you. Good morning, everyone. My name is James Wanjohi-Nyaga. I work for the Regional Center of Mapping of Resources for Development, RCMRD, which has member states, 20 member states across East and Southern Africa. I am a project manager there. I have implemented several disaster risk reduction projects under funding from UN Office for Disaster Risk Reduction. And just a highlight of one of the projects that we implemented in Malawi under funding from UNDP on the establishment of a community-based flood early warning system that was actually a highlight at the COP and several other conferences. Thank you.
Thank you, Mr. Moderator, and everyone. My name is Johan Mini. I work for the City of Cape Town, adjoining this municipality. I'm the head of the Disaster Management Center. We're about 80 people looking after the 4 million people of the City of Cape Town. And we are looking at 30 plus identified hazards that we need to be prepared for. And we have a responsibility regarding risk reduction as well as response. On the risk reduction side, we work with expertise, the people who understand the different hazards and who can advise and who have the budgets, for example, for flooding, the people who build dams, the engineers are part of the risk reduction effort. And on the response side, we try to follow an all-hazard approach where the same resources can respond to multiple different hazards because the impacts can be similar between the different hazards. Thank you.
And now our last panelist who's online from Nigeria. He couldn't get here, he didn't get his visa in time, so Ademuyiwa, over to you.
Thank you, Lauren. Good morning, everybody from Nigeria, Abuja precisely. My name is Ademuyiwa Oyewumi. I work with the pioneer African Space Agency called the National Space Research and Development Agency here in Nigeria, where I work as an assistant director, and I also head the Hazard and Disaster Management Division within the Strategic Space Applications Department of the agency. I also double as the Regional Support Office Coordinator for UN SPIDER, and within this role, I've been able to, work on different projects, including being a project manager for different activations within the International Charter, Space and Major Disasters for floods in Ghana and Nigeria. And we've also been able to add value to other disasters within Africa, in other countries. I'm happy to be here, and I look forward to, contributing to this panel. Thank you.
Thank you very much. I like it that you're sitting on a chair in Abuja, just like us here. So very nice setup. I think we can start with the slides then from Anderson. If you could please help us bring up the slides, then we will bring the questions back on the screen. There are some slides from SADC, right?
Yeah. So maybe as we await for the slides to come, the few slides which I've actually prepared You can go to the next slide. That is the shock building in Mozambique, in Nacala. And then we are looking at the assumption here that all the other efforts might have failed. And we are looking at a situation where now we have to prepare and respond to this near-Earth object impact. And in the region, the preparedness response activities to this situation will be coordinated by the SADC Humanitarian and Emergency Operations Center. So we can go to the next slide. These are the scenarios which we have been talking about. We have a situation where the information has circulated, and then we are now in those situations like we did yesterday and today. What happens? We have a situation that if the shock is to coordinate this situation, then we, as a shock, depending on what we are getting from the scientists, depending on what we are getting from specialized institutions at a global level and continental level, we'll be able now to issue an impact-based preparedness and response advisory to the member states. And these are the member states which might be affected according to the predictions which we are having. We can go to the next slide. We're talking about the questions which were given to us. So what are the factors which we want to assess at the shock? So we are looking at political, social, and economic factors, especially in the state parties, the countries which are likely to be affected. So there's need to come up with a mechanism for international and national response organizations so that we are able to work together. For us in the shock, the space missions and the other issues, definitely these will be determined by the technical people and the appropriate institutions. In terms of trusted voices, and I think we discussed this yesterday, when we are talking about especially public awareness, I think this is one of the most important issues which we have to look at. The trusted voices for communities in those countries, these have to be determined and identified by the national disaster management authorities, and the national disaster management authorities in the identified or the state parties to be affected know how these situations is configured. We can go to the next slide. So we continue with the possible questions. There will be need to review regional preparedness and response plans, depending on other events which we have experienced in the region. You may be aware that the region has been experiencing a number of other disaster events, and based on that, tsunamis, cyclones, and so on and so forth, our asteroid regional and preparedness response plan will be reviewed. Again, there's need for us to ensure that the information which is being communicated is actually timely, is clear, and to ensure that the communities get that information. The shock to continue coordinating preparedness and response to normal disasters. So even as we are preparing, because as you may be aware, this preparation might take a number of years as we go towards the impact, but the shock will also be taking care of the other disasters which will be happening in the region, floods, cyclones, and so on and so forth. But finally, what we are saying that in this whole scenario, as decisions are being made, it's important to make no regret decisions, yeah, with the current information which we are given. It is important that we convince our leaders, political leaders, traditional leaders, and other leaders in the region on the importance of the situation which is at hand. Next slide. So basically, these are the few slides which we're talking about in terms of how the SADC Humanitarian and Emergency Operations Center may and will be able to coordinate that arrangement. Thank you so much.
Thank you, thank you. And now we have the questions, the lead questions in a way back on the screen. And we should take maybe the next 20 minutes or so to have a discussion on those points or maybe others. Then let's see what questions the audience might have for us. I would say raise your hand if you want to take any of the questions I'm going to ask and answer. I start with the first one. Based on what you have heard in these last 2 days, both from the expert scientist side and also from our side, as on those hypothetical scenario panel discussions yesterday, do you think that based on all these previous large-scale disasters that we have witnessed and worked with, because we did see a lot of those happen as on the first slide from LA, do you think we are prepared as international organizations for a near-Earth object impact? And maybe I start with you from the regional humanitarian coordination side, but then anyone else who wants to tune in, please do.
Thank you. And I think to build on what my brothers just talked about, and in the presentation prior to Anderson's intervention, I think how do we gauge our readiness as international actors? And if we are learning from any kind of past and current response mechanisms, I would say that maybe the first dimension to this question is around whether we have adequate institutional coordination mechanisms that could then be used to enhance the preparedness or to gauge whether the preparedness is there. I would say yes. I would say that we would not necessarily need to create a new coordination arrangement. I think the first presenter talked about the current early warning for all mechanism, which actually adopts a multi-hazard approach to understanding hazards and how they'll be impacting us. So I would think that what is missing in the current humanitarian coordination or risk reduction coordination mechanisms is really integrating the aspect of the near-Earth object dimensions. When these, if you look at tsunamis that have happened or earthquakes like the recent one that we just had in Myanmar or the most significant one in the recent years that we had in Turkey, you realize that the parameters and dimensions of how preparedness mechanisms will work, or even including response, if it gets to that point, will not be different. You know, humanitarian coordination architecture is there through OCHA at the global level, and you have the interagency standing committee that has all the humanitarian actors in there working on how they can work together to mobilize resources for preparedness and response. And of course, in the early warning, you have WMO, which is, of course, limited to hydromet indicators. But those existing platforms could easily integrate with the information that our colleagues from the space community can provide to then update the levels of multi-hazard warning mechanisms at the global scale and cascading down to the African Union level, where there's also existing DRR and humanitarian coordination structures. And then we get to the level of SADC, where the shock then picks it up. I'm so insistent about not creating new coordination mechanisms. One, because that will create a lot of duplication of efforts. And two, the current dimensions in terms of financial flows to entities like the UN has become precarious. You know, we don't know whether there'll be continued funding for some of the agencies. There might be bundling in of agencies and mandates being re-questioned and being redefined. So it makes a lot of great sense to appeal that the existing coordination mechanisms do adjust and integrate. So to answer the question, I don't think, because most of these have not thought about the near-Earth object impact. And I think this current discussion is great. It's bringing together the two communities to start this discussion. And with the furtherance of science and observations in the next few years,
we could have input into the multi-hazard early warning systems, try to embrace scenarios of a nearest object impact and start, to trigger the preparedness activities at the global scale, cascading down to the continent. Thank you.
Yeah, maybe I can add some scientific perspectives to what Clement has reflected already from the operational perspective. I would look at this question, especially at the part, are you adequately prepared for near-Earth object impact? I would be critical here. What I can say is there has been extensive research, and there is also a very solid body of research documented in academia around the world on the recent leading disasters that we have experienced. Look at the tsunami, Indian Ocean tsunami from 2004. There has been a lot of research done into the cause and the root factors of that and the impact on land. That was the base to design early warning systems. And these early warning systems, I was part of them to a certain degree, and we have seen that you never have enough information. Yeah, so when we did the topography of the coastal line, that was one thing, but then we figured out great errors when the waves were coming in. And we found that the bathymetry of the shelf area is also a very, very critical aspect. And this is, I would love to have a discussion with Mark on his tsunami presentation, if the modeling that you are using is also including the bathymetry of the shelf. And I was looking at his examples, but we have also seen the earthquake, the strong earthquake in Alaska, right, in '64, in the Prince William Sound. And there we have seen most of the fatalities caused by tsunami waves going more than 60 meters, 67 meters in height. Yeah, and that was a mass allocation into the ocean plus the earthquake. So modeling tsunami wave height is really a very, very tricky thing. But there is, of course, again, a lot of research out there. I want to mention what our colleagues in Japan are doing after the Great Eastern Japan earthquake in 2011, plus tsunami. There was the establishment of the Irides Center attached to Tohoku University. And to me, this is one of the world-leading institutions when it comes to tsunami modeling. So that's definitely also a resource for that community here. And with that, I would say we learned a lot from the disaster management community, also supported by scientists from all over the world. But the missing part is still how can we integrate that part on asteroids. And I fully agree with Clement. It would be not necessary to reinvent a new coordination mechanism. It's all there. And this is going around the world. And there are so many coordination structures that have developed over the last 3 decades. So nothing is new. So we can build on that, but the missing step is a stronger integration of this community into the disaster management community. Thank you.
Maybe you have something to add? Please go.
Yeah. Yeah, I just also want to echo what has been said, and just to emphasize on the time component. I think most of the coordination frameworks that we have either consider the floods, which is a very fast hazard, and also drought aspect, which is also a slow onset. But now here is a very, very slow, kind of issue, and I think that has not been considered, especially when we're talking about governance and the way governance, especially in Africa, looks at some of these things. So I think as part of what we need to integrate for the purposes of this scenario, the time component will be quite an important issue. Thank you.
And maybe just to jump on another point that you, Jörg, made, the data availability, and we mentioned all these mega disasters, Turkey and 2004 tsunami, and Haiti 2010, and a lot of other such major disasters. We always think we learn from the past, but every time there's such a major disaster, to be honest, it's a scramble for data, it's chaos, it's lack of coordination, duplication, it's happening all over again. So in terms of that data, access to data, availability of data, I'm just wondering, maybe starting from the local level, going to Cape Town, I mean, do we have enough geospatial, statistical, demographic data in our hands currently to make good decisions when something like such a threat would come our way. I mean, in the case of a potential impact, we do have some time to prepare and maybe even develop some of that data, maybe sometime. But are we comfortable? Is there anything else needed? As I mentioned in Tonga last year, we realized we need to do a digital twin of that island. There's no other way on such a small island we can work with, you know, free data sets and this and that. So what do you think in terms of that availability of data, and is something missing, something that you can work on?
No, so I would also reflect on the adequacy that I don't think disaster response can really ever be adequate. It can be the best we can do, but I don't think adequacy. And just to translate disaster management in South Africa is called emergency management in America, or civil protection in much of Europe. So that's the kind of people that we are talking about. And they rely on, it starts with a map. You want a map of the impact. You want to make a outside border. This is my area of impact. And then you want to look at what is impacted. And it's very much information related. And there's, for example, Tim Titus is in the audience. He put a paper on about flooding, how flooding from USGS, from how flooding can be affected down in terms of time after such an impact. And that's a kind of understanding the risk, understanding the potential impacts that will be important. And I think in the 14 years that you have before this impact, you will need to capture and analyze and think of the downstream, distal, temporal impacts and quantify them and then try to work on them. And I think over 14 years, an issue like this is maybe less emergency management than just development management. You need to develop around the risk, like you develop around a river or how you develop around a sea. So, yeah, that's my point.
Of course, we are not discussing the hypothetical scenario from yesterday anymore, so it could be in 2 years. So, anybody else? Yes, please.
Yeah, I think Africa in general is a data sparse region. From a regional organization like us, I think one of the things that we have found is the different countries are at different space in terms of data collection and also making that data accessible. We have found many a times that data could be available, but is either sitting in someone's desk or it is in paper format. So we really need to either collect that, curate it, and maybe make it digital. And also, most of the nationalities do census. So they actually collect some of the vulnerability information that would be quite useful in understanding how maybe such a scenario would impact different kind of population. So, but unfortunately, that data accessibility is also an issue. So there's a lot of reliance to global data like the DHS data, possibly even the HDX from the humanitarian side really provide this data. And also I should add that if you looking at GIS layers, most of these boundaries change quite a lot. So having that updated databases is also quite an issue. But generally, there are baseline data that we could reference, but really require updating, really require curating, standardizing, and also making them available, for use by everybody. Thank you.
Anybody else? Jörg?
Can I say what?
Okay, let's give Ademuyiwa the floor first. He's been silently waiting there, and then Jörg. Go ahead, Adem.
Yes, thank you once again. Yeah. Talking about data, I'm going to delve a little bit from what everybody's been talking about. Yeah, in Africa, we have that data inadequacy. Yeah, we know. But to think beyond that, even with the little data we have, and complemented by global data that we usually use, to kind of come up with our models and all that, when we turn this data into like risk information, I am a bit worried about the fact that this information may be there, but then how do we communicate this information to our locals, the vulnerables? I think this has always been a bane for Africa. So, Nigeria, for example, different action agencies. The Space Agency produces maps. We have the Meteorological Agency produces seasonal predictions, and we have the Hydrological Agency, which gives flood outlooks. These things are there. They kind of, publish them from time to time, but then do the people that are really, concerned that are going to be impacted, do they get to understand this information? I think beyond just having this data, having them turned into information, I think there is the need for that communication, risk communication, to be looked into. How do we convert these scientific jargons, these maps showing categorized risk and all that? How do you translate them into local Hausa language, Swahili, or whichever dialect, that you are aiming to, safeguard? So for me, beyond having data, please, as we move on, let's also consider the aspect of risk communication, perception, risk perception. This goes a long way. If you go to Africa and you probably, not even just Africa, if you put up a list of risk, if you say people are, how sure are you to die of malaria first, or flood, or hurricane, or HIV, you will be shocked that a lot of people have different rankings of these risk. This is due to what? But their perception, media, different things, culture. So for these, I think we should also look inward and also see how we can also put these at the front burners when we're talking about risk. Thank you.
Yeah, okay. Very quickly, and back to the tsunami early warning system, because that also answers a little bit the last question already, and it's directly addressing the community here. One of the core elements of that system was an overlay between all the redundant monitoring data that were coming in from satellites, from GPS measurements, from pressure gauges at the ocean floor, from floating buoys and so on. And this data was overlaid with back archive data from previous events. So the question is, if we would think about how to design an early warning system that integrates the impact of asteroids on Earth, the question is, can you deliver? We heard a lot about the monitoring data that you have, but are there enough archive data on potential impacts or impacts that have happened so that you can learn from the past to project into the future? That could be a very vital instrument for, or idea, how to design such an early warning system. Thanks.
I wanted to add the aspect to do whether, with our normal work in emergency and disaster response, would we have time to also prepare and respond to the projected asteroid impact? And just to clarify that, I think work in disaster management and emergencies is really always simultaneously responding to various hazards. And I think you do not stop anticipating other hazards impact because you are busy with responding to one. And so we're always in a state where we have multiple emergencies happening. We're dealing with issues of conflict, floods, outbreaks, and cyclones. And sometimes when you look at the regions, like for example, SADC, you'll face multiple hazards affecting countries at the same time. So it would be great for the disaster management community to embrace preparedness for any possible asteroid impact while continuing with the work that we're doing. My other point is about also when you're looking at preparedness, there's an opportunity to do simulation exercises, which I'm borrowing from the space community that is already happening, but really looking at, for example, options for diverting and all those kind of things. We need within the disaster management community to also look at simulation exercises in terms of the possible impact, which areas and what would it mean, and I think that's very important. The hazard early warning issue that we have talked about, which is already there, the early warning for all. Once it integrates this, I think what I've seen also is a big gap, is that when early warning is provided, there is less and less of the early action, which is conceptualized, but practically, I haven't seen a lot of what constitutes early action. And so we have, most of the times, capability to perceive and to anticipate that this is going to happen. But that is not often followed with actions. And this is where now the engagement with leadership would be very important. And I think leadership at this point, you're looking at global, through the UN General Assembly, for example, the African Union and SADC. I think to put out a message there in terms of what sort of action is required to really help communities and countries prepare for this. So I just wanted to emphasize that I think good early warning is not adequate until there's corresponding early action that really speaks to how do we then get ourselves into action to start preparing for this.
Yes, thank you, Roland. I just wanted to add that in terms of information and our experiences from the previous large-scale disasters which affected the continent, the world, and particularly this region, it's important that there is a lot of information out there which has been collected. A lot of vulnerability assessments have been done, a lot of risk profiling has been done, but in this case, it's important that we are able to have mechanisms for analyzing that data so that the data is able to make sense from data to information, not only information, but also it becomes knowledge which is actually being shared among its communities, institutions, and authorities. So that this information, this knowledge which is coming from the data can now be used for emergency preparedness in relation to what we are talking about, but also in relation to other disasters. So that we are able to talk about, for example, evacuation plans. If we are talking about this scenario which we are talking about, how do we do the evacuations? But also we need to talk about what will be the cascading disasters which will come out of this event. So it's important, and this all depends on the data which we have. So I just wanted to add that. Thank you.
Thank you. And then let's take maybe one last point from the list of questions before maybe we go to questions from the audience. In the introductory presentation, you heard about a proposed new mechanism that would be kind of coordinating disaster management related aspects of a response to a near-Earth object impact. I heard many of you said we don't necessarily need new mechanisms, we have enough. But I like the idea maybe of, as it was framed, as an advisory group that sits under an existing mechanism, under the United Nations maybe. So I'll ask each of you in 10, 15 seconds to express your view on that. Is that something useful and how you see it going forward, starting with you.
Right, so in disaster management in South Africa at municipal level, we have what we call a disaster management advisory forum, which is where all stakeholders in the municipality talk about the different hazards that confront us and how we can manage them. And that can then go into hazard-specific working groups. I don't think there's any harm in establishing a working group that really focuses on this hazard internationally and really unpacks it and gets us all the detail that we need. At the same time, the existing structures must be strengthened to be able to respond effectively. And one important point I want to make is that disaster management is bigger than disaster management. The effort of managing the disaster, reducing the risk and responding is much bigger than those few people that has disaster management on their clothing. Thanks.
That's correct. We talk about the full disaster management cycle, as we call it, not only emergency response and all that. James.
Yeah, I would like to echo what he has said. I think already the platforms for disaster risk reduction discussions are already there. We just need to anchor it maybe from a continental level. At the AUC, I think yesterday Director from SANSA made this recommendation. We have now an Africa space technology, I think, a framework that we can also leverage. So adding an advisory group where now this now cascades to the regional level, to the national level, I think would be good.
Jörg?
Yeah, I think from our perspective, it's a pretty simple thing because it is an update of the hazard profile that we have, integrating the asteroid. And no community in the world can replicate the knowledge that you already have. And why would you? Yeah. So it's just to define an appropriate integration of new knowledge and your monitoring networks and all your capacities and capabilities into the existing coordination mechanisms, because they cannot be replicated, and you would see a lot of resistance on government sides that this would happen. But it's all there. So just integrating what you already have, I think, is the adequate step. Thank you.
Andy?
Yeah, so the issue of the advisory group or the special group is actually supported. This is because we are talking about this group being a composition of different experts in this area, but that does not eliminate the existing coordination mechanism, meaning that the advisory group is the one which has got that information and being able to feed into the existing decision-making mechanism so that the decisions which are made are actually evidence-based. You have informed decisions because you are working based on what the specialized advisory group is giving you. So this comes into the contingency planning as you are going towards the response. Thank you.
Thank you. Clement?
I agree with those that are proposing that an expert or advisory arrangement is great, and not necessarily to replace the current coordination mechanisms, but to inform. Because I don't think within the current humanitarian or risk reduction coordination arrangements, there have been thoughts of, sort of integrating near Earth object risks and all that. So the expert team would just provide that sort of advisory information to existing structures. And that integration would then allow what is existing to really work on this, as I think Prof. York has talked about, updating the profiling of our current understanding of hazards to add this dimension. And that
Thank you.
Yeah, thanks.
Can we ask our colleagues to transition to the questions from the audience, if we have any? And then, Ade, from your side.
Thank you.
Anything you want to add?
Yeah,
Go ahead.
Yeah, so I'm in support of this initiative that is so African. Because as we can see, African countries have a critical stake in planetary defense. We've seen that large parts of the continent are under-monitored. I observed that in some of the presentations earlier. So having a regional group, advisory group, I think that is very apt. And with that, African region can benefit, from these, by, having its interests and vulnerabilities, and that I made sure they're adequately, addressed when talking about this discourse. So for me, it's not out of place to have these regional initiatives good. Thank you.
Thanks. Well, I think, LA, you see, we have quite a representative panel here from local to global, so I think it's it's a collective agreement to what you're proposing in terms of an advisory group. So I think we should look at that. And I think from our side as UNUSA, we are happy to facilitate if that's required. We still have about 3 minutes. I don't see any questions for us. Thank you. 5.
So Laurent,
Yes.
there were a few questions on our agenda that I thought were interesting. So if we can find a way afterwards to share it with our disaster colleagues on the stage. There are a lot of interesting questions. One that I was interested in was, what do they consider a no regret decision? And then on our questions we have up front, just one of the things that we were interested in, especially since we've done exercises here, was for 2024 YR4, how many of my other fellow disaster colleagues actually heard about it or got any inquiries from your government or your emergency agencies on whether this was something important that they should be prepared for or not? I got a phone call and I was retired, so it'd just be interested to see if you heard about it, did you know about it, and what was missing? Was it a big, okay, no big deal, or should we worry about it, or like in one of our exercises, do we have to worry about this right now, or do we have time? So I was just curious as if my other colleagues got any interest from their governments or besides what was in the media, particularly on 2024.
Anyone? 2024? Any inquiries? Any concerns expressed? No? So the answer is no so far. Well, we didn't know exactly where would that impact, if ever, right? So probably it was, it didn't get to that level of concern. I think we were concerned on a planetary scale. Oh, there's a 1%, 2%, 3% chance. Then we started wondering where, how, myself included. But then came the news, nah, it's actually not. So I think it was too fast downgrading, right? Yes, Jörg.
I think the special case is the very long lead time. That makes this case exceptional for us, because if the hazard would take place, it would be very rapid and strong and everything. But the lead time is so long. And there were 2 remarkable questions in the original set. The one asking, could you prepare next to the other things? That is the wrong question, because we have to. We simply have to, because there's ongoing hurricanes and floods and earthquakes all over the world, so we have to integrate that. And the second question was, could there be a no response to such a situation by officials? And I would argue yes, because there are more pressing issues. Here in Southern Africa, there is not the question of when or if the next hurricane comes, or cyclone in that case, it's the question when.
Thanks. The chair gave us 2 extra minutes, so the gong is on, but we have 2 more minutes. Anything else anybody wants to add, please?
I just want to give an example of a no-regret decision. So if you know that the impact is going to be a radius of 50 kilometers where all infrastructure will be destroyed, if you take your water infrastructure and you build it around this possible impact area to provide water in the future, even if the impact doesn't happen anymore, and it is useful in the future, even if impact doesn't happen, that is a no-regret decision.
Thank you. Yeah. And to me, honestly, as I mentioned also yesterday in the panel, we work with numbers, we work with population estimates that are 5-10 years outdated. So that's what you see on those screens. I mean, we have a lot more investment to do in collecting the good data we need. And I mean also real census data with all the details on every household, on every building, because that's what you will have to look at when you start discussing evacuation. Those are the concrete points, not estimates and statistics derived from 10-year-old or 20-year-old census data, or in the case of Congo, from 50-year-old census data. So any other questions? I don't see any on the screen. We have still 1 minute. Any closing remarks from anybody? The questions from the audience are still on the last session, so I guess there's no questions for us.
I wanted just to talk about the dilemma you get when you're trying to implement a risk reduction. I think the experience we've had in Africa is that much of what would be risk reduction, and I think Johan talked about, is pretty much development as well. So capability for any community that is expected to be impacted by this in terms of how much preparedness they would do really depends on the financial capacity that they have. Whether an evacuation can be executed by a country to move over 1 million people from one place to another is really an issue of financial capacity. And I think that has to be considered significantly because depending on where it happens, there might not be adequate capacity for some of the preparedness interventions just because of poverty and lack of resources. Thank you.
Thank you. Now our time is really up. Thank you very much for all, especially for LA waking up early in the US. Thank you and for joining us. And I think if there's any other questions, you can email us, reach us. We are still here these next days. Thank you for your time. I hope this was useful. And over to the chair. Thank you.
Thank you.
Yeah, so I finished this morning with this very interesting discussion on disaster management. It's now time for the lunch break. We are a little bit behind schedule time, so I suggest we reconvene at 13 hours 35. That is 5 minutes later than indicated in the program. That should be absolutely fine. And there are another short announcement. There is a shuttle service available, which you can see here. So for example, for accompanying persons, or if you decide I have to get out of it for some time. So it's available, and I think it has hardly been used, so you can book it with Zelda in the organizer's office. And again, this is in principle available for us all the time. And there is, I believe, a second notification. I was told if we can display it, otherwise we can do it there. If you need a certificate of attendance, you might have noticed, I mean, when you signed up, you got a confirmation for payment. But if you need a specific one, it can be produced on request. Then please email Fabrice at the IAA that you need such a certification of your attendance, so for the conference fee or for whatever. Okay, then let's take a break now. Thank you.
Yeah, okay.
So it's time to start the afternoon session. Welcome back after the lunch break. And this session is on ongoing and upcoming space missions. And I hand over to the chair of this session, Gerb. Please, it's all yours.
Thank you very much. Thank you to our speakers and my co-chairs, Dr. Richard Moisel and Dr. Ryan Park in the guise of Dr. Farnokia. So our first talk is going to be given by Michael Kuipers, and he's going to talk about the ESA Hera mission to asteroid Didymos and give us an update on its progress. The speakers have 15 minutes, and they will be gonged, I'm told, on time. So thank you, Michael.
Thanks, good afternoon. I hope I get through it. I'm a little bit out of voice. Perfect. Yes, so I'm pretty much starting where the movie on Sunday, who are already there, ended. So it's essentially what happened so far in flight with the Hera mission. So as this is the first talk of the session, I give a little bit the general background. So DART successfully impacted Dimorphos, the moon of Didymos, in September 2022. The Lichia CubeSat took some images of the ejector, flying past the asteroid a couple of minutes later. The period change was determined by ground-based telescopes, and now in October last year we launched the Hera mission, essentially to look what happened during the impact and to generally characterize Didymos and Dimorphos. So this is the mission profile. The mission was launched 7th of October last year, flew by Mars in March this year, and will arrive at Didymos in fall 2026. Generally, the operation scheme at the asteroid is largely borrowed from Rosetta. So first, from a safe distance of 20-30 kilometers, there will be a general characterization of the target asteroids. Then we will have released the two CubeSats, Juventas and Milani, and have a more detailed overall characterization of the asteroid with arcs at distances of more like 10 kilometers. And then the spacecraft are getting closer and closer with increasingly close flybys until the Hera flyby reaches foreseen of less than a kilometer from Dimorphos. And the foreseen end of mission is to land all three spacecraft on the different asteroids with the details still to be determined. So this is the start of the actual operational mission. Hera launched on the 7th of October last year from Cape Canaveral in Florida. And actually the launch was, in a sense, very lucky. It was essentially between two hurricanes. And the evening before launch, the likelihood of launch was 15%. And we were really lucky to catch like half an hour between the clouds and the thunderstorms. What I personally find still more impressive due to the onboard cameras on the rocket is the release of the spacecraft. So this is not a simulation, this is the actual release of the Hera spacecraft from the Falcon 9 rocket. So afterwards, the spacecraft and the instruments were commissioned, and the first calibration slots happened, and it's all green. We were really happy. Everything worked very well. So the spacecraft, the switch on of the spacecraft system, the characterization, also the first Delta D door was exercised during this period. And the mainstream remote sensing instruments, the black and white asteroid framing cameras, the hypercount spectral imager in the visible near infrared between 650 and 950 nanometers, and the thermal infrared imager, which is a filtered imager in the 10 micron region provided by JAXA. They were all commissioned successfully, including some images of Earth and Mars, where I show a few examples. The autonomous attitude guidance was tested with the Earth and the Moon, and then later also with Mars, which will allow the spacecraft in the later phases at the asteroid to operate fully autonomously. The first maneuver was executed, and also the CubeSats were successfully commissioned, as far as to the extent it is possible within their deployers. Those are a few images of the asteroid framing cameras of the Earth and the Moon. On the left-hand side, the first image taken from a distance of roughly 1.6 million kilometers, and on the right-hand side, a small movie. The resolution was around 150 kilometers per pixel from that distance. Here, one can see another small movies in the 25 wavelength ranges of the Hyperscout imager. So this works with a mosaic filter, which means that on the detector there are 5x5 mosaics, 5x5 pixel mosaics with 25 different filters, which gives the spectral range that we can see here with the filter bandwidth of 20-25 nanometers. And finally, here one can see it's a thermal infrared imager that we can see as well the night side of the Earth in the image, and it's a movie taken out, taken from the different images taken in post-launch commissioning, which essentially sees the Moon moving around the Earth while the spacecraft is receding from Earth. Next was a Mars flyby just a month and a half ago. So this is a geometry. And actually, because it happens that the Mars flyby was tuned so that Hera could be close to Deimos during the Mars flight. Essentially, the closest approach was delayed by several hours to make sure that Deimos is really here crossing the path, close to the path of Hera when Hera passes here. That allowed us to have a closest approach of Deimos of roughly 300 kilometers. Also, it was not anymore in the fields of view, so images were taken down to around 900 kilometers from Deimos. And this is interesting because Hera saw essentially the side facing opposite Mars, which is not very well studied because of course, most Mars orbiting spacecraft are inside Deimos orbits. There are some data from the Emirates mission and some old Viking data, but generally the far side of Deimos is not very much studied. Closest close to Mars was around 9,000 kilometers from the center. This is the Mars flyby seen with the asteroid framing cameras. Those are the actual images, but they are artificially colored, so you see Mars like you used to be seen. The cameras do not have any color information by themselves. So this is the approach phase. Here a feature tracking test was done, and this feature tracking was here really only the features were followed by the software, but this feature tracking will be used at the Demos to really for the spacecraft to maintain its attitude, and in the last experimental phase, also to correct its trajectory autonomously. Getting closer to Mars, and then the Deimos encounter, roughly 40 minutes before closest approach. And actually the closest images that we will see of Deimos in a few seconds are taken with Deimos in front of Mars, which was the easiest way to implement this flyby, with the Deimos imaging plus enough Mars images for calibration of the instruments. So this here we can see now the images taken closest to Deimos in front, passing in front of Mars. Those are the last images at around 900 kilometers. Closest approach is somewhere now at about 300 kilometers from Deimos. We are now moving to Mars closest approach, which is the only opportunity for Hera to actually calibrate the images with the objects that fill the field of view of the instruments. And after closest approach from Mars, we finally had some glimpse of Phobos. In the last image, one could see some light from Phobos in eclipse, which we think is because of light scattered in the atmosphere from Mars, and then we had some more Phobos images relatively far from relatively far distance. Now this is Mars as you are not used to see it. This is Mars with a hyperscout H. And actually in this wavelength, Mars is blue, which is mostly because of the solar spectrum, but not only. Also the Mars spectrum itself becomes slightly bluish in this wavelength range. And here again, Deimos in front of Mars. And finally, Mars was of course also observed with the thermal infrared imager. Again, the image with Mars and Deimos. And here this is not calibrated, it's not yet calibrated to actual temperature, but here the brightness is proportional to temperature, and one can see that Deimos, that doesn't have an atmosphere, is brightest on the day side, and that the Martian temperature, as expected, decreases from the center to the poles. So the calibration of all those data is still ongoing, but we expect to have first scientific results, particularly from Deimos, in a couple of weeks or months from now. So further activities until arrival at Didymos. Yeah, one thing we still have to do is the commissioning of the laser altimeter, and the reason is simply that we still need a software update to command the laser altimeter. This is something that simply wasn't ready at the time of launch. And now in the summer or up to September, there will be an onboard software update which allows also to operate the laser altimeter as a last instrument. Otherwise, it's now for the remaining of the cruise phase just regular checkouts. And then arrival at Didymos is October, November 2026. And the early characterization phase is the first detailed observations of Didymos start in December. So there's not that much going on, in other words, in the remainder of the cruise phase. So we foresee to use this time to focus on the asteroid phase preparation. Thank you very much.
Our next speaker is Alain Henrique, and he's going to be talking about the radar experiment for Hera.
Thank you. Yeah, I'm going to speak about the radar on board Hera, and also propose for the two Apophis missions. In fact, if I consider Apophis as a relevant example for this room, what that we know about the internal structure, what we assume about the internal structure, In fact, we assume Apophis is an aggregate. We have no evidence of that, covered by a regolith. It could be a binary, a contact binary asteroid when we see the latest shape model. And also, from modelers, we don't expect a global reconfiguration during Earth encounter. But we have a lot of missing information. First, we have no direct evidence of the aggregate structure. And we have no constraints on the physical properties, especially about the cohesive strength inside the body, about the density, the composition, etc. And we have no knowledge of the heterogeneity inside the body. If we have different subaggregates, what is the difference in terms of porosity, composition of the different subaggregates, if we have some structure, large voids, etc., or layering. And more generally, we have no information about the size distribution of the constitutive material. That means not only the polar law of the debris size, but also a range if we have fine material filling the void between the bigger blocks, etc. It's important for modeler. How we can improve this knowledge? It's clear that from models, we have a lot of input, and it was one of the results of that to be able to have constraints on the cohesive strengths, on the layering of the size distribution, coming from model of the impact, so possible from model of the stability conditions, such kind of body. But we need to have direct observation, but the point which is important to understand is the fact that any instrument looking inside a small body is opening a small window, just a small window with a limited number of physical quantity observed. Typically, when you are speaking radio science, the study of the dynamical state from an optical image, we have only the larger structure. It's not possible to access the details. When you are looking about gravimeter, seismometer, it's something which is more local. And with the radar, it's complementary, the different instrument. With the radar, we are able to have information about the heterogeneity and the size distribution. And is now a mature technique, especially after the launch of Jura. We have a radar on board Juventas, one of the two CubeSat of the Jura, of the ERA mission. And it is a monostatic radar. Oops, sorry. It is a monostatic radar, a low-frequency radar at 60 megahertz in order to be able to penetrate. Okay, it's a full polar coded radar. I'm not going to go into the detail. But the idea is we expect to be able to penetrate more than 100 meters. Maybe the full moonlet is going to depend on the level of heterogeneity and then of the level of backscattering of the waves. With the radar, without any processing, we have a resolution in the range to 10 to 15 meters. And now we can see how we form an image. The specificity of a radar, with one measurement, we have only a range, a propagation delay. That means we don't have an image. We need to have an arc of orbit of acquisition in order to be able to form an image. And with only one arc of orbit, we have a 2D image. The 2D image, we are mixing in the same pixel information coming from the surface and from the interior. And if we want to go in a 3D model, to have 3D representation, we need to have a better coverage. And at the end is the diversity of the geometry of observation, which is giving the final resolution of the image we can have. It's one of the complexity, especially when people ask what is the resolution of the instrument. It's strongly dependent on the data volume. It's the reason why we ask more data. Okay, and with this instrument, what we expect to obtain, we want to identify the internal structures. That means if we have layering, if we have large voids, as I said, if we have subaggregates, also in the case of dimorphos, didymos, to see if we have some differences in terms of structure, in terms of texture of the material, size distribution, between the moon and the main, in order to give input to the models, to provide information to the modelers to better model the formation of the binary system and the stability of this system. We also want to have information about the average permittivity. With the radar, we are measuring jointly an information which depends on the contrast of permittivity and of the scale of the heterogeneity in fact, is the scattering. If you have small, fine particles by regard to the wavelength, you have no scattering. If you have particles as blocks at the size of the wavelength, you have a large scattering. We have measuring a mix of the two, but with a large coverage, we can deconvolve partially the two information and have information about the permittivity. That means the composition and the density, and to map this information in 3D. It is an example to illustrate of a scaled measurement. In fact, is a measurement done on a 3D printed model of asteroid. You know the shape of this asteroid, and it's a 3D printed. We put in the big anechoic chamber, and we do similar experiments at Jura at 30 gigahertz, sorry. And with this data set, it's possible to inverse the data, and you have an example of inverse data here with the three cuts on the bottom of the slide, and you can identify the surface, and also we have inside the 3D printed model a seed with a higher permittivity, and you can recognize this seed inside the inverse data. Is what we ambition to do with Jura. Here, the electronics, the instrument is a fly model, typically 1U, 1 kilogram for the electronics. And for the antenna, we are 2 cross dipoles, that means 4 booms. Each boom is typically 1.26 meters and 60 grams all included. You can see the mechanism of the boom folded is a carpenter spring you can deploy on the fold during the operation. Okay. It is Jura on the way to Didymos and to be operated in 27. We expect with the CubeSat 2 months of operation at a distance ranging between 2 and 2.5 and 1 kilometer to the surface of the body. Now for Ramses, in fact we plan to do the same, it's the same consortium. Plus TIVAC International, TIVAC is leading the development of the CubeSat, one of the 2 CubeSats. And the idea is to do exactly the same. In terms of science objective, is quite similar. In fact, we want to identify the same kind of structure. But it's clear that now one question for Apophis is this question of bilobed structure, if we have subaggregate, to be able to have a differentiation or how to quantify how the 2 lobes are different, and what is the connection between the 2 lobes. And in this case, it's clearly relevant information to better understand the evolution during the Earth encounters, the tidal effect. We have also secondary objectives for Apophis. One is to use the radar as a classical radar for higher frequency. In higher frequency, at high frequency, it's usual to do interferometry, to use radar for the ranging, and for Apophis, we propose to try to see what we are about to provide using our instrument in such kind of mode to support the orbit determination and also the determination of the dynamical state. Typically, we are going to be able to measure the position with an accuracy in fraction of a wavelength, that means some meters. And this can be useful to monitor the evolution of the dynamical state before and after Earth encounter. Another point, which is more prospective, is to study the feasibility to have measurement between the Earth and the spacecraft. It was a long question. We started to discuss that 20 years ago or something like that. And the idea is to use LOFAR, which is a system to receive radio waves on Earth, and to use LOFAR to receive the radar waves after propagation throughout Apophis on the surface of the Earth. It's clear that it's something really prospective, but it's a unique opportunity we can have to do In terms of instrument, we are close to a refly of ERA. The instrument is now under production. We started the production in January, and we are going to implement minor evolution, lesson learned from ERA, question of position of the matching network, improvement of the thermal design, and also some onboard compression. And also we have to look the accommodation on a new platform. It's a new CubeSat. You have a new protocol for the communication, and also you have the question of the antenna accommodation. The accommodation of low frequency antenna, like a dipole is, when we want to have a good quality of the signal, is not a problem of telecommunication, it's a radar. That means we need to have the best quality, the best calibration of the antenna, is something complex we are working on. Okay, as I said, it's a refly, but with minor modification. We are also involved in another mission, which is a Caltech mission to Apophis. Carol Raymond will present the mission later in this afternoon. And we are working on a bistatic version of this instrument, in fact. The idea this time is to use two CubeSats to study the direct propagation of the wave between one CubeSat and the other one. Is what we did 10 years ago on Rosetta with concert experiment studying the propagation of the wave between Philae landed on the surface of Chury and Rosetta orbiter. And the interest of this configuration is the fact that we access a direct measurement of the dielectric permittivity because we have the wave propagation throughout the body. And with that, we have another way to do the tomography, and is a way to decorrelate the information coming from the size distribution and the information coming from the permittivity. Okay, this bistatic mode, inheriting from concern, as I explained, and we are going to have more rich information on, with this mode, in fact, we arrived to a limit, a theoretical limit to a tomography at 5-meter resolution, maybe a little bit better, could be better, but it's something like that. But in this case, we need to have a full coverage, full 3D coverage of the body. That means to have a lot of data we can imagine. In practice, we are going to have something in the range of 10-meter 3D. If we have 10-meter 3D, it will be wonderful. With this configuration, the goal is to have an alternation of sequence of bistatic measurements throughout the body, and also to have monostatic measurement. That means to have a versatility between the different radar modes we can expect. In terms of instrument, in this case, the main problem is to have the synchronization between the two instruments. We have two electronics with two different clocks, and we need to have a synchronization in order to have the same frequency and the same timing, in order to have the information of the phase, which is crucial when you want to do a 3D radar processing. To do that, the idea is to use the intersatellite link between the CubeSat and the main craft, and to have, during the operation, each CubeSat looking at the main craft in order to preserve this synchronization in time and in frequency. And in this case, the two electronics are just to pick the information of frequency reference and time reference to the ISL. And with that, the development of the ISL is under study at the moment. With that, we have still a significant revisit of the instrument in terms of software and firmware, because we have to implement this bistatic mode and to preserve the monostatic in the same time. It's now under study. And I think that's it. Thank you.
Our next speaker is Patrick Michel, and he will be talking about Ramses.
Thank you. Good afternoon, everyone. Always happy to be here. So Today I will present the Ramses mission, which is under study at the European Space Agency. Ramses stands for Rapid Apophis Mission for Space Safety. So before going to Ramses, I'd like to show this slide, which reveals the incredible diversity of asteroids, as you can see, with different kind of shapes, of sizes. Composition does not reflect here, but densities. We even have many binaries now. But what is really exciting and also intriguing is that we now know that images do not necessarily tell us the mechanical response of an asteroid when you touch it. And this is, of course, very important for planetary defense, because if we send a spacecraft to deflect an asteroid, we want to know what would be the response. And when you see those images, you could think, okay, we have a lot of boulders, so the surface will have some strength, and therefore it will be hard to resist to any action. And in fact, the recent missions like OSIRIS-REx or Hayabusa 2 told us that these images can be misleading, because even though the surface looks like a solid, in fact, when you touch it, it behaves like a cohesionless surface. Not like a fluid, but almost like a fluid. So basically, with the OSIRIS-REx touch-and-go sampling mechanism, when it touched the surface, there was basically no reaction of the surface. So that shows that we still need to interact with those bodies if we want to better understand their behavior, and if we want eventually to relate images to the actual mechanical response of these bodies. So the great thing is that on Friday, 13th, April 9, 2099, NATO does the job for us. It interacts effectively with an asteroid through tidal forces. So we don't even have to make an interaction ourselves, which has always been what we have done so far with a sampling tool or an impact. This time we just go there, we observe how tidal forces influence the property of an asteroid. And this is spectacular. This is something that happens only once every millennia. So it's our only occasion to see that happening. And this is so exciting that we have the UN resolution that 2029 is now the asteroid, the International Year of Asteroid Awareness and Planetary Defense, because effectively this is really the great opportunity to tell the world what we're doing. First, to tell that Apophis will miss the Earth, and then observe what happens. So because of that, the European Space Agency started development, waiting for formal approval at the ministerial in November 2025, of the Ramses mission, which aims at arriving at Apophis before the close approach, measure its initial properties, observe how they change due to the influence of tidal forces, and therefore tell us about the behavior of these objects in their natural environment, which is really exciting. So there will be all the measurements that are shown here about the physical and compositional characteristics of the object, including the shape, the rotation axis, internal properties, surface properties, etc. And that will be done before, during, and after the encounter. And also something very interesting, that we will take images of the asteroid during the closest approach, and we will feed them to the public, while more than 2 billion people will see the light with naked eyes in Africa, in Nice, and in other countries that are in Europe and basically Africa and part of Asia. So I can imagine a child looking at the light in the sky, and then on a screen, the real images of the asteroids. This is really absolutely exciting. So to do so, of course, we have to launch very quickly. You will see in 2028, so there is only 3 years left. So that's why, in order to be ready, we basically use the heritage of Hera and essentially rebuild the platform of Hera, adapted, of course, to the case of Apophis. Apophis come closer to the Earth than Dimorphos and Didymos, so you need a smaller antenna, smaller solar panel. However, you have a higher delta V, so you need a larger tank. So it's basically an adaptation of the Hera platform, which, by the way, was built in only 4 years. So it's already really a great milestone. And so now we use it to build another spacecraft, this time in 3 years, basically. There is, as you can see, a mid-gain antenna and a smaller solar panels. We also have international cooperation, in particular with JAXA. JAXA is providing a thermal infrared imager, the same as on Hera. Also solar arrays. And there is a discussion that they could provide also the launcher A3 to be confirmed. And there is a synergy with the Destiny mission, which is a Destiny Plus, which is a mission that aims at the flyby of Phaeton, you know, this active asteroid, but on its way, it should do a flyby of Apophis, in principle before Ramses arrives. So that would be great because we could have a better informed shape model to start with when Ramses arrives, saving time for the close proximity operations. And with NASA, as you will see in the next talk, there is also an amazing mission called OSIRIS-APEX, and we are already discussing with APEX to have a synergy between the two missions. In terms of mission profile, so the launch will take place in the spring 2028 with a 10-month direct transfer to Apophis. So basically the mission will start really at the end of February 2029, about 2 months before the close approach of Apophis, and then there will be a series of trajectories leading us to the closest approach, where we'll be do a hovering and therefore observe the changes, and then go back to hyperbolic orbits, and with a mission nominally ending in August 2029, but we may also be extended depending on how it goes. These are the core and opportunity payloads. So at the core payloads, we have the one that we are already ready, basically the cameras and the radio science, of course, for the mass determination, accompanied with inter-satellite link, because we have 2 CubeSats like on Hera, and using the link, the communication link between the CubeSats and the spacecraft, you can better measure the trajectory of the CubeSat and the influence of the gravity of the asteroid and enhance your knowledge of the gravity field. So out of these 2 components, cameras and radio science, we have other payloads that have now been selected by ESA. So there is, of course, the thermal infrared imager, I talked about it, by JAXA, laser altimeter. We have also Hamlet, which is the same as the Hyperscoot imager on Hera, but extended to longer wavelengths. So this is nice because we can see the 1 micrometer band, which is a characteristic of silicate minerals and characteristic of S-type asteroids. We have also another high-resolution camera in the middle range with colors. And we have something quite original, which is a sort of a plasma spectrometer. You would wonder why we use a plasma spectrometer of an asteroid. Well, why? We don't know. That's why we put it. In fact, we come within the Earth's magnetosphere, so there may be some effect of the magnetosphere. You know, there is a theory that maybe it can cause dust levitation that could explain why some asteroids look fresher when they come close to a planet. Don't ask me more, that's all I know. And then we have 2 CubeSats. So one will carry the low-frequency radar that Alain just talked about, as well as a dust detector and analyzer, which is also on Hera. As you see, we really use the heritage of Hera. And the second CubeSat is planned to land. This is under study. This is to be confirmed. And will then carry a seismometer, a gravimeter, and a magnetometer. And this is absolutely exciting because we have decades of seismology studies on the Earth, on the Moon, on Mars. We never did it on an asteroid, and this would be the first time we measure how the seismic waves propagate into an asteroid while it vibrates against the tidal forces of the Earth. So this is really exciting. And if you combine the measurement by a seismometer with the measurement by the radar, which both have some degeneracies, then you have a better, even better knowledge of the internal properties of the asteroid. So that's going to be absolutely exciting. Close proximity operation, we have different epochs where we will do some hyperbolic arcs in different ways until we hover at low distance, 1 kilometer, and then go back at 5 kilometers. So these are the series. I can show you a few examples of these kind of arcs where you see the asteroid and you see here these hyperbolic arcs that we start to do that allow us to get a surface covered with a resolution of only 1.2 meters. Then we have a bow tie, what we call bow tie hyperbolic arcs. We even reach a higher resolution, less than 1 meter. And finally, we have hovering with simultaneous science and Earth communications that could feed in live the images to the public. So in terms of programmatic status, the contract with the OHB Italy, the industry was signed at the last International Astronautical Congress in Milano. That was in October last year. So there was a successful PDR already done in January. And then we have the 2 CubeSats, which are going through SRR, one by TIVAC, also in Italy, and the other one by MXIS in Spain, with also a GomSpace contribution. So this is going nominally, and as I said, there was a pre-funding phase that was approved because we couldn't wait the Ministerial Council of ESA in November this year to start the development, to be ready in 2028. So the member states kindly agreed, those who contribute, kindly agreed to already put some money on the table to start the development until we have formal approval in November. So these are the master schedule where you have the PDR that was already passed. We have a CDR that will go across the Ministerial Council in November. Spacecraft integration up to December 2026. Qualification acceptance review in first quarter of 2028. And then the launch in April, March 2028 to arrive at Apophis in the end of February 2029. As a comparison, I had put a little square the development of Hera as a reference, and you can see that we squeeze even more the schedule in order to be ready. But as I said already, Hera proved to succeed to develop something in a very, very, very quick time. So we are very confident that this can be done within the time, and with a project team led by Paolo Martino at ESA is absolutely fantastic, do a lot of work, and we are super excited and confident. Another thing is international cooperation. This is very important. We have demonstrated with DART and Hera that we are happy to work together. So Hera is now on its way, and so we can do the same. In this case, a little opposite. So the ESA arrived first at Apophis, and then OSIRIS APEX, that will be presented just afterwards, come just after, and we can have a sort of a continuity between the measurements that can extend over a long time scale. And this time we would have Destiny Plus maybe arriving first, then Ramses and Apex, and maybe other missions. There will be an Apophis session later today. You will see that there are a lot of other projects that are planned to go, which will require that we coordinate very well so that we don't crash into each other. But again, I'm confident we can do it because we enjoy working together. So in conclusion, I would say that Ramses is a way for ESA to demonstrate a very rapid response, which is one of the objectives of planetary defense. For the second time after Hera, we have a deep space exploration of an asteroid with not only one spacecraft, but a mother spacecraft and 2 CubeSats that operate together in order to enhance the science that we can do that feed into planetary defense. We have promising synergies with at least OSIRIS APEX. Already we are coordinating Destiny Plus and possibly other missions. We have contributions from international partners. We have also a great science return over a very rare event that will allow us for the first and maybe only time to observe the natural behavior of an asteroid under natural forces. It's absolutely spectacular. And of course, a great opportunity for public outreach because, as I said, having missions there while people are looking is not only good for the inspiration, for the science, but also for the message that, we always work together internationally, and this is very important regardless of all geopolitical tensions. With this, I will thank you. I just finished by showing you what won't happen. This is a simulation that we did with my former postdoc Yun Zhang about a tidal encounter, but this time at 3 Earth radii. This is a rubble pile, and if this happens for Apophis, that would be super cool, but that won't happen. Let's see. We turn an asteroid into a sausage, basically. Okay, thank you.
So our next talk is from Anjani Polit. Discussing OSIRIS APEX and its encounter with Apophis.
Great, thank you so much. So Patrick just gave a great overview of Apophis and also the international cooperation and possible synergies between missions. So I'll go ahead and dive right into the NASA's OSIRIS Apophis Explorer mission. And I'm Anjani Pollitt, OSIRIS Apex Deputy PI at the University of Arizona. Next slide, please. So OSIRIS Apophis Explorer, or APEX, is a NASA mission that is already on its way to Apophis. That long journey to Apophis began in September 2023.
Okay,
After...
Anjani, could you hold on
Yes.
for just a second, and we'll note the time on the timer. Your slides are not showing in the room.
Got it. They're showing on my screen, so that's all I know.
Okay, now they just went up. Okay, thank you. Please continue.
Okay.
Sorry.
Great. This is the first real slide, so we'll just start here. So yeah, as I was saying, the journey to Apophis began in September 2023 after the OSIRIS-REx spacecraft, which is shown here, dropped off the sample return capsule full of asteroid Bennu sample. That's here in the white in the middle that's crossed off because it's no longer on the spacecraft. So we were able to repurpose this great spacecraft for this mission of opportunity. This is a New Frontiers class spacecraft that was specifically built to rendezvous with and study small bodies like Apophis in extreme detail. We do have a highly capable payload specifically built for that. So that includes the OCAMS camera suite built by the University of Arizona, which includes the broadband polycam, our highest resolution imager, and the color map cam. We also have 2-point spectrometers covering from about 0.4 to 100 microns between the two spectrometers, OVIRS and OTIS. And we have the navigation cameras and also the scanning LiDAR instrument contributed by the Canadian Space Agency that produces amazingly detailed topography. Next slide. So here's our mission timeline. You can see the Apophis operations begin in 2029 and extend through the end of calendar year 2030. We will acquire Apophis as a point source at the beginning of April 2029, which we'll talk about in more detail later. So for us, the big challenge during our long cruise to Apophis is the 6 close perihelion passages that we have at 0.5 AU. This is a challenge for us since the spacecraft was only designed to get 2.77 AU. And so the spacecraft team had to come up with some special configurations to accomplish this. So as of now, we have completed our first 2 perihelion passages, which are shown by the green arrows on this timeline. And we're actually right now, the spacecraft is in the middle of our next perihelion passage. And then we have a break before the last 3, which are shown with the yellow arrows. Upcoming, we have an Earth gravity assist in September of this year, and we will be using that for instrument calibrations. Next slide. So to show the journey and trajectory form, that's here on the left. The starting point is their little red arrow and a place that says start. And so that shows that we're doing these loops around where we have the close perihelion passages. And the arrow labeled Apex shows where the spacecraft currently is before coming around to that EGA-3 in September of this year. And on the right is our newest poster showing Apex during perihelion. And if I was there in person, I would be handing out stickers based on this. So next slide. The summary of our objectives, we have 3 main objectives for OSIRIS Apex. The first objective relates to the close encounter that Apophis will have with Earth in 2029 and looking at those effects on the asteroid. So looking at the change in the rotation state, any mass shedding, resurfacing on the asteroid and studying that in detail. The second objective relates to the determining the overall characteristics of this S-complex near-Earth asteroid, looking at its global composition, thermal and photometric properties, and bulk structural properties. And our third objective relates to studying the properties that help inform planetary defense knowledge and strategies. And I'll just also note that see the poster from James Roberts for more on our objectives and plans. Okay, so what will we actually accomplish when we get to Apophis? This is our proximity operations timeline. At the left, you see an arrow that shows first light. We will start observing at the end of March and will acquire Apophis as a point source by the beginning of April, and then the from before the Apophis close encounter with Earth. And our first couple of mission phases will focus on getting the rotation, the shape, the mass, and then we have a number of mission phases in which we will be doing detailed mapping of the asteroid from various geometries and also studying the orbit and the Yarkovsky effect. And then at the end of the mission, we'll be looking at the material properties of Apophis through an active investigation of surface disturbance, which I'll talk about a little bit more as well. So, and then at the end, our mission ends in December 2030. So to talk a little bit more about the Apophis close encounter with Earth, on the right is a graph showing that encounter imaging geometry. The red line in the middle is that Apophis encounter with Earth to provide context in case you can't see the detailed labels. And on left in the blue lines, those are showing the Apophis diameter in our cameras, for our cameras in terms of pixels, and the orange line shown on the right is the phase angle over time. So as I said, we will obtain data starting before the close encounter with Earth. We'll start obtaining regular light curve observations at least 12 days before the close approach, and we will continue to observe after the close encounter with Earth to look at that possible change in rotation state for Apophis. We will also, around this time, be focused very much on looking for dust liberated by the encounter. So again, we'll start observing beforehand, and then after the encounter, during and after the encounter, we'll search for dust liberated by the tidal forces that have been acting on Apophis. And that will, be looking at the mass shedding. And Apex will be in a unique position at this point to make this measurement. We'll be far enough away to see the environment around Apophis, but we'll have good viewing geometry for these types of observations. And then, of course, we'll start our approach to Apophis, and those observations later in approach will be used to develop the shape model and lots of other things. So this proximity operations slide here, I won't go through all of the details here, but generally what we are doing to contrast with what we did at Bennu. For asteroid Bennu, it had a 4.3 hour rotation period, and so we could observe for one rotation period and build up a global coverage of the asteroid, whereas at Apophis, we will have to observe at regular intervals every few hours in order to slowly build up a coverage because of its slower rotation and non-principal axis rotation as well. So to talk a little bit about some of these mission phases, I talked about acquisition and approach already. We will then go into a series of hyperbolic flybys in gravity survey, and then we'll go into triangle survey, which is shown on the right. It is what it sounds like. We're flying in a triangle pattern to get mid-phase angles so that we can build up a medium resolution base map. And then we will go into a terminator orbit to acquire our high resolution shape model with the LiDAR instrument on board And then following that, we have the starfish surveys, which are shown on the right and are in the shape of a starfish there. Again, trying to get a wide variety of phase angles from low phase angles up to about 120-degree phase angle. And that is for the color imagery and spectral mapping and photometric mapping as well. So, and then finally, the variable phase orbit is a resonant terminator orbit shown at the bottom right-hand side, and that will be used for acquiring high-resolution base map. Let's go to the next slide. And so, okay, I'll talk about our final phases, which are the reconnaissance and STIR mission phases. So at the right is an animation of what STIR will do, which is the spacecraft thruster investigation of regolith, where the spacecraft will descend a couple meters from the surface, blow the thrusters, the backaway thrusters, and disturb the surface of Apophis. But before that, we will do close reconnaissance flybys. On the left is an example from OSIRIS-REx, where we got to 250 meters above the surface. And from there, we're able to map in sub-centimeter pixel scale a region of Bennu. And so we will be doing the same thing for Apophis, looking at some really high resolution looks at some specific regional areas on Apophis that are of interest, including the site that we plan to STIR. And so the STIR maneuver is really exciting. We'll get to look at the photometric effects of space weathering from this, as well as the near surface structure and mechanical properties, because we will do the STIR maneuver, we'll back away, we'll monitor what we actually did to the surface, and then do another reconnaissance flyby to characterize what we did in extreme detail. Okay, next slide. Okay, so this is the final slide. Again, just want to emphasize what an exciting opportunity this is, that Apophis will fly so extremely close to Earth on April 13th, 2029. As Patrick has already talked about, this will be a great high visibility event across the world. And so to summarize, APEX will fly by the Earth an hour after Apophis. We will be providing unresolved images in the days before and resolved images after the encounter, followed by 18 months of proximity operations around the asteroid to map it in great detail. And we will be exploring this S-complex asteroid with the New Frontiers caliber scientific payload. And this is really important since these S-complex asteroids are the most abundant near-Earth asteroid population. And we will be conducting multiple unique investigations, as well as, of course, having great synergy with missions like Ramses that are also planning to be there. So in that case, we have some unique things. Each mission has unique things that we will be doing, as well as some great overlapping capabilities to produce the best science from that cooperation and synergy between the missions. So for APEX, that will include global high-resolution imagery and visible to thermal IR spectra. We will be able to look in great detail at the changes caused by the Apophis close encounter with Earth, both from the mass shedding perspective, which we'll look at right during and shortly after the encounter, as well as looking in detail at possible resurfacing or landslides on the surface. We will be doing the STIR maneuver, the spacecraft thruster investigation of regolith, as I already mentioned, which will give us the geotechnical properties of the near surface, informing planetary defense. And we will also be studying a change in the Yarkovsky effect from the changes that Apophis went through from that Earth encounter. So looking at how the orbit will evolve over time. So again, we're really excited by this mission. Everything so far in cruise is going well, and we very much look forward to being part of the worldwide response to Apophis. Thank you.
Thank you. And I just want to remind our remote speakers to stay online for the Q&A session at the end. Next up is Makoto Yoshikawa, and he will be talking about planetary defense activities at JAXA. Thank you.
Okay, thank you. I'm going to talk about the planetary defense activity in JAXA. And now in JAXA, we have a planetary defense team. And all of these courses are the members of the team. Okay, so at first, I quickly summarize the activity of planetary defense in JAXA. And then I will talk about the recent work for YR4. Collision probability analysis and deflection by Hayabusa 2. Okay, so this slide summarizes the JAXA's activity for planetary defense. We are doing many things: observations, space missions, orbital analysis, and international and domestic activities and outreach. So, for example, this is an astro observation in JAXA. We have Bisei Space Guard Center, where we have 1 meter and half meter telescopes. The main observations are space debris, but of course we observe asteroids. And we have small telescopes inside JAXA and in Australia. These small telescopes are mainly experimental use. So, for example, we developed a method to discover small, fast-moving small objects by using the stacking method. So we take lots of images in short time exposure, and we overlap them to find the moving object. So in our experimental observation, we found these small near-Earth object by using very small telescope, just 20 centimeter or so. And of course, we have the NEO missions. We had Hayabusa and Hayabusa 2, and now we are operating Hayabusa 2 Sharp, which is an extended mission of Hayabusa 2. The targets are Hitokawa, Ryugu, and Torifune, and 1998 KY26. All of them are near-Earth objects. And we are collaborating with ESA for Ramses, for Hera mission and Ramses mission. And in future, we will have the Destiny Plus. This is a Phaeton flyby mission, but maybe it will fly by also Apophis. And we will discussing the next generation sample return mission. Maybe the target is a comet. So this shows the Hayabusa 2 extended mission. So we have 2 targets. One is a Torifune 2001 CC21, and this is a flyby mission. So spacecraft will fly by this asteroid next year, July. So relative velocity is 5 kilometers per second. And since Hayabusa 2 is a rendezvous mission, we need to have spacecraft pass close to the asteroid to get the good data. So we need accurate navigation technology. So this will also contribute to the planetary defense. And then we have 2 Earth swing-bys. Actually, these 2 swing-bys are important for the YR4. I will talk about this later. And then a final target is a very small asteroid, 1998 KY26. The original estimation was that the diameter is just 30 meters, but a recent paper says that much smaller. The diameter is 11 meters. And the rotation spin period is originally estimated about 11 minutes, but the recent paper says it is just 5 minutes. But so this is very tiny and object, but such object is very important for planetary defense because Earth's collision probability is, roughly speaking, once in 100 years or so. Okay, so this is Hera and Ramses collaboration with ESA. So So now you know this because previous presentations talked about this. And anyway, for Hera, we provided the infrared camera TIRI. And for Ramses, we are considering to provide TIRI, infrared camera, and lightweight solar array paddle, and possible launch opportunities. So for this, in detail things, please see the poster by Okada-san. And except for Ramses, JAXA currently has no plans to launch a new satellite or spacecraft to Apophis, but we are investigating the possibility of observing Apophis using existing satellite. This is currently under consideration, and no conclusion has been reached yet. But detailed thing, please see the poster by Ikenaga. And this is the outreach activity of JAXA, Asia Pacific Asteroid Observation Network, APAON. The purpose of this APAON is to promote the asteroid observation in the region of Asia and Pacific. We started this activity from 2013, but about 7 years ago, we stopped this activity. So now we plan to restart this activity. Okay, so let's move on to the next topic about the YR4. So first, collision probability analysis. So JAXA has a software called Deep Space Multi-Object Orbit Determination System. We use this software to operate our deep space spacecraft. And for example, and this system has ability to simultaneously estimate the orbit of deep space probes and target celestial bodies. So for example, we use this software to Hayabusa 2 mission, and we use, and these operations were carried out. And now we add one function to this software, a function to directly import asteroid observation data of ground-based telescopes. So we use the MPC data, and we can determine the orbit of asteroids. So using this software, we calculated the collision probability of YR4 to the Earth in 2032. So these figures are the same that many people showed. This is a B plane, and the green circle indicates the position of the Earth, and the line shows the uncertainty of the position of YR4 at the time of 2032. So if we use the data up to February 6, the left-hand figure, the collision probability is estimated as 0.8%. And if we use the data up to February 16, the middle, the collision probability is about 2%. And the right one, if we use the data up to February 27th, then collision probability becomes almost zero. So these estimated values were almost consistent with those by JPL and ESA. And we calculated this probability by using the Monte Carlo simulation. So this movie shows our result of calculation. So in this movie, the particles that collide with the Earth are not deleted after the collision. So be careful of this. Okay, so next thing is the deflection of YR4 by Hayabusa 2. Of course, we do not have to do this. We do not have to do this, but this is just a case study. So we investigated whether it would be possible to change the orbit of YR4 using Hayabusa 2, which is currently in flight. And the result is yes. And but if we must give up the final destination, 1998 February 26, and if we change the condition of Earth swing by, then we can send Hayabusa 2 to YR4. there are two cases. Case one, we use the first Earth swing by in 2027 December. So in this case, YR4 intercept is 2028 September, and the intercept velocity is 16 kilometers per second. And case two, we use the second Earth swing by in 2028 June. And in this case, the intercept is 2028 November, and the velocity is about 11 kilometers per second. Then we studied the change of the velocity and position of YR4 when HiveSat-2 collided with the YR4. So result is here, but here we assume that the size of YR4 is about 50 meters in diameter. And this value is a little bit smaller than current estimation. And we assumed the density is 2 grams per cubic centimeter. So if HiveSat-2 collides to the YR4, the velocity of YR4 change like this, case 1 and case 2, and it depends on the impact efficiency. So we choose impact efficiency from 1 to 4. So the velocity changes, for example, in case 1, and impact efficiency is 1, then delta V is about 6 centimeters per second. So this is rather big. And on the B plane, the position of YR4 changes, but it shifts towards the Earth. In this case, we use the solution up to the February 6th. So this is not good because YR4 come close to the Earth. But anyway, we find that just HiveSat-2 impact, we can change the orbit of YR4. So finally, this shows the fictitious case where YR4 collide to the Earth. So we chose one orbit for YR4 that will collide to the Earth, and if HiveSat-2 impact to the YR4 in 2028, then finally the position of YR4 can be changed, not to collide to the Earth. Here I showed two cases, efficiency is 2 and 3. So HiveSat-2 can change can save the Earth, but of course HiveSat-2 is a rendezvous mission spacecraft. So technologically, it is very difficult to collide with a small target by high speed. But anyway, this analysis indicates that if we have lots of spacecraft in near-Earth region, it is very useful. So that is this new idea, a deep space constellation concept. In this concept, we launch a lot of spacecraft in near-Earth region, and each spacecraft repeats the Earth swing by, and during Earth swing by, it can fly by an asteroid. So simply speaking, if we have 12 spacecraft, then we will have asteroid fly by once in every month. And the good thing is, if we find a new object like YR4, then we can quickly change the orbit and to visit the new object. Okay, so this is a summary. So JAXA has started to contribute to planetary defense in many things, and we will just started this work, but we want to enhance our activity in future. So the final slide is we have many support like this, and now I think Japanese people also acknowledge this activity. So thank you very much for your kind attention.
Okay, our next talk is by Masatashi Hirabayashi, and he will be discussing Hayabusa 2's next encounter. Take it away, Tashi.
All right, thank you everyone for having me today. I'm going to discuss a little bit about science operation planning for Hayabusa 2 Sharp at asteroid Trifune on behalf of Hayabusa 2 Sharp team. All right, so first of all, I'd like to introduce a short summary of Hayabusa 2 Sharp. This is Hayabusa 2 extended mission, which is the extended mission of Hayabusa 2. Previously, the sample return mission that was successfully bringing samples from Ryugu to Earth in 2020. Hayabusa 2 Sharp has a specific mission objectives, including long-term space flight operations, which has been about 10 years already since the launch. Exoplanets and zodiacal light monitoring Trifune flyby in 2026. And last one is 1998 KY26 rendezvous in 2031. My presentation is going to focus on flyby operation planning. The flyby operation specifically has mission objectives, including or basically coming from technological innovation in planetary defense. Those are based on both engineering and science perspectives. I want to mention a little bit about the space flight status right now. Recently, spacecraft encountered the safe mode. However, the team is currently working on the issue and its resolutions. So in terms of Trifune flyby condition, the spacecraft will approach the asteroid at a distance from the Sun of 0.81 AU. At the time of flyby, the phase angle would be around 20 degrees and encounter speed is around 5.25 km AU. The encounter date is currently set July 2026. Regarding Trifune's geophysical conditions, it is still unknown. However, thanks to dedicated observations in the community, we are getting more information. Some of them are here. The size or equivalent diameter is between 0.3 and 0.5 kilometers. Shape aspect ratio, or B over A, is between, around 0.5, where A is a long axis and B is a short axis. Taxonomy is S-complex, possibly SQ. Spin period is 5.21 hours. Spin axis is reported to face toward celestial north. Geometric albedo is about 0.2. So I am showing here two shape models driven by light curves. As you can see, the common feature is like elongated shape. So we are expecting to see this kind of elongated shape. However, the key issue here is those two shape models developed by two different groups give us some inconsistencies, meaning that we still have uncertainties. So this is sort of like advertisement, but if we consider the next observation opportunity, it is going to be happening end of this year. So if you have some observation time, that would be great to have some observation for this asteroid. Those are very important for us to do planetary flyby planning. So I'd like to discuss a little bit about how flyby operation at Trifune can contribute to planetary defense technology. I am considering here Torifune flyby is a great opportunity to consider particularly targeting fast reconnaissance. Fast reconnaissance is a campaign to get key information of a hazardous object prior to the planetary defense action. Let's consider this way. When you have telescopic observations identifying a hazardous object possibly hitting the Earth in short term, in this case, you have to take action very quickly. However, having key information prior to that action, it would be very beneficial. So, for example, telescopic observation, space flight observation, those are key fast recon operations. Recent NEO warp effort identified that the primary properties to be characterized would be compositions, mass, orbit, and strength. Regarding the spaceflight observations related to fast recon, flyby would be the quickest proximity operation to do so. One idea would be to make fast recon happen is to use a retired spacecraft. By retired spacecraft, I mean the spacecraft flying right now or at the time of investigation, and it has completed its nominal mission. However, when it comes to this particular condition, having a retired spacecraft doesn't mean you can get ideal situation to meet observational requirements. Hayabusa 2 Sharp is exactly that example. For example, the spacecraft was designed for rendezvous, so it's not for flyby. For example, the spacecraft doesn't have a rotational or rotating platform. Also, spacecraft is already old, older than 10 years. So the instruments are getting degraded. However, this is a great opportunity because we would be able to use a retired spacecraft to see how this condition can advance or characterize the primary properties. So Hayabusa 2 Sharp's flyby planning, it will have 3 sequences. First one is on-ground GNC phase. This is going to be between T-minus 10 days and T-minus 12 hours. In this phase, we're going to have TCM, radar, and optical navigation. It will have a ground station in the loop actively. On-ground GNC phase will be happening between T-minus 12 hours and T-minus 5 minutes. In this phase, it will not have a ground station in the loop. It will be happening everything on board. Finally, encounter phase will happen between T-minus 5 minutes and closest approach. This particular phase will be focusing on science investigation. So, in order to characterize the properties we want to pursue, we will use 5 different onboard remote sensing instruments. ONCW1 is a wide-angle camera. ONCT is a narrow-angle camera. TIR is a thermal imager, and NIRS-3 is a point spectrometer, and the last one is LiDAR. Once again, the spacecraft does not have a rotation or rotating platform. Also, we are not planning to have any major slewing processes, meaning that we're going to have huge challenges. However, it is necessary to make sure all the instruments can get meaningful data from the closest approach. So, given this particular conditions, we have been working on flyby planning for the last few years. The final findings will be completed within a few months, but we are getting a very exciting solution here. For example, we are trying to close Torifune as much as possible, possibly within 10 kilometers from the target asteroid. This is not from science investigation, but this is from engineering perspective. This particular plan actually gives science investigation benefit. For example, we will have high-resolution observations without motion blur. Team has established an integrated tool to characterize best viewing conditions based on all the constraints as well as all science input. The right side, the figure is showing an example of best condition that we found from the tool by using Itokawa shape. I'd like to give a short summary of flyby conditions here. The left side, I am showing phase angle evolution around the closest approach. As you can see, the center is closest approach time, and before that, phase angle is keeping around 20 degrees. However, after closest approach, it goes to 160, meaning that we only have a chance before, only have a chance to see Torifune just before the flyby. So after that, we won't be able to see it. The right plot is showing the pixel number in one direction as a function of a T minus encounter. So if you look at the leftward, then you are seeing closer to the encounter. If you want to consider a two-dimensional pixel number, we should multiply, or we should do square the pixel showing the y direction. I am showing 3 different remote sensing conditions. I like to focus on ONCT, which is given in blue. As you can see, a few seconds before the closest approach, we're achieving about a few hundred pixels. So we're going to aim for that during the actual flyby operations. All right, so this is the summary. We are going to have a flyby operation in 2026. However, we are going to have a critical limited capability and a timing. However, we are considering that this is a great opportunity to find or maximize science returns, particularly Torifune's property characterization by using Hayabusa 2 spacecraft. Once again, the spacecraft was not designed for flyby. It was for rendezvous, and we're going to switch that capability to flyby operations. We will have degraded instruments. They are healthy right now. However, we cannot ignore the degradation, so we have to take into account all constraints. However, given that, we would be able to find the best solution to be able to maximize the science return. Also, I want to mention performing a kilometer distance flyby is a great opportunity to test Hayabusa 2 Sharp's GNC operations. Finally, I want to emphasize that Hayabusa 2 Sharp's Torifune flyby is a great example of using used spacecraft to demonstrate rapid reconnaissance operations. With that, I stop here. Thank you so much.
Okay, the last talk before the Q&A for the future and ongoing missions session will be given by Luca Conversi, and it will be on Neomir.
So, good afternoon, everybody. So I will try to highlight a bit what's the status of Neomir and yeah, what we can do from space. So for those of you who don't know, NEOMIR is a space mission, the first one that we are studying in ESA, devoted to detect near-Earth asteroids in space in the infrared waveband. And we want to do that because especially ones coming from the sun direction are very difficult, if not impossible, to observe from the ground. So that's why one of the reasons why we want to space. And then on top of it, if we observe them in the thermal infrared, especially in combination with ground-based observations, we can much better determine the size of these objects. So we started studying NEOMIR in 2021. It was already presented at the previous PDC. And at the moment we are in so-called phase A2, so we are still in the definition phase. It's been studied by 2 European industries. And we have plans, of course, to keep studying it for the upcoming years. So NEOMIR in a nutshell is a spacecraft that will be launched most likely on Ariane 6.2. It will be launched on and placed into a hollow orbit around the first Sun-Earth Lagrange point. And its peculiarity is that apart observing the NEOs in the infrared, they will observe them as close as possible to the sun. So our idea is to observe a ring around the sun that will change from 30 to 70 degrees of solar elongation. The other particularity is that it will produce quite some large data. Our benchmark nowadays, at least for ESA, is Euclid, so it will produce about 1.5 gigabit of data per day. And the target date for launch is, let's say, between 2032 and 2035. So in terms of payload design, it's basically a single instrument with a telescope of 50 to 60 centimeters. We are still analyzing trade-off over there. It's a so-called three-mirror astigmat. So the particularity of this kind of mirror design is that it provides a very large focal plane corrected for aberrations. It will have a very large field of view. It's about 1.7 by 7 degrees. It will have a single channel covering, at the moment we are aiming at 6 to 10 micron. And it will have 4 infrared detectors. The technology is similar to the one that was already flew on James Webb, on Euclid, on Ariel, and of course on NeoSurveyor. I will mention NeoSurveyor in the next slide. And there is an aim, of course, to detect as much as possible these infrared technologies, infrared sensor in Europe. So that's still something we are discussing. Since it's an infrared instrument, of course, everything needs to be cooled down. And we have still also over there, we have studying the options of having a fully passive system or having an active cryocooler for the detectors. So in this plot, what I want to show is basically what nowadays we can do from the ground. Current surveys, they don't go so close to the sun, but in principle, this is possible. And in red, you see the NeoSurveyor field of regard, so the one that will be explored by NeoSurveyor. And all these dots, as you see, these are simulations of impactors and where they are different times before the impact. And basically what we try to do with NEOMIR is to cover the missing ring. So in terms of observing strategy, the basic observing strategy is basically, as I said, to do a ring around the sun at different solar elongation. And we are still thinking about 2 options. One is the classical one, which would be basically to go on a given field, observe for 1 minute, and then move to the next field, and repeat this cycle 4 times before we move to the next ring. And the second option is to do a synthetic tracking technique, so that basically we'll go to a given field, stay there up to 4 or 5 minutes, but taking much shorter exposures, down to 10 seconds exposure. And then to do a post-processing on the ground, stacking the images using synthetic tracking technique. There are pros and cons. The main issues that we have with the synthetic tracking technique is, of course, a much higher data rate and the number the amount of overhead that you have in reading out the detector. But the process that you can gain up to a factor of 2 in signal-to-noise ratio, of course, assuming the same amount of observing time per field. So now I want to show you some results we have about trying to assess what Neomir could detect. So we started from I called quote-unquote populations of impactors. It's been provided by Steve Chesley. We have it's not really a population, but let's say we have a number of orbits, 3,000 orbits of objects that will impact Earth. And then we assume that none of these objects have been detected, and so we propagate these orbits in the last 60 days before impact. And out of these 3,000, about 1/3 will pass in front of Neomir field of regard in these last 60 days. The other 2/3, of course, will go and hit the Earth from the night side, so supposedly they should be detected by ground-based observatories. So of these 1,000 impactors, then we assume 2 sizes, just to try a bit what are our capabilities. We try 35 meters and 15 meters, so basically a Tunguska-like and a Chelyabinsk-like. In the first case, we can detect up to 92% of these objects. In the second case, up to 82%. Being about 20% in both cases been detected in the last 2 days. So it's very, we'll show you later, it's very hard, and even if you detect it, to do anything. The next question we pose ourselves is, okay, we are able to detect these objects, so can we actually do anything with it? So the first thing is, okay, if you detect an asteroid, can you actually assess the asteroid is an NEO and then it's going to impact Earth? And our simulation shows that, in this case, we took a sample of 100 objects because of various issues I don't have time to discuss right now. And these 100 objects, 80% of them have an arc which is longer than 5 days, and so it's long enough to predict that it's going to impact. And also, it's long enough that the uncertainty is dropping. So, for example, if you see the graph to the right, this is showing you the blue curve is the magnitude, the visual magnitude. So the idea here is we want to know if we observe something with Neomir, can we actually follow it up from the ground? Again, remember this is an impactor, so it's getting closer to Earth as time is passing by. And so it will be brighter and brighter. So it's worth noting, first of all, that when Neomir detects something, it's basically impossible to be detected from the ground because all of them are above magnitude 26 in the visible. And also the uncertainty is very huge. At the same time, if the observational arc provided by a mission like Neomir or NeoSurveyor is long enough, you will have, on one side, it's getting closer to Earth, so it's getting easier to be observed from the ground, and also the uncertainty is dropping. Over there, I don't know if it's clear, but it's less than 1 arc minute, so even nowadays with instruments like VLT, it is possible. That's a bit the summary of what I was saying earlier, and it is that indeed we can detect most of the objects detected by Neomir from the ground, not all of them. Our statistics one says that about 57 of them are observable from Earth. And the largest majority of them that are not observable is in one of the 2 cases. Either they are too faint or have been observed by Neomir. The observational arc of Neomir is not long enough that then basically the orbit uncertainty is still too large to do a follow-up from the ground. So why it is important to do follow-up observation, actually why it is so beneficial? And well, there are 2 reasons. One is size estimation, because the moment you have infrared data plus visible data, you have a much better constraint on the size of the object. But then you also have a parallax effect. You also have this from the ground, actually, when you observe the same asteroid from 2 stations, but it's much more evident if one station is in L1 and the other station is on the Earth. So here, for example, you see the Strew fields at various times, It's on the left plot, for example, you see all the cyan dots. These are the stereo field with Neomir data alone, with this 12 days arc. And the moment we have combined Neomir data with ground-based data, you get the blue dot that probably it's not even visible in the plots, but it's just coinciding with the actual, with the true location, the true impacting location of the object. So last things is that we try to do is what Neomir could have done for Chelyabinsk and YR4. Let's start with Chelyabinsk. So here you see a plot of basically the signal-to-noise ratio as it evolves in days, let's say, from 60 days before impact down to the impact date. And similarly, the elongation. So Chelyabinsk is a really complicated object because it was in the gray area, the gray area are the limits of Neomir. So you see that Chelyabinsk was in Neomir field of regard 60 days before impact, down to 20 days. But it was so far away and so small that it was basically not detectable. Signal-to-noise ratio was below 2, I think. Then at some point it starts increasing because it gets closer. But unlikely, it gets also outside in the field of regard Neomir and gets too close to the sun that it's not observable for engineering reasons, let's say. And then it flies by. And then if it flies by, basically, both the signal-to-noise ratio will increase up to 1500, as you see. But then you only have very short amount of time to observe it. So when we combine elongation and signal-to-noise ratio into a single plot, you get basically these two plots. The one to the right is a zoom in. And each dot over there is about 1 hour observation. And there are 24 dots, actually. So basically, Chelyabinsk would pass the whole Neomir field of regard from 30 to 70 in 1 day. So the long story short here is that depending on the survey strategy we will employ, Neomir would have detected Chelyabinsk before impacting. It's another question if we were able to then assess where it would have impacted. So that's much more difficult, honestly. Regarding YR4, that's very briefly. Well, first of all, I invite you to check Thomas Mueller's poster. It goes into much more details on this. Here, what we inspected is, well, first of all, if it was visible by Neomir, and the answer is yes, and it would have been detected about 1 month before it was actually discovered by Atlas. So let's say the 1st of December, it was already visible, according to Neomir performance expectations. And so 2 things happen here that are very interesting. The first one is that, as I said earlier, given the parallax effect, the moment you combine Neomir data with any ground-based data, you reduce your uncertainty to such a level that it's basically what happened later with I mean, after 3 months of gathering data from the ground, you could have done much better just combining space data with ground-based data. The other advantage I see is that giving 1 month of working time before the flyby to Earth, then it could have provided enough time, to prepare a characterizational campaign and especially radar observations. Then with a radar observation, again, you nail down if the object is going to impact or not. So then you don't need to spend the other 2 months and GWC precious time to analyze the object. So regarding roadmap, as I said, at the moment we are in the so-called phase A. We are going to start phase B1 by the end of the year, beginning of next year. Of course, we will propose Neomir at the next ESA Ministerial Council, and hopefully if we get enough fundings, we will go into the next phases, and we will fly in 2035. And these are my conclusions, and I finish here. Thanks.
So I'd like to turn over the Q&A to my illustrious co-chair, Dr. Moisel.
Okay, so if we could ask, please, all the on-site speakers to come up to the stage. And I hope our remote colleagues are still connected. Then if we could have the questions on screen, please, that would be great. Okay, luckily there are many ways to the questions thanks to the app. Okay, so I see the top-rated one here. How many missions are currently planned for Apophis, and does satellite traffic management need to be considered? Who wants to take this?
Yeah, that's a good question. We don't want one mission to be the kinetic impactor of the other. So in fact, as we said, we identified already, Osiris Apex, which is already flying, Ramses in preparation. Maybe Destiny Plus could be a flyby, and you will probably hear later about the Caltech mission to Apophis that Alain talked about with a bistatic radar, so a mother spacecraft and 2 CubeSats. And at the Apophis T-4 workshop in Tokyo, there were other rendezvous missions by a company called X Labs and other flyby missions. I think we'll have one that will be presented later in the US. I know about another one. So basically, we have 8 to 10 mission concepts, rendezvous and flyby. Which will go, we don't know yet for sure. And this is why, effectively, we need to identify the serious players and start the coordination to make sure that we all are complementary and get more knowledge than the sum of the missions.
Okay, I might actually supplement the answer to this because there is an Apophis mission coordination working group being set up under the lead of COSPAR. Please, for those involved in the missions and the ones listening to this online, please get into contact with Pascale Ehrenfreund. She's coordinating or setting up the group for COSPAR. The idea is that we have 1 or 2 representatives per mission so that everyone can talk to each other in order not to perform unwanted impact experiments in the process of the mission. Okay, so the next question here on the screen is to Makoto Yoshikawa and Toshihiro Hayashi. Has the Hayabusa 2 Sharp team considered performing a flyby of 2024 YR4 instead of a rendezvous with the target asteroid? Because, and I think you touched, of course, on this point, but here there's the twist in the question, because YR4 still has a relatively high impact probability with the moon, which might make it an interesting scientific target.
Yes, thank you. So actually, in fact, we have discussed about this in our team, Hayabusa 2 Sharp team. And the problem is navigation accuracy. And we must do the optical navigation, but Hayabusa 2 can detect YR4 maybe just 1 day or less before the encounter. 2 hours, really. So this is very difficult to navigate. So, and anyway, next year we will have the Torifune flyby. So we have the result of flyby. So then we can discuss about the YR4 flyby, but maybe very, very difficult.
Okay, I understand. Of course, it's a risky business to deviate, but yeah, sounds interesting. Anyway, so the next question on the list I see here is: we have seen that rubble. It's now not in sync on the 2 screens that I'm seeing, so I'm going with the screen that we all see. So for Patrick, how will the seismometers be coupled to the surface of Apophis?
Well, actually, it won't be coupled in a way that it won't be attached. It's just the CubeSat will land, probably bounce, and then it's just a geophone that just needs to be lying on the surface. So there is no coupling in the sense of trying to attach on the asteroid, just lying on the asteroid.
Needs to be deposited extremely gently.
Exactly, like the gravimeter will function both on Apophis and also on Dimorphos, just coupled to the surface.
Okay, then we have seen that the rubble pile asteroids have surfaces behave in a fluid manner when struck, or quasi-fluid. I've also been told by researchers, asked the questionee, involved in the mission to Bennu, that their spacecraft would have fallen inside the destabilized asteroid had it not immediately engaged its thrusters to fly away again. Is it therefore possible to simply sink an explosive device inside such an asteroid and detonate it from within? Would this be a viable or any way helpful mitigation strategy?
So, I don't know if it would be a useful mitigation strategy. It would be super cool to try. But in fact, I made a shortcut because I think that's very interesting actually. What we see is that globally, the surface, that's both for the small carrion impactor on Hayabusa 2 and with the taxam, globally the surface behaves like a cohesionless one. Globally, because in fact, we see some boulders being displaced, which means that not everything is cohesionless. You have still solid boulders that are moved by an impact or during the taxam also, and yet globally it behaves like a cohesionless surface. So it's complicated. So I don't have a clear answer, but the key is that these surfaces are complex. So I wouldn't say that even if OSIRIS-REx behaves as it did, you would just deposit something and it would sink. Actually, the mascot lander on Hayabusa 2 bounced. So that's why, I mean, we are still in the stage where we try to understand exactly the behavior of these bodies as a function of the energy you deposit. And that's why the Bruce Willis approach, where you land someone and with a sledgehammer tries to bury a bomb, not sure is super viable. We are not at the stage where we really understand how to do that, because we see some counterintuitive behaviors.
When I saw this question, I first saw that is related to Armageddon. This is a film, right? And one of the smartest guy in the world said, well, let's do it like that. In terms of small bodies like rubble piles, I guess it is kind of creature, I would say, when it comes to outer impact. When you detonate and then when you disrupt, but it comes back to another asteroid, because reaggregation actually create another rubble pile. So depending on the input of energy, you may have a completely different result. So you have to take into account that.
Okay, thanks. For the missions that said they would characterize the interiors of the asteroids, are there any theories of what you would expect to see? Will you be able to characterize global structures around the asteroid, voids, core layering, etc.? I think this goes to Alain.
Yes, I think so. Speaking about the radar, in fact, what we are measuring with the radar is return power coming from the reflection, but also from the backscattering, the scattering. And this scattering is related to the heterogeneity. That means if you have, to be simple, if you have sound, you have a propagation without scattering because waves see only an homogeneous material. If you have blocks with large voids at the scale, as a metric scale, you have a huge scattering. You experience that in optics with the smoke, for example. And if you have an homogeneous material, you have no scattering. In fact, this information is crucial to understand the heterogeneity in a statistical point of view. If we have two different lobes inside the body, if you have a contact binary, and if you are able to detect different properties, different scattering in the two parts, that means we have different texture, we have different content in terms of size distribution, in terms of small particles filling the void between the larger block. is a crucial information for us. And in the other hand, we can see larger scale, but in this case, I'm speaking about structure at a scale larger than 10 meters, typically. In this case, we can imagine to have layering, to have a clear reflection between two blocks, two subaggregates, or to have large structure, maybe large block also. We can imagine to have monolith inside the rubble pile.
I want to say that I think this is very important information to really know what's inside, because let's say you have a low bulk density and therefore a high porosity. The question which is really relevant for planetary defense is whether this porosity is represented by microporosity of a solid material, like a homogeneous distribution of micropores, or is it due to a few large voids that decrease density? This has totally different implications for the deflection strategy, because a microporous rock does not behave as a rubble pile, a macroporous one. So knowing how the voids are distributed, whether they are micro scale or just a few large scale voids, are totally different implications. And that's why it's really good that for the first time we can do that to the radar, and hopefully do it other times, because this is really relevant for, in particular, deflection efficiency for a kinetic impactor, for instance.
We start to work with modelers to try to better understand what they need and to have iteration. But it's clear that it's something complex, including due to the fact that the scale we are able to simulate are not the same. And it's a long-term work to try to refine the input we can provide to modelers.
So I see a lot of people were missing updates on the NEO surveyor mission. Do we have this covered in another session, I guess? Yeah, exactly. So I think that's the short answer there. Lindley and Kelly nodding. So will be covered in another session. In the context of the OSIRIS APEX mission, could you clarify what is meant by a terminator orbit, given that Apophis has a rotation period of approximately 27 hours and a precession period of around 263 hours? How does the period of a terminator orbit compare to these values, is the question.
Yeah, so the terminator orbit is at sunrise, sunset, right at the boundary between night and day, and so it's not necessarily related to the actual period of Apophis. I don't recall the exact period. It's on the order of 50 hours or something like that.
Yeah, I guess it might have pertained to the mapping. It's just a bit unusually formulated. Next
Yeah, it does pose challenges to acquiring and globally mapping the asteroid with that long rotation and non-principal axis rotation. But we have actually done some recent coverage analysis of that terminator orbit to determine that we do acquire global data for the shape model with the scanning LiDAR.
Okay, thanks. I think the next one is actually for me. What are the chances? Sorry. What are the chances if the ESA November decision is bad for Ramses? We hope very, very low. Are Neomir and Ramses hurting each other's chances? Both are on the so-called cornerstone mission track for planetary defense. We can only, the funding level to our office is only sufficient to have one of these missions basically in implementation. Of course, Ramses has grown a little bit since it was studied. So I wouldn't say hurting, I would say that Ramses has filled the slot for the next ministerial completely, and this is why, if you've been following the NEMIA updates, we gave earlier dates before, and now the development timeline had to be stretched out and delayed, basically, which is not a big thing for Neomir, since Ramses is time critical, and Neomir is an infrastructure observatory at L1. However, it poses some challenges that we need to address, and we will take this, let's say, additional constraints and focus on de-risking and following the critical path and development of critical technologies. So while we have to wait a little bit longer, at least we get a chance to have time to look at the nitty-gritty details, more time than usual in development.
I mean, I would add that no planetary defense mission should ever disrupt the other one. We should have a programmatic such that actually we have a good roadmap that allow all these missions to happen with a different time scale. Of course, Ramses is first because we have to launch for Apophis, and then Enionia next. Yeah. But we should never, as a community, destroy each other by competing. We should support each other, always.
This is also, yes, exactly, something for future missions, that we might poll the community what is the greatest need, but at some point these things need to be settled and consolidated. That's also a lesson learned here. Yeah.
For the first question of the two, I can maybe add that the reason, or that one reason for our optimism is that a non-negligible fraction of the Ramses mission cost is already being spent before the ministerial.
Exactly. Yeah. So the next question is for Luca. For an object discovered by Neomir just 2 days before impact, would it even make it to the NEOCP? Is the expected data volume going to be a problem for that?
I guess you jumped to one question, but okay, let's start with the second. No problem.
Okay, yeah.
So the NEOCP, yes, I did not mention this, and basically the baseline is that we will have contact with the ground every 12 hours. So we expect to analyze the data and submit something to the NEOCP within, let's say at the 12 hours. So let's say total 24 hours since detection on the spacecraft. So yes, it would make to the NEOCP.
Good.
So it's not a problem of volume of data.
Okay, and have you considered employing a coronagraph for Neomir to allow to observe even closer to the sun?
So the short answer is no. Honestly, I'm not an expert in coronagraphs, but I think they work in the optical. This is a thermal infrared mission, so even if you remove the sun, I'm expecting maybe just the impact on the spacecraft, it's too much, but it's a nice question. I will investigate it further with the instrument teams, if that's, with industrial teams, if this is an option.
Okay, yes. Interesting question. What is the level of autonomy of these spacecraft, specifically when executing the deep space maneuver? Are there Earth-based observations of the targets involved? Is the entire plan developed on Earth and then transited to the spacecraft, or does the crafts have more autonomy to execute the mission?
I guess this depends on the mission.
I think this is for the more creative mission.
From HyEPSA to SHARP, I'm going to discuss a little bit about Tryphon flyby then. So Tryphon flyby is more based on HyEPSA 2 mission, which was a rendezvous mission. So we are going to use a ground station actively until some time. But after the point of no return, basically we're going to use onboard system. In terms of autonomy, this is a really critical point. The reason is it is going to use observational data. So in terms of that, we are actively including detailed observation. For example, the accuracy of the asteroid position, as well as what kind of shape, what kind of rotation. Those are critical factors because those are critical input for our autonomy system. I think I answered that a little bit, but not all of them.
Okay.
I can maybe add for Hera, so the deep space maneuvers that are done during cruise to keep Hera on track for the asteroids, they are all ground planned. And actually, Earth-based observations of Didymos with interest for Hera are also not from that, but they are more for arrival at the asteroid, where we would like to know beforehand the orbital phase of Dimorphos. And then the autonomy for Hera comes into the play for the close observations at the asteroid, where starting in the detailed characterization phase, the attitude will be autonomously kept, so the spacecraft will autonomously follow either Didymos or Dimorphos in the field of view, and in the experimental phase, the spacecraft will also use the data taken with the cameras and the laser also to autonomously correct its trajectory.
Thank you. So another one on Neomir. Luca, will Neomir be able to determine diameters completely on its own, or will that require some sort of optical follow-up?
Short answer is yes. Neomir alone will be able to determine diameters. Then, of course, it's a question of uncertainty in the determination. As I said, it has a single band. Still, even with a single band, it would be more precise than ground-based surveys working in the optical. Now, the moment you combine infrared data with ground-based optical data, basically you reduce about an order of magnitude uncertainty in the size. So you go from 200% uncertainty down to 20%. This is just no. So, yeah.
Okay, thank you. The next one is for Alain. How exactly can we match up internal composition with radar scattering observations? How much detail can we get from these measurements? For example, can we get porosity as a function of position or just bulk porosity?
Okay, as I said, what we are measuring is the return power, and the first tomography we are doing is this backscattered power. That means the power we are measuring with the instrument. And after, we need models to do an inversion in terms of heterogeneity, in terms of composition. In the composition, I include the porosity at smaller scales. And it's really a two-step inversion. The first is deterministic, is a SAR processing, is something, or tomography processing is something deterministic. But after, the interpretation of this backscattering is model dependent. And for that, it's very important to use information coming from other instruments, from other observation, as we did in another propagation regime for Chori on Rosetta. Okay. Now, to go in a little bit more into detail, in fact, this power we are measuring is coupling the contrast of permittivity on the scale of the permittivity, is more or less corresponding to the gradient in the permittivity. And when you are measuring with different orientation, as a phase function in optics, in fact, it's better to deconvolve this information. Is the reason why the bistatic is able to provide more information than the monostatic one, because we have this measurement to be able to deconvolve information coming from the scale and information coming from the porosity, or from the composition. But in all the cases, the density is extracted from model, and we ambition to have a map of density extracted from the map of the scattering power.
Okay, thank you. I think we have room for one more question before we wrap it up. So last round of votes. For Patrick, how will you ensure the surface maximum coverage of surface changes on Apophis? Do you have an idea of where the asteroid landslides will occur? It's a tricky question.
If even I had an idea, I wouldn't say, because so far we have always been wrong in our predictions on asteroids. So I wouldn't say, no, we don't have any idea, because even if we have a shape model, we don't have a gravity model of the asteroid, and so the gravitational laws, we don't know where they are. And since we don't expect, major changes, but more like, local surface changing, everything relies on where are the slopes. And I think there are studies with the current shape model, but since it's very sensitive, I would say we don't know, and that's why we're going to go and check. And probably we'll still be surprised, as always.
Exactly. There's only one way to find out. Go there and look. Let's thank all the speakers again, please.
So it's time for a coffee break again. And I propose that we reconvene for the last session of today at 16 hours 10, so 10 minutes past 4 o'clock. Yeah, exactly. Welcome back. I think please take your seats. It's time to start again. So we have the last session of today, Apophis T-4 years. And I will hand right over to the session chair, Patrick Michel. Patrick, please.
Yeah, thank you. This is a session organized with Rick Binzel, who is online, and Brent Barbie. And I think Rick, at the end of the session, before the Q&A, will express some findings and recommendations from the Apophis T-4 workshop that took place in Tokyo about 2-3 weeks ago. So let's start. We have a busy schedule with Marina Brozovic that will tell us about the 3D shape model and spin state of Apophis.
Okay, hello everybody. So I guess since I'm the first talk over here, let's start with just a basic overview, what we know so far of Apophis. What you're seeing over here, this is radar-based shape model. From here we see that Apophis is an elongated object. This is something that we have known since the first light curves were obtained because it has a significant amplitude. And based on radar data, we established that this long axis is at least 450 meters in length and possibly longer. So we know it's in a tumbling spin state. So it has its fast period is about 30.6 hours. And by this, I mean, this is the period of the long axis precessing around the angular momentum vector, this marked in cayenne. And then you have on top of that the slow rotation period of 11 hours, and that is this rocking motion back and forth. If you're just looking where the green axis is doing, it's like banking like an airplane. You are hearing a period of 27 hours. That is also correct. It's just two different spin notations. It just basically means if you're looking in a long or short axis. Based on radar data, we established that Apophis is about 340 meters in diameter. This would be diameter of the equivalent sized sphere within plus minus 40, and that is 1 sigma. So what this means that we still have considerable size uncertainty in Apophis, and this is something that we may revise in the near future. So this is, the best radar data we collected was during the 2012 and 2013 apparition. At that point, the Apophis came within 1/10 of AU. So for Goldstone, something that is several hundred meters in size at 1/10 AU still is very distant, and it's the edge of our capability. And so we had, relatively low SNRs, but we were still able to get these delayed Doppler images, these fuzzy things in the first column that are not showing up that great. But so just radar images are very different than your optical images, but they carry a lot of information because you are directly seeing the object's size, hints of its shape, and the orientation of the echo that tells you about the spin state. It was relatively sparse data set over a period of 2 months. We got a snapshot of asteroid on about 11 days. And then here is the first published model in Spravitz et al. You see it here on your right. And first thing, our objective was to see the spin state and this shape, how well does it correspond to what we observed in radar. And the correspondence is very good with a small exception that we were noticing this pinch in radar data on certain dates. And that was our objective, why we ended up basically modifying this shape model in order to better match the radar images. And at the time, we also tweaked the spin state. So basically, it ended up being kind of slightly bifurcated, which would mean that this is kind of a contact binary. And we know that we need to update this model. So for example, we definitely need to combine both radar and the light curve data. And I can immediately tell you that the shape model needs to be a little bit longer than what we originally published with radar. So the aspect ratio needs to be adjusted in order to better match the light curves, because I'm showing you here just these are just the 3 weeks of optical light curves out of 4 months that were collected at that time. And what you can see, in black, these are Pravets et al. Shape model, which is perfectly matching the data. And then in blue is our radar model that, first of all, has a slightly tweaked spin state that, we basically should not have done. And so basically light curves are the ones that carry the most information regarding the spin state, and Joseph Durek, that is speaking right after me, is going to give you the update on that. So where we go from here is, we definitely want to combine we are combining radar and light curves, and we also we have data that we collected with radar in 2021 apparition. So at that time, Apophis was even further away than it was in 2012. It's even kind of fuzzier. It's supposed to be showing better than this. So it is enough to inform us about, again, the spin state. And one of the first kind of analysis we did is, can we bridge the gap of 9 years without any data? And the answer is yes, just, we can tweak the initial spin state and match the orientations in 2021, but that solution just based on radar data is not unique. And so we definitely, this is something you need the light curves because they have many months in both ends of apparition to perhaps get that spin state better. So I'm going to let Joseph speak about the spin. I'm going to, many times we get asked a matter of shape, is Apophis a contact binary? So they are very common in the near Earth population, larger than about 200 meters. In our radar sample, we have many dozens of objects. We see them all the time. And so I'm showing some examples. These are on the left side, you have Apophis showing that bifurcated echo, and then some examples of other contact binaries that are obtained at the similar SNR, as signal-to-noise ratios, and as similar resolutions. And we know these are, in fact, contact binaries because we have actually much better data sets, and I'm just showing you here something that does compare with Apophis SNRs and resolutions. So, they're very common in the Earth population. We are estimating anywhere between at least 15%, and there was a recent study by RC that is actually saying 30% of a near-Earth population is a contact binary, so that would mean that Apophis is just your very, very standard near-Earth asteroid. And so one thing that we really cannot tell is if it's bifurcated just a little bit, so this is almost no bifurcation, and equivalent light curve would be in Cayenne, and then if it's bifurcated a lot, you really can't tell difference. So light curves will not tell you they have no opinion of the amount of bifurcation. So they are very sensitive on the aspect ratio, and that is important, and that still needs to be implemented in the updated shape model. But only radar can basically tell you how bifurcated something is, and in this case, it's actually not easy to tell because when you are doing a fit, these couple of pixels that are showing a bifurcation are not contributing very much to your overall residuals. Your chi-square is really not very sensitive to these couple of frames that are showing bifurcation, but it's still the best that we can do, and we'll probably we definitely will look into this some more. And so, the bottom line is that, yes, Apophis is still bifurcated, and we are in the process of updating this shape model that is going to contain all the light curves and radar data that we collected to date. The shape is probably not going to be, it's still going to, the shape is still going to end up being ambiguous. To some extent, but we will probably be in a better situation to anticipate 2029 encounter. And now, I'm just going to stop there, and now we'll hear about the spin state. So.
We'll take questions afterwards, so we move to the next talk by Joseph Durek, Spin State of Apophis.
Thank you. Good afternoon. So I'm going to talk about the spin state of Apophis and the prediction of the orientation of Apophis for the close encounter in 2029. So Marina also covered several topics related to Apophis. And what's important in the context of my talk is that Apophis is in this excited rotation state that we can describe by two periods of rotation and precession, and that the orientation of Apophis in space is uniquely defined by three Euler angles that evolve in time. And if we have enough light curves, we can, in principle, uniquely reconstruct the spin state together with the convex shape model. And it has been done in past, so there are at least two shape models reconstructed from light curves, one from one radar model, but none of these models is precise enough in terms of their rotation parameters to be able to reliably predict the orientation for the encounter in 2029. So that was motivation for our work and our aim to collect every data that are available and try to uniquely reconstruct the spin state of Apophis. So we collected all available photometry. We ran our own photometric campaign using the Danish telescope at La Silla. We applied the light curve inversion method, and the result is, at least as far as I can say, that the current photometric data set is not complete enough to enable us to uniquely reconstruct the spin state of Apophis. However, the task of predicting the orientation for 2029 is possible, and I'm going to show you why. So if we take these two shape models, let's call them A and B, they both fit the photometric data sets perfectly, and we cannot say which one of them is correct. They differ slightly in their spin parameters. The difference is small, but they represent different local minima in parameter space. And then and their shapes are kind of similar. And then if you look at the evolution of Euler angles in 1 month in 2013, there are those two curves for the three angles. You can see that they are very similar, which means the models are oriented the same way in space in March 2013. And it's not surprising because that interval was covered by data. And the models were reconstructed from the data. And the same applies for March 2021. Again, the Euler angles are about the same, which means the orientation of these two models at that epoch is the same. And again, at the time we have the data from which the models were reconstructed. And so, but if we propagate the models into the future in April 2024 or 25, doesn't matter, then suddenly the orientation is different. So the Euler angles are completely different. And it means that we cannot say what's the orientation of Apophis in 2024 or today. But if we propagate the solutions to 2029, March or April, then suddenly, again, the Euler angles phase together and they become the same. And it's because the models, all models that fit the data were reconstructed from two operations that are 8 years apart. And we are interested in predicting the orientation, again, 8 years after 2021. So this coincidence means that we are able, at least to some extent, predict the orientation in 2029. So here is an example of how the model fits the data. The fit is quite good. There are no discrepancies. We can use the convex shape model and use 4 occultations that are available and scale the model to fit the occultations, so that the model is the blue silhouette, and the resulting equivalent size is slightly larger than what Marina got from radar, so now we have 400 meters. And the same size we got if you take the radar model and use the spin state from light curve, so again 400 meters of equivalent size. So now we can look what's going to happen during the close encounter due to Earth gravitational torque. So the right panel shows the distribution of 1,000 clones that represent uncertainty of that model A in the two periods parameter space. So the distribution is very tiny because the uncertainties are small. But still, every of these models, it comes with slightly different orientation in 2029. And the torques are so sensitive to orientation that the outcome, the post-encounter spin state that is represented by, again, two periods of rotation and precession, and those are the blue points on the left panel. So the originally very tiny distribution, it blows up and occupies now a very wide range of periods in the parameter space. And this is a very optimistic scenario because if we include Yorp effect that inevitably affects the spin state of a body of this size, and we take some realistic estimate of the Yorp strength, and the Yorp again slightly affects the spin, which means the orientation in 2029. So now the distribution of the blue points is much wider than without including this Yorp. So it means that we cannot say much about the outcome or the post-encounter spin states in terms of periods. We can say something about what's going to happen with the angular momentum vector, the direction of that vector. So again, the red points here are original. This is the original distribution, including uncertainty, and it's going to move during the torques about 10 degrees of arc away, it remains compact even with including Yorp. So the conclusion is that the current data set does not allow us to uniquely reconstruct the spin state. We can predict the orientation for the encounter. However, the torques are so sensitive to exact orientation that we cannot say much about what's going to happen after or during the encounter with the spin state. And what's important is that photometric data from 2029 won't help because, again, they are or will be obtained after 8 years. So to break the degeneracy, we need observations from 2027 and 28. Thank you.
Thank you, Joseph. Okay, thank you very much. We go for the next talk, showing already that we need to be there to understand this body. This will be by Diane Shears, modeling Apophis as a bilobate rubble pile body using contact dynamics.
Okay, thanks, Patrick. What this is work that we've been doing under support with NASA's Yorp-D program and also from a JPL SERP. And we're sort of embracing this idea that Apophis could be a contact binary and seeing how that changes predictions for what would happen during the flyby. So the existing predictions for the Apophis close approach, orbit will change, spin state will change, surface might change a bit, and the shape might change a small amount. And that's the least likely. What hasn't really been looked at yet is the response if Apophis is actually a contact binary body, where you have two components, which could be rubble piles in and of themselves, but which are mediated by just some regolith, because those different components would be more susceptible to torques acting across them. We've already seen that many bodies in the solar system are contact binaries, like Marina was stating before. And in fact, the Apophis radar model that we've been borrowing from her actually shows some bifurcation. So, and finally, we know that neck regions in these bifurcated bodies are more sensitive to stress variations than other areas across the body. So it seems reasonable to take a look at this. So our question is, how will Apophis respond if it's a contact binary with a neck? The mechanism or the simulation tool that we use is contact dynamics, which is a bit different than a lot of the other runs that have been done, which use a soft sphere approach. Here, we're actually modeling polygonal bodies as rigid bodies, and there's no interpenetration, so we believe it's a very realistic model for rubble piles. So the process that we go through, or that my student goes through, is we start with the radar shape model, we do a convex decomposition, and we have to make this, we apply a potentially spherical fit, and we come up with a few, two polyhedra that can contact each other. We can continue this process, and we've looked at 3 and 4 component models as well. We also, for reference, create a spherical model of 2 spheres resting on each other, just to have this as a sort of as a base model to do comparisons with. We also add a number of boulders about the bodies that will fill in some of this intercontact area, and then use this in a realistic flyby of the Earth in order to ascertain how the system responds to, or how these models respond to that. We change a couple different parameters during the flyby. We adjust the orientation of the body because we know that the changes that we see are extremely sensitive to the orientation. We also control sort of how much regolith is between the 2 bodies. We control this with this neck size ratio. Then we run the model by the Earth, controlling the orientation at closest approach. And what we're measuring is what we call an internal shift, which is how much the 2 lobes rotate relative to each other, and also tracking the motion of surface material or boulders relative to this body. So here's sort of a picture of several of these different models that we've used, and now we go through the Earth flyby, and depending on the orientation, you see that each one actually has a slightly different spin rate. We don't care so much about the spin rate. What we really care about are these internal degrees of freedom so that we can measure what happens. What we see is that for the nominal Apophis flyby, we see variations that tend to be consistent with the previous runs that people have made. There are some other specific situations that we look at, just like Patrick ran his simulation much closer to the Earth. We've run some of those too in order to actually understand how a contact binary body might deform if it actually had a closer Earth flyby. We selected some for further study, looking at friction parameters, tensile strength, and the like. And what we find consistently is for the unrealistic spherical bodies, we actually get large changes, but we sort of expect that. For the realistic polyhedron bodies, the changes in general are much smaller and consistent with some of the previous runs that have been made. One thing that we do find, which I think is interesting, is we can construct some artificial bodies that definitely fail when they come by the Earth, and we do that by messing with this neck ratio. If you look at the lower right, you see that we can crowd more or less material between the 2 components, and if you make that a bit too narrow, that's really an unstable system. And when you go through the close approach, it just collapses, which again is expected. It's not really a prediction, but it more is an exercise of our model to see how things vary. So we've submitted this paper to PSJ. We got the first reviews back, and they're pretty good. So it should be coming out soon. So I'm not going to go through all of the details that are represented here. And instead, I'll just jump to our takeaway. One of them is the bilobate polyhedral body in the spherical models, as you might expect, produce very different results. And this highlights the importance of the particle shapes, or the body and the lobe shapes. For the more realistic polyhedral bodies, the internal mass shift is quite small, tenths of a degree, hundredths of a degree, while the surface mass shift at the neck region occurs on a centimeter scale. Surface mass shift is also dominated by local morphology. If it's in a higher slope region, it tends to fail. If it's in a lower slope region, it tends not to. And we also found a stability threshold for the neck ratio, which below that, the system was actually quite unstable, and we wouldn't expect to find such a natural body in that sort of a configuration. So with that, thanks for your attention.
Thanks, Dan. Okay, thank you. So we move to the next talk, will be online by Joe DiMartini, the effect of irregular constituent particle shape and internal structure on the anticipated physical outcome of the Apophis close encounter. Joe, are you online?
Yes, I'm here. Can you hear me?
Yes. Okay, your slides are on the screen.
Perfect. Thank you very much. So, hi, everybody. I'm Joe DiMartini. I'm a PhD student at the University of Maryland, College Park, working under Professor Derek Richardson, and I'll be defending my thesis this summer. But today I'm going to talk to you guys about some of the soft sphere models that we've been doing with irregular particle shapes as well. So it's great that Dan went before this, because that covers most of my introduction. I don't need to go over this too much. Basically, Earth is going to come close to Apophis, and then the tidal forces are going to stretch and squeeze Apophis a little bit. And if we go to the next slide, then some of the anticipated outcomes are a potential small change in the bulk shape, or a deformation of the body, a likely change in the rotational state, as has been mentioned many times. And I'm also going to try to convince you that there may be some measurable seismic signals, some quaking induced in Apophis as a result of the tidal encounter. And what you're seeing on the right is a simulation of an impact into a rubble pile, and we can see the seismic wave propagate through there. Next slide, please. The way that we investigate this is with the parallel n-body gravity tree code pkdgrav. We calculate mutual gravity between spherical particles, and we resolve contacts between those particles with the soft sphere discrete element method. So in contrast to the contact dynamics method, which doesn't allow interpenetration, we do allow that interpenetration between our particles with a degree of interpenetration mediated by a restoring Hooke's law spring force, where that's the stiffness of that spring can mimic a material stiffness in our particles. We also have the ability to, back a slide, please, sorry. We also have the ability to glue our spherical particles together into these irregular shapes to deparameterize some things like rolling friction and sliding friction for particles moving past one another, and get into some of those real models, those real parameters of particle shape that Dan mentioned in the last talk. Next slide, please. So the next slide. The way that our simulations work is we generate 3 different packing distributions for our particles. The first on the right side here at the very top is the most dense possible packing distribution for monodispersed spheres. This is the model that we used in our 2019 publication. And we generate a sphere of particles and then carve out the most recent shape model for Apophis. We also do a random polydisperse packing, that's in the middle there, and a packing of our mixed aggregate shapes on the bottom, which get increasing porosity as we go from sort of top to bottom in this right side figure here. The random packing, for both of these other packings, we generate a cloud of particles and allow them to gravitationally collapse in on itself, generating the sphere that you see in the left side. And then we carve away particles to create the Apophis shape. In all of these simulations, we allow Apophis to settle in free space after it's been carved away under its bulk rotation period. Next slide, please. A little bit of detail about the geometry of the encounter and sort of how it works. You can see on the left a sort of 3D representation of the encounter, where the dashed line means that Apophis is below the Earth equator and the solid line means it's above the Earth equator. In our more recent models, we sort of rotate the orbit so that it occurs entirely in a two-dimensional plane. But for, you can see these little red and green markers that I've got on the left side plot, and these indicate the moments that you see on the right side diagram where the tidal forces of Apophis become dominant over any of the rotational forces, but still about an order of magnitude below local gravity. We call this the period of significant tidal influence. This is when Earth's tides are, like I said, more significant than most of the other forces acting on the body. Next slide, please. These are the results from our 2019 paper, just to give you a sense of what we measure in order to determine deformation in Apophis. The left side diagram shows this pretty well, where you have, this is essentially the distance, the separation between a pair of particles in Apophis, where the red, blue, and black lines indicate primary body axes and the other lines indicate random particle pairs throughout the body, just to show that this is happening everywhere. And in this case, you can see that the minor axis, the black line, is being stretched, it's in tension, and that the red and blue, the major and intermediate axes, are being compressed as we get towards close approach. And if we alter the spin state, as Joseph Dürek said, this is our major uncertainty at the time of encounter. So if we alter the encounter orientation, then we can see we can change our deformation by about an order of magnitude, but in this case, it's still on the order of hundreds of microns or millimeters for our most dense packing distribution. Next slide, please. So if we then do all of our different packing distributions and also models with only individual aggregate shapes, as I've shown on the right side here, then these are sort of our results. We have two models each for the hexagonal close pack and the random polydispersed packing. These are to match the individual particle density to the mixed aggregates case, or the bulk density of the rubble pile to the mixed aggregates case, which we're calling our control here. And we can see that in general, the increased porosity does seem to have an effect, but also the difference in particle size. So the size frequency distribution that we get from the random polydispersed packing plays a role as well here. Next slide. I don't want you to pay too much attention to the magnitude on the left axis of that histogram that I've shown there, because it is the strain, the degree of strain that we get, the magnitude of it, is strongly related to the Young's modulus, or the material stiffness of our particles. This was a plot on the right side here from our 2019 paper, where we show that if we increase our particle stiffness by an order of magnitude, then we decrease the strain that we measure by an order of magnitude as well. So for these models that I'm showing on the left side, we use an effective Young's modulus of about 10 kilopascals, but we don't know what the actual material strength of the regolith on Apophis will be, and that makes it difficult to come up with an exact change in axis length here. So next slide, please. I'm going to talk about some of the seismic source analysis in one of our higher resolution random polydispersed packing runs. If we look at the velocity profiles of particles in the co-rotating Apophis frame, we can find peaks, spikes in the velocity amplitudes, and sort of match these up to events. And essentially what all of these parameters that I've listed on the slide are saying is that we're looking for short, tall peaks with a minimum interval of 5 seconds between them, because we don't want to find reverberations from the same spike in velocity, right? So it's a little bit conservative, actually, the parameters that we've chosen. No, please go ahead to the next slide. It's a little bit conservative, the parameters that we've chosen, but in this model, what we find when we pull out all of those peaks is on the left side diagram here, I've got a histogram with a logarithmic axis here, the number of seismic events as a function of time during the encounter, where I've marked perigee and the beginning and ending of tidal influence. And we can see hundreds of events right around that period of the end of significant tidal influence, when Apophis is settling into its new rotational state. And on the right side diagram, what we're seeing is another histogram of the depth of an event as a fraction of body radius. And we see that it's actually mostly very shallow, these events. Most of them happen in the top 30 meters. That's about 2 particle diameters here. So going to the next slide, if we look at the autospectral density here, and don't ask me exactly what this is, but we convert this to frequency space, and the seismometers say, oh my goodness, or the seismologists say, oh my goodness, this is amazing. If we look at this, in comparison with the measurement capabilities of the seismometer that's being proposed for Ramses, we can see that it should be measurable in principle by their instrument. And the peak frequencies are in the range of between 0.5 and 1 hertz, which sits nicely within their instrument baseline. And our amplitudes are of order 10 to the minus 3 meters per second squared for accelerations, for a much more conservative Young's modulus, megapascal or tens of megapascals. A little bit of ongoing work that we've got here. We're also looking at differing internal structures. It's not an Apophis model over here because I'm having trouble with figuring out the neck region right now, but we're looking at a contact binary structure, a single core structure as well. And we're looking at real polyhedral shapes in addition to just our glued sphere aggregates. You can get more information about this in the poster by Adriana Daca. So this is just a quick review of my conclusions here. It will not Apophis will not deform very much, but we are likely to generate quakes or faults at the end of the period of significant tidal influence, and it should be measurable with current technology, which is good news if we're planning to put a seismometer on Ramses.
Thanks, Joe. Thanks a lot.
Thanks.
Thanks for this good news. And we move to the next talk. Estimating the effect of Apophis close approach on Earth satellites. That's scary.
Thanks a lot. So I'm Marta Ceccaroni. I'm a lecturer at Cranfield University. For those of you who might not know me, I was, well, proudly half of the orbit determination team of the NEO Coordination Center quite a few years ago in the prehistoric times together with Laura. Just right after we got rid of dinosaurs, pretty much. So today I'm talking to you about the effects of Apophis on geosatellites. So in talking about this good old friend, I thought to pick up facts that couldn't duplicate the other information that have been shared so far. So if you had a chance to take a look at the vineyard just outside the restaurant, pretty much looking down to the houses, to the very beautiful panorama there, you'll have a good idea of what is the diameter of Apophis. It weighs like 1/4 of Mount Everest down. Now, don't ask me how they estimated the weight of the Mount Everest, but that's pretty much, well, let's take it with a pinch of salt. It's been in risk list for about 15 years, well, for more than 15 years, and then it has been removed just in 2021 by a combination of observations, orbit determination predictions, and a little bit of black magic, I guess. So it will pass by the Earth on April 13th, 2029, 9:45, but it will pass by at a distance that is comparable with the distance of a geosatellite. So, yes. So, well, this is just the with reference to the moon. Okay, now, I thought it was interesting to see where is the guy today. So it's just on the other side of the solar system. Well, pretty much at the same distance from us to the sun. Okay, so in around the Earth, there are more than 10,000 active satellites, of which pretty much half, a bit more than half, are in the geozone. Providing us services like telecommunications, live streaming, and weather forecast. And these are the ones that account for the most revenue from space. Apophis will swing by the Earth, staying outside the georing, and then will arrive to a distance comparable with the geodistance, but outside the equatorial plane. It will reach its moid, well, let's call it moid, it's not really, but it will reach its kind of moid with the geo satellites 1 hour before the close approach with Earth, and it will swing by at 6,000 kilometers. Now, we are talking at the moment about active satellites, and therefore the effect of it will be accounted for in, with respect to an active satellite. So with no perturbation, like if no other perturbation are accounted, because we think about, well, the active satellite is actively station keeping. So the effect is pretty much nothing. What we can say is there is a very little effect on the rate ascension of the ascending nodes, and not much more than that. You might be more used to the figure of 8 that the geosatellites do in the sky, from which you can understand the east-west drift and the north-south drift. Well, this is the effect of Apophis with respect to the other major perturbations. You can see that it is several orders of magnitudes less than the smaller of the effects, which is solar radiation pressure. Therefore, the propagators that do not include the solar radiation pressure, the propagators for the two-line elements of the satellites, shall not worry too much about including Apophis, well, if solar radiation pressure is not included so far. This is the north-south drift, which is, well, pretty much the same. Well, the GEO is not only done by active satellites. There are more than 1,000 objects that are major than 1 meter, most of which are classified as large debris. And there are more than 1,000 estimated to be objects major than 10 centimeters in diameter. These images of 12 years ago, and I didn't dare searching for a newer one because I don't know the situation there, but I don't want to see it. So these orbits are kind of wobbling around. And therefore, in this case, we are thinking about the effect of Apophis on top of all the other perturbations. And with this, I mean the effects is going to be evaluated on a satellite that is perturbed by the major perturbation plus Apophis minus the dynamics that it would have with just the major perturbation without Apophis. So minimizing the distance, so the object that was minimizing the distance, not the MOID, but the actual distance, is this Meteosat 1, where there is a clear typo in the slide, which, well, it's this pretty big bloke. And the effect on it, as you can see, starts to be a bit more interesting because, well, it becomes of the order of millimeters after a few months. So the thing is, distance is not the only effect. So yes, these are the drifts. So they become of millimeters after a couple of months. Distance is not the only parameter that affects the close approach. Geometry is even more important, together with also relative velocity. And parallel close approaches, which is not the case of Meteosat 1, which was pretty perpendicular, parallel close approaches might affect even more the orbits. So searching quickly, well, filtering quickly the debris by the geometry of the orbit, we can find other interesting cases like Intelsat 603, for which the mass this time is in kilograms, and, well, is a pretty big guy. And you can see that the effect after 6 months becomes of the order of 10 meters. So, in conclusions, the effect on an active satellite, it's much less than solar radiation pressure. So it has a bit, well, the main disturbance being on the rate ascension of the ascending node. The delta V for the station keeping of our active satellite will be totally irrelevant. However, for the collision avoidance, for the collision avoidance forecast, there could be peculiar debris geometry that might have to be taken into account. In thanking you before the gong, I will, I'm telling you that me and Marco Fenucci are the guest editors of Advances in Asteroid Dynamics, and we will be honored to have one of your contribution in our issue. Thanks a lot.
Thank you. Thank you very much. So we go to the next talk by James Bauer, Near Future Plans for I-1 Apophis Observing Campaigns.
Okay. I just want to start out by pointing out that this is Dr. Vishnu Reddy's talk. I'm just giving it in his stead because he was not able to attend this conference. And we want to introduce you to the plans for the International Asteroid Warning Network's Apophis observing campaigns over the next few years. Just to review, the International Asteroid Warning Network, or IWAN, is a collaboration of organizations and individuals to discover, characterize, and monitor potentially hazardous and NEO objects. And then we currently have 71 signatories from 29 countries. We frequently run observing campaigns to test the operational readiness of the community. There have been, since 2017, 6 campaigns in the past involving hundreds of scientists. And we've had a lot of lessons learned, including topics including astrometry, timing, astrometric timing, and characterization and modeling of potential impacts. And we've seen it yield benefits in events like the discovery of 2024 YR4. And there are the organization structure for these campaigns is with Dr. Kelly Fast, the NASA, as our NASA headquarters point of contact, and also the IWAN coordination officer and the NASA acting planetary defense officer. The IWAN campaign coordinator is Dr. Vishnu Reddy, and the observations working group lead is Dr. Christina Thomas at Northern Arizona University, NAU. So in the 2027 and 2028, the observations are going to focus more or less on physical characterization. We saw a lot of good reasons for that in previous talks. Opportunities are restricted to large large aperture ground-based observatories or space-based telescopes due to the magnitude range, the limiting magnitude, and the observing geometries. So IWAN will be coordinating, the idea is IWAN will be coordinating these telescopes and endorsing these efforts, but the scientists and the investigators will publish their own results for these campaigns. So likely, 2027 will likely mostly focus on light curves, again, owing to the magnitude of Apophis at that time, during that window. And then in 2028, it'll be a little brighter and accessible to visible wavelength spectroscopy. And so that will also be a theme during that observing window. We saw some good reasons for the rotation state. It is a non-principal axis rotator, and the idea would be to organize and observe the object on cadences for about 2 hours, on cadences of about 2 hours, and coordinated effort would really benefit the light curve analysis. Okay. Of course, it's known already that it most closely resembles LL chondrite spectral type, but there is compelling evidence put forth by Rick Binzel and collaborators for a correlation between low minimum orbit, intersect distance, and spectral slope. So suggesting possible tidal stresses that can lead to asteroid resurfacing or asteroid surface spectral changes. Apophis will also be visible for 4 windows with Hubble, 3 of them overlapping during the proposed IWAN observing campaigns, and then a post-encounter which we also endorse. The post-encounter window opens June 16th, post-close approach. So it's also viewable with JWST at three times in 2028, and then later just immediate pre-encounter, close approach, and then after close approach. So the 2029 campaign will be more conventional, more in line with previous IWAN campaigns. It'll be open to and accessible to more to a broader range of telescope diameters, smaller telescopes, of course, and it'll be aligned towards International Year of Planetary Defense in getting out the message, and also potentially folding in other consequences, looking at Apophis as a newly discovered NEA, and involving modelers for potential impact scenarios and as exercises, and IWAN, subsequent IWAN campaign focusing on post-close approach observations. So we welcome better coordination with the PDC exercises, if there is one to be planned around the Apophis encounter, and inputs from the spacecraft rendezvous missions. And with a minute to spare, that's all I have. Thank you.
Thank you. Thank you, James. Thank you. Okay, so we can move to the next talk by Nathan Golovich, Rapid Apophis Characterization with 2 satellites, RASCATS, Residual Mission Benefit for NEO Tracking and Characterization.
Hello, everyone. I'm Nathan Golovich from Lawrence Livermore National Laboratory. Just a little background on, so I'm going to kind of give 2 halves to this talk. The first half is just a quick overview of what this mission concept is, and the second is looking at what you can do with these satellites after Apophis flies by. So we got started in this game after the Vienna PDC conference when Matt Daniels reached out to us looking for a much cheaper option for a Apophis mission. And so we have some experience in rapid space capabilities, so this is what we came up with. The idea for us was to think about working with commercial space partners who build and launch small satellites, and we would provide the payload. The idea was to limit costs, to look for rideshare opportunities to Earth orbits that would have flyby potential to Apophis. And so we would be looking to put wide field of view telescopes on these to do imaging during these high-speed flybys from something like a GTO or a SSTO, these transfer orbits that you can get to from rideshares. The basic mission we'd want to do on the right is showing the geometry of a rapid flyby. So essentially you just look downstream with this 25 centimeter telescope as the asteroid flies essentially into your face and zips past your head. It'll get much bigger, and at some point you won't be able to slew anymore, but by that point the asteroid will only be tens of kilometers away. And so with this aperture you could get pretty resolved imagery of the surface of just the sunlit side, which is a nice detail of the orbit dynamics. The speeds would be about 8 to 10 kilometers per second, depending on the orbits that we choose. The other thing that we want to do is get an image of the asteroid transiting Earth. This would just be for public engagement. I think this would be in the pantheon of images of Earth if something like this were able to happen. The beginning of this was to talk about the low cost. Possibly the lowest cost option would be to look at working with some of the companies that are doing very frequent geo rideshare programs. We've been working with Impulse Space, which is a company that builds a spacecraft called the Mira bus. It's roughly an ESPA class bus. We've talked to them about hosting a telescope on a geo mission that they have in the next couple of years, and it would essentially just sit in geo until 2029. And at the end of life, Mira has enough delta V such that it can make a 350 meter per second maneuver and raise its altitude about 11,000 kilometers to intercept Apophis as it transits the equatorial plane. And this would be about 2 hours before perigee. So this would be before the largest of the tidal forces take hold. And so this would be a relatively pristine view of Apophis before the tidal forces potentially make some surface changes. Here's a, hit next, it might, yeah. So here's some of the orbit options we've looked at. The rideshare with the Mira bus raised 11,000 kilometers is the green orbit. The rest of these are various SSTO or GTO transfer orbits that give you different viewing conditions. The one that allows the look down on Earth would be the pink one. Okay, so that's just a quick overview of that mission. It's just a mission concept. We're still exploring this, but without significant funding or something coming from NASA or another agency. Possibly only this rideshare with GEO is likely. So now I'm going to transition to what you can do with these if you did happen to have multiple satellites in the GEO vicinity for other purposes. So this timeline in 2029 will be a time when we're discovering more near-Earth objects than ever before. So 2029 is when we'll have both NEOSurveyor and the Rubin Observatory detecting much smaller and more numerous asteroids. And so it's interesting to think about what you can do with a couple of satellites in GEO during this time. This plot came from the US National Preparedness Strategy for Planetary Defense that Matt Daniels helped put together. So what I did was took the full Grand Vic catalog of about 800,000 asteroids below H mag of 25 and simulated them through the Rubin Operations Simulator to estimate how often Rubin would detect them and issue an alert. And then we took those orbits and then propagated them forward in time and assessed the ability to track them with these GEO-type orbits. Here are some histograms of the detections. So the full Grand Vic catalog is the blue histogram, and then various, so the orange histogram is anything that was observed at least once with Rubin. The green are the ones that were actually issued an alert based on the alert requirements for the prompt alert stream from Rubin. And then the red ones are the ones that would be bright enough to observe with these 25-centimeter telescopes in the GEO vicinity. And you can see over the course of the 10-year Rubin survey, there's very many alerts across a range of apparent magnitudes. For something like this Apophis mission concept that I described earlier, there would be roughly a one-year lifetime of this mission, and in this time there'd be thousands of asteroids that were detected by Rubin and would be available for follow-up with a bistatic observation capability from if we were able to have multiple of these spacecraft. So to assess their ability to improve the tracking or the orbit estimation of these objects, I took the alerted asteroids, propagated them forward for 100,000 days to see how close they come to Earth in the future. And so I circled one of them in the bottom. This is just a case study to look at what something like this could do. So to do this, I basically I simulated some additional observations with these satellites and did a Fisher information matrix analysis to estimate the improvement in the orbital estimation based on the Rubin alert plus the extra data from the GEO spacecraft. Here's the simulated, so the lower right figure shows the crosses are from the Rubin alert, and then the additional data comes from either ground or GEO, and I'm going to do a comparison of what you get for adding extra observations from either a single ground-based observatory or a bistatic observation with these two GEO spacecraft. So here is the orbital estimate. So the black points this is a position on the sky propagating 10 days forward from the alert with the additional data from the ground showing in the blue, and the orange is what you gain from having a bistatic observation, getting that extra parallax from the diameter of the GeoBelt. And then the corner plot shows the orbital elements improved. But importantly, going all the way forward, decades from that detection, you can estimate the minimum approach of this object much more precisely with the addition of this binocular GEO follow-up as opposed to ground-based follow-up. And just kind of to close, the last thing I wanted to say is just, this is, I showed that plot of the expected completeness of the PHA or the NEO population going forward in time with the addition of these surveys. There's going to be a ton of these objects to track, and here's the full 800,000 objects from the Grand Vic catalog, simulated forward in time for hundreds of years, And we're going to, it's very likely that Rubin or NeoSurveyor or any of these other surveys that are coming online will be detecting more objects like WIRE4. Interestingly, there's no objects in the Grand Vic catalog that impact Earth in the next couple hundred years, but there are a number that come within the geobelt, and this is complete down to age of 25. So having more capability to do rapid follow-up of these objects is a need for the future. That's all I have. Thanks.
Thank you. Thank you very much. So we move to the next talk, maybe online, by Fazle Siddique, leveraging circumlunar orbits for the upcoming Apophis encounter. Oh no, you're okay.
Hi, I'm Justin Atchison. I work with Fazle, Juan, Amanda, and Jackson, and they asked me to present since they couldn't attend here. So very similar to the prior talk, we were tasked with the question, what is the most accessible or the lowest cost way to get to Apophis? And so I have the slides here. We proposed that it would be as a cislunar rideshare as opposed to a geo-rideshare. I think they both have merit, but and our proposal was, or this team's proposal is that there's roughly 3 to 5 CLIPS launches planned generally per year, and in the prior CLIPS launch that happened a few months ago, there were 3 rideshares, so there's some precedent for riding to the moon. And then the premise is once you get to the moon, then you could enter a staging orbit or to loiter until Apophis comes close by. The constraint that we were provided, it sounds like it was slightly different than the prior presenter, is that the encounter needed to happen 30 Earth radii away prior to the flyby, with the reference that 16 Earth radii is where surface mobilization could begin. So that corresponds to about 8 hours prior to the Earth encounter, and so you lose the ability to encounter near the equatorial plane. You're now well out of the plane. You're out of the ecliptic plane, the equatorial plane, and the Earth-Moon plane, and that ends up driving a lot of the trajectory choices. So the approach that the team took was to say we're going to start out with a mission that's going to the moon, and that mission that's going to the moon is either going to stop and enter orbit or do what's called a ballistic lunar transfer, where they'll come back to the moon a few months later. And then you can either enter a staging orbit, where you're going to just loiter for many months, because maybe if you're a rideshare, you're launching a year in advance of the encounter or 6 months in advance, you don't know, so you enter a staging orbit. Or if you're up against the timeline, as we all know, sometimes missions slip the launch window. In the event that that happens, then you could launch maybe as late as a few months before the encounter and go directly to the flyby. That's that direct transfer. The plots I'm about to show are all in the circular restricted 3-body problem. And the quick summary is that this is a frame that rotates with the moon. So it's a synodic frame, and there are the 5 Lagrange points you're probably familiar with. And the upshot is that you get really pretty plots like this, where what might typically look like an ellipse looks like these very unique shapes. And what we're showing here are 3 orbit families that all cross the Apophis distance, that 30 RE from the Earth, across Apophis's orbit. The first one is a 2-to-1 resonant orbit, and you see there's different colors. Each line is a particular orbit within this 2-to-1 resonant orbit family, where the difference is the Jacobi constant. A 3-to-1, and then this L3 Lyapunov orbits that where you're orbiting the L3 point. And this was interesting because there aren't a lot of orbits that are usually use L3, so that was something that was interesting to come out of this. For that particular case, the L3 one, it turned out that it was actually a better choice to use a Lissajous orbit. So we've gone Lagrange point, Lyapunov, now we're at Lissajous quasi-periodic orbit, because it has the property that it evolves out of the plane. And so in that plot you see on the top right, you're seeing different families of these quasi-periodic Lissajous orbits that evolve up and down. And so from that, they selected one in red, you see there, that crosses that 30 RE point of the Apophis orbit. Okay, so we've got 3 candidate families, and from each of these families, they selected one that satisfied the criteria of crossing Apophis and was stable for, in this case, they looked at 13 months with the idea that the time it would take to design a spacecraft and get it as a rideshare could push us up towards the 2027, 2028 timeline. So this is at least 13 months, it could extend longer. And you see those on the top right, you see the flyby speeds we're looking at from 5 to 7 kilometers per second. And so these are all the staging orbits, and the idea is that you can launch any time and get into one of these staging orbits at any point within these orbits, and you know that eventually you're going to get your flyby of Apophis. So the next question is, how much does it cost to get into these different orbits? And so they focused on 2 examples. The first is that 3-to-1, the green one. In this case, there's a 104-day transfer, so 3.5 months, and you can get there for about 250 meters per second. And the plot is maybe a little bit tricky to look at, but you launch from that center 0 point Earth, you do 1 flyby of the moon, it kicks you way out, so you're now in this very perturbed by the sun region. I would estimate you're maybe like 5 lunar distances away, and you complete a few revs of that, and then you come back in for a second lunar flyby that kicks you in to a place where you can insert into the green orbit there. And the second example is for that Lissajous orbit. In this case, you only need 1 Earth flyby, that original one. So this looks more like what would typically be considered a ballistic lunar transfer, where you kick out and you go out to this same large distance, and you come back in, and then you just enter directly into your staging orbit. In this case, it was only 160 meters per second, and it took 2 months. So then that was if you want to launch early. The second question was, if you don't get the advantage of launching early, what's the latest you could tolerate? And so we saw it maybe 10 weeks before the encounter is a pretty sporty amount of time to have a spacecraft launch and check out and then do something. And so up against the end of January, they were able to find solutions. In this case, there's no staging orbit. It's just you do 1 flyby of the moon. It kicks you out into, again, what looks like a ballistic lunar transfer, and then you come back, in this case, come back and do a second flyby of the moon, and then do your Apophis encounter. And so the top right plot shows the delta V, which is a little bit hard to see, but that lowest line is 50 meters per second. And so about half the month you can achieve for less than 50 meters per second. Some of them take upwards of 200 meters per second. And the coloration of the different lines, each of those is a different trajectory. The coloration corresponds to red, means a lot of delta V required, and blue means less than 50 roughly. And it's a little bit confusing because that middle plot switches from the Earth-Moon to the Sun-Earth rotating frame, and that was just because it's already a ball of yarn, but if you don't do that, it looks even more complicated, and you can see the moon's orbit there in white as a circle. So the conclusion is that this did end up being what we would consider a viable approach to reach Apophis, and if you could get on one of these cislunar ride shares, then there are lots of options. There were at least 3 different families that they looked at here that were able to achieve it with very long time periods. So it took time out of the equation, which is one of the toughest parts of being a ride share when you don't have control over the schedule. They also showed that you could go directly there if you are up against the schedule window. And the final thought is that this could be extended to other asteroids. You saw that it kicks you out relatively far, so it doesn't have to be as close an approach as Apophis, but in any asteroid that was coming in the vicinity of the Earth-Moon system could potentially be reached this way as a low-cost mission. For that, I appreciate your time and look forward to questions. Thank you.
Okay, thank you very much. We move to the next talk by Carol Raymond, the Caltech mission to characterize Apophis.
Okay. You didn't see my title slide, but you can look at the abstract to see my co-authors. So I don't really need to talk to this group about why Apophis. I just want to make one point on this slide, and that's that to maximize this opportunity, we would like pre- and post-encounter observations. So while Apophis Apex is going to give us a fantastic data set, we want to make sure to get the before picture. So that's really what motivated us to start studying a rendezvous concept to arrive at Apophis, launching in early 2028, and rendezvous, and then escort Apophis through its Earth closest approach, and then do a biostatic radar experiment after closest approach. So I'm going to hit some of the highlights of this, and then the next talk by Adriana Daca is going to go into some more detail. So we started with asking the questions of what could we do with this opportunity? And obviously, we've been talking about this all day, so I don't want to belabor the point, but obviously it's a great opportunity to understand the interior structure of a rubble pile asteroid, which we know very little about. Arguably, maybe what we think we know is all wrong. It gives us an opportunity to understand formation and evolution of these bodies, but also how it would respond to a mitigation attempt, and then how do close planetary flybys affect these bodies, just in the general case of resurfacing, but also in terms of an impulsive event like a deflection. So to do that, we want to map the shape, the bulk density, the porosity. We want to understand the interior structure in terms of block sizes, composition, the porosity, and then we also hope to get some handle on the cohesive strength, as well as determining the changes, the dynamics of the spin state, and the changes in the body itself. So we expect that the changes will be slope failures on slopes that reach the angle of repose due to the changing rotation state. These would be small effects, as have been modeled by many people. So that drives us to our observational requirements. So those are the key measurements we're making with our imager to do global shape. We have the bistatic radar to do both monostatic and bistatic, and we'll be imaging to drive shape model, as well as look at the geology, the geomorphology, and the changes. So now, this is an eye chart, but it demonstrates what I just told you, which was we derived quantitative measurement requirements from those objectives and from the existing knowledge to drive us to imaging resolution of less than 10 centimeters per pixel, and also the gravity field to degree in order 4, based on the Doppler tracking, and the intersatellite links, which will be operating between the 3 spacecraft. So this is just an attempt to highlight that this mission can complement both APEX and Ramses. It's very similar to Ramses, as we've seen from the previous presentation. Ramses is doing monostatic radar with a single CubeSat. Our mission would do bistatic radar with 2 CubeSats, and by coordinating those measurements, we would have a much richer data set, much better coverage of the interior structure, and by combining those data sets, we get a synergistic result. In addition, though, the bistatic gives us this direct measurement of permittivity, from which we derive the composition and the porosity. So this is kind of the unique thing that we're going to deliver. And then you can see all the other things that are common to the 3 missions, and yet will, as I said, increase the value of all the data sets. So what does the mission look like right now? It's a collaboration with Caltech, JPL, and Rocket Lab. The mothership that we're planning is a 3rd copy of the Escapade spacecraft. The first 2 will be launched to Mars later, we hope, this year. And it carries the cameras, the intersatellite link, and the 2 CubeSats. The 2 CubeSats are equipped with bistatic radar. It's nearly identical, as Alon already described, to the Jura radar, and also it's in the Ramses version. We launch early in 2028. We arrive in February 29, and we'll deploy our CubeSats after closest approach. I think that's on the next slide. And we will have about 2 months to do the bistatic radar experiment before OSIRIS APEX will be getting into its proximal orbits. And I think this is my last slide. So to summarize, the purpose of our mission is really to monitor the changes resulting from the closest approach by getting the before picture probing the interior structure where we don't expect changes to occur, but that's the important information that will allow us to use these data to better inform modeling of how deflection might work for an object like this. We will be working together with the other missions to make sure that we're as complementary as possible. The current status is that we have key contracts in place for all the pieces of the mission. Our team has been funded through Phase A. We've just completed our first design review, so we're doing detailed design, heading towards a PDR at the end of the year. And right now we're in a position where we are near we have identified and are working on the funding source for the mission, and we will find out fairly soon if that is going to take place, or that's going to be available, and then we will be ready to go. So I'm really looking forward to this realization of all of these amazing missions and this amazing opportunity to go to Apophis, and thanks for your time.
Thank you, Carol. I give the floor to the next talk on the same mission by Adriana Daca.
Hello. So I'll be expanding a little bit upon Carol's presentation and speaking more about the Caltech mission to Apophis. This is not my slides. Can you pull up my slides, please? Okay. Well, one moment, please. But anyway, so I'll just talk about the presentation while we wait for that. Yeah, I'll be speaking more about the science objectives and how these relate to planetary defense and our mission in more detail, if they can find my slides. Notes. Oh, I think I know what happened.
Should come soon.
Okay, here they are. Thank you. All right. So you'll recognize this slide from Carol's presentation. And as I mentioned, I'll be discussing in more detail the goals, objectives, and key measurements of the mission. So we have our 2 CubeSats that will be performing bistatic radar, and this will be done in the modes shown at the upper right corner of the slide. So we have we're going to be doing both monostatic and bistatic, and for bistatic measurements, we have transmission through the asteroid, and we can also do bistatic reflection measurements. And we will learn about the block and void size distributions at sizes greater than 10 meters. We'll constrain the bulk porosity with global average permittivity measurements. We will also assess the heterogeneity of the material on scale of hundreds of meters, and we'll be able to determine the structure of the lobes of the object if it is bilobed. And then just on the lower right part of the slide, you can see a 2D dielectric permittivity model that was reconstructed using various radar sampling geometries, and you can see that the one at the very lower right of the slide, that is the full bistatic sampling geometry, and that provides the best reconstruction of the object. Okay, and so then for the surface imagery, the main thing that we want to see is changes due to the Earth close approach. So as we've seen throughout this session, multiple studies have predicted that there might be some local resurfacing on Apophis, but it's predicted to be quite subtle, so we do need to have good resolution imagery. So we're aiming for less than 10 or around 10 centimeters per pixel. Hopefully we'll have better resolution on some certain areas where we think there's a higher likelihood of resurfacing based on slopes from the updated shape model that we'll get. And that brings us to also, we'll be developing a detailed shape model before and hopefully also after ECA, depending on the mission constraints, with a height accuracy of about 0.5 meter. Also, we will be obtaining albedo and spectral slope information in the range of 400 to 1,000 nanometers, also at 10 centimeters per pixel. So this will allow us to potentially detect any albedo changes as a result of the resurfacing as well as unspace weathered material becomes uncovered. And we'll be also, of course, observing the spin state changes due to the Earth flyby. Now, one interesting thing that might happen is that small deformations in the body might actually cause spin changes beyond what is expected for the rigid body case. And there were some simulations that Toshi had done recently that he's preparing a manuscript on right now. So those are the lower right plots. So that's showing the change in the axis, the rotation axis over time compared to the rigid body case. So it can actually diverge up to 3 degrees from the rigid body case after about 30 hours after ECA, depending on the encounter orientation. And then the very right corner plot is just showing that projected onto the distribution of the spin axis orientation. Okay. Then for the interior structure, as we've seen and talked about this whole session, we have very little knowledge of the interior structure of Apophis. So another way that we can constrain this is through gravity science. So using interior structure models that use radar information, gravity field, and inferences from the rotation state change, we can learn more about the interior and changes resulting from the Earth flyby. So for this, we need to get an estimate of the mass to derive the bulk density, bulk porosity, and we can use higher order gravity field, so up around degree 4 would be good for this to determine the mass distribution. And again, we'll have to get the global shape model with a height accuracy of about 0.5 meter and the spin state changes during the Earth flyby. So how does this all connect to planetary defense? So we're going to rendezvous with Apophis about 2 months before the ECA. So we can think of this as like a quick reconnaissance mission practice to see how planetary science techniques can help to learn about information that we need for planetary defense. So for the first couple months of the mission, we're going to be characterizing the mass, shape, and spin of the object. We'll be developing a global shape model, and then during the close approach and after, we'll be doing the imaging to characterize how the object is resurfaced. And then after the Earth closest approach, we'll be deploying the CubeSats and starting with the interior characterization measurements. So for planetary defense, 4 key parameters have been identified by the NEOWARP working group: the mass, orbit, composition, and strength. And the Caltech mission will help us to characterize all of these for Apophis. And yeah, so I guess I still have a little bit of time. So yeah, the current knowledge of Apophis's mass is very, there's a very wide range of estimates for the mass. We don't really know. So our mission will help to constrain that, as well as the internal mass distribution. The orbit is pretty well known, but we'll be able to track that, enhance our knowledge of it, and tracking the spin state changes. The surface composition we know is likely an SQ type, but with the bistatic radar measurements, we'll be able to learn more about the internal composition and if that's different than the surface composition. And same for the strength, we don't really know. We think it's a suspected rubble pile body, but this mission will help to confirm that. And this, of course, ties into deflection planning, understanding what is the beta parameter and how it would react to a deflection attempt, and informing planetary defense models. We can also observe boulder shapes, and to learn more about the strength of those, like there was a recent paper about that, looking at different rubble pile asteroids, boulder shapes, and deriving the friction angle from that. So we could do something similar. And also we could look at the surface material movement to constrain the cohesion of the surface material based on how it moves. Okay. So as I stated, so we need to have an understanding of both surface and interior properties of asteroids to understand how we can deflect them and plan for planetary defense. And Caltech is leading a mission that aims to do just that for Apophis. And so we're going to characterize both the interior and the surface. And here we discussed how the current knowledge of Apophis flows down to mission requirements. Check out my poster later tonight. And we also have a review paper coming out soon, so look out for that. Thank you.
Thank you, and sorry for the presentation problem. So we move to the next talk. It's about the TERP Raptor mission concept development by Adrian Rudolph. Thank you.
Can I get my slides, please? Awesome, thank you. Okay, hello everyone. My name is Adrian Rudolph. I'm a PhD student at the University of Maryland. And if you have not yet heard of TERP Raptor, today is your lucky day. So I'm going to gloss over this. Apophis, big rock coming at us, is going to miss us, thankfully. Credible opportunity for scientific investigation, but what we really want to know is who will be there to have eyes on Apophis, and hopefully that'll be TERP Raptor. So our questions, our scientific questions, were derived from the 2023 NASM Decadal Survey and the SBAG Apophis Specific Action Team report. So our main two questions are, firstly, how has the collisional and dynamical evolution of Apophis affected its surface and structural characteristics? So we want to understand more about its size and shape, weathering history, and cratering history. As well, how will its close encounter with Earth affect the movement of surface material on the asteroid? So we want to understand the nature of tidal resurfacing, movement of regolith, boulder displacement, etc. Okay, so this is TERP Raptor, our spacecraft design. TERP Raptor is a 12U CubeSat designed for a flyby of Apophis during its closest encounter. On board, we will have two imagers. The first one is the Mantis imager, which is an optical visible imager. The other one is Orion, which will be used for near-infrared imagery. And then additionally on board, we will also house a high-frequency receiver antenna tuned to 9.6 megahertz, which I'll talk more about later. Our lifetime is expected to be roughly 1 year, or at least 1 year. And then our limitations are in delta V and radiation shielding. And as of now, we have calculated a mission cost of $3.4 million, which is before labor. And then we have also calculated, which we're pretty proud of, a nominal cost per image, which is 20 times lower than that of typical asteroid flyby missions. So here is our concept of operations. On the left side, This is a large overview. So after launch and deployment of TURP Raptor, it will undergo commissioning, and then we will perform a perigee raise maneuver in order to get on an intercept course with Apophis. After some final phasing maneuvers, we will fly by Apophis at roughly 10 kilometers, gathering images and data, and we will downlink that back to Earth. And then on the right side is just a more zoomed in version of the actual flyby itself. Okay, so I mentioned earlier that we wanted to house a high-frequency receiver antenna on board. This would be provided by the University of Alaska Fairbanks and the Naval Research Lab. So for those of you that don't know what HARP is, it is the High Frequency Active Auroral Research Program in Alaska. They have a massive bistatic transmitter on the ground, and what they want to do with us is illuminate Apophis at 9.6 megahertz, and then we would receive that reflected signal on board TURP Raptor and provide that data back to them so we can get awesome measurements on the interior of Apophis. So we have a few considerations for our orbit and rideshare. So standard launch providers don't go directly to Apophis's hyperbola. So these are a few cases that we have come up with. So design reference case 1 would be a transfer to a standard geosynchronous transfer orbit with a substantial delta V perigee raise. Design reference case 2 is a little bit different. It's a lot more highly inclined. And then design reference case 3 is more retrograde, so we would do a swing by of the moon. Now this is really nice because it would put us at our lowest relative velocity to Apophis, but unfortunately require a very large amount of delta V to get into such an orbit. We have been in talks with Blue Origin and a couple of other smaller launch providers and are still considering other options. So I think we were using a design reference case 1 for these calculations. So with a relatively high relative flyby velocity of Apophis, we would require high resolution imagery, a high frame rate, and some kind of snapshot or global shutter imagers on board, which I mentioned earlier, Mantis and Orion. We would fly within 10 kilometers of the asteroid to suit our scientific needs. And we looked at whether or not we would be able to slew this close to the asteroid, and we found out that this would probably break apart our spacecraft. So we have decided to fly by at a fixed pointing angle of roughly 40 degrees. And this configuration, as we have run the calculations, does optimize our number of images collected to be roughly 15. I would put our success criteria at 1 image. Some of you might even say getting on the launch pad would be success. Our resolution would be 0.5 meters per pixel, and as I mentioned before, we would have a much lower cost per image than most other flyby missions of asteroids. So yeah, ready or not, Apophis is coming. Time is running out to develop missions, and this would be an incredible opportunity for public engagement, planetary science, and planetary defense, obviously, that's why we're all here. And to study a giant rock in our own backyard, that's just crazy. And it would also give a bunch of grad students an incredible opportunity to do something real. So TURP Raptor is currently in the process of gathering funds. We have applied to the Maryland Space Grant Consortium in the US. We have a couple of verbal back and forth things going on at the moment, but we hope to be there when Apophis comes by and makes its historic close encounter. So go TURP Raptor, and I still have a little bit of time left, so I just want to recognize that I have 2 of my other team members here, Sean and Chintan, if you guys want to wave. The rest of our team couldn't make it, but they have worked so incredibly hard, and we really want to be there when Apophis comes by. So with that, I thank you for your attention and your time.
Thank you. So we go to the next talk by Shogo Tachibana online, I guess. Low energy multi-impact experiments on
Patrick.
Apophis. Hey, konnichiwa, Shogo. Okay,
Yes, can you
yes,
can you hear me?
We hear you very well, and your slides are on the screen.
Okay, thank you, Patrick. I'm Shogo Tachibana from the University of Tokyo. I'll be talking about possible low-energy multi-impact experiments on Apophis to study its surface properties. Next slide, please. Near-Earth objects have been target bodies of sample return missions, and we now have samples returned from S-type asteroid Itokawa, C-type asteroid Ryugu, and B-type asteroid Bennu. NEOs are potentially hazardous bodies, as well as potentially useful bodies for space resource utilization. From all perspectives, it is essential to understand what materials NEOs are composed of, what their surface conditions are, and what their structures are. So here we propose low-energy multi-impact experiments to investigate surface properties of Apophis after its close encounter with Earth. Next, please. So why impact experiments? We know that impact experiments have huge impacts and provide huge insights. For example, NASA's Deep Impact mission targeted Comet Tempel 1 with an impactor, allowing us to observe the comet's interior. JAXA's Hayabusa 2 performed a small carry-on impact experiment on asteroid Ryugu, creating an artificial, about 15-meter-sized crater. And this helped us understand the physical properties of Ryugu's surface and allowed us to sample subsurface materials. More recently, the DART mission impacted Dimorphos and successfully changed its orbit. Next, please. Hayabusa 2 also conducted lower energy impact experiments on Ryugu during its 2 touchdown operations for sample collection. At each touchdown, the spacecraft fired a 5-gram projectile at an impact velocity of 300 meters per second, delivering about 225 joules of kinetic energy. This impact likely created a small crater about 15 to 20 centimeters in diameter. However, unfortunately, the spacecraft was unable to observe the crater directly, but we believe the impact successfully excavated surface materials. Next, please. Because we now have samples. And Hayabusa 2 collected about 3 grams and 2 grams of materials from 2 surface locations. These were the first return samples from a C-type asteroid, and they were found to be very similar to Ci group chondrites, a very rare type of meteorites on Earth, yet chemically representative of the solar system. This combination of rarity in the meteorite collection and chemical representativeness is likely due to the fragile nature of the C-type asteroid material, which prevents it from surviving the atmospheric entry. So understanding such material properties is also essential for planetary defense. Next, please. So here we propose conducting low-energy multi-impact experiments on Apophis from a distance of several hundred meters to 1 kilometer above the surface using 10 to 20 projectiles with impact velocities below 150 meters per second. The corresponding kinetic energy would be about half to a quarter of that of Hayabusa 2's sampling impacts. These experiments would help us characterize Apophis surface properties, such as material cohesiveness and the degree of space weathering by excavating surface materials. By targeting different locations with multiple projectiles, we can assess the variability of surface conditions and examine diverse materials like regoliths and boulders. This would allow us to compare Apophis surface with those of other small bodies such as Itokawa, Ryugu, and Bennu. Next, please. So how will we carry out this experiment? We plan to develop a compact mass driver system with a total mass of about 5 kilograms. IAA, a space startup in Japan, has been developing a mass driver system for the world's first artificial shooting star experiments. And we aim to build a smaller version of that system. We call this system LME, Air's Low Energy Multi-Impact Experiment. LME uses a compressed gas propulsion system using helium or nitrogen to launch 1 centimeter metallic spheres at controlled velocities with high pointing accuracy. We are currently in discussions with XLab, the US space startup, to get this system on board their Apophis XL spacecraft. Next, please. So this impact will not alter Apophis orbit at all because the impact energies are so low. And we like to emphasize that LME will offer additional opportunities for dynamic exploration of Apophis, complementing the effect of Earth's tidal forces and OSIRIS-APEX star experiment. LME will provide unique scientific insights and enhance the overall value of all Apophis missions. One important point to note here is that the resulting craters will be around 10 centimeters in diameter. Therefore, collaboration with other missions equipped with high-resolution cameras, such as OSIRIS-APEX PodCam, is essential. Next, please. So even if we are unable to carry out this experiment on Apophis, we believe that LME has the potential to enhance the scientific return of onboard scientific instruments in future solar system missions. It may also pave the way for a new era of dynamic exploration of solar system small bodies. I will stop here. Thank you very much.
Thank you very much, Shogo. So we move to the last talk of the session. Let me take it by Kevin Walsh, who will tell us about Apophis kinetic impact test and cratering experiment after the close approach.
Thank you very much. Happy to be giving a talk today. Thanks for sticking around to the last talk. So to get right to it, this is a change of pace or a different flavor of Apophis mission concepts. The bottom line up front here is, regardless of Apophis's flyby of Earth and what happens during that event, it's going to be one of the best studied asteroids in the entire solar system, due largely to the presence of OSIRIS-APEX and its long visit at that asteroid, and hopefully the visit of Ramses as well. It will be orbited, its mass will be determined down to the 1% level, shape models at the centimeter level. Imaging, spectroscopy, everything is there. So its mass, known to great precision, highly capable spacecraft for radio tracking, etc. It is a perfect target for a cratering and deflection experiment. And that's what I'm going to talk about for the rest of the talk. A large crater could be observed, again, mapped at excellent precision. The ejecta plume could be mapped with an entire array of spectroscopic instruments from multiple spacecraft. It provides a real perfect before and after experimental workshop for a cratering and deflection experiment. And I'd like to emphasize that this is not the DART mission all over again. This is different. Apophis is a larger target. We expect it to be a full robopile on its own. It's not the satellite of something else. It's a cratering event that we'll be exploring here. It's expected that Dimorphos was fully reshaped in the DART impact. The experiment, again, is designed to have a precise pre-impact mass and shape of the target, to be compared with the post-impact shape and deflection amount, the delta V measured from the OSIRIS-APEX spacecraft. And because the observers are already there waiting for us, it cuts out half of the mission effort. And the effort here and the cost here is getting an impactor to that asteroid and impacting at a time when those observers are capable of making the required measurements. This will also not increase the Apophis impact risk. This is fully in the explored range from the Apophis Specific Action Team report in the time following the Earth flyby and the expected delta V from the impact. It's entirely within that box with orders of magnitude of headroom on the delta V, orders of magnitude. That was in the range that was determined to be assuredly safe. We went even further. I asked David to rerun everything and going another order of magnitude in delta V, and it still does not change the impact risk at all. So the science objectives here are numerous. This is, again, a really potentially deep way to explore this asteroid. One of the first big science objectives is to get another anchor point on our crater scaling relationships. The artificial impact at Ryugu from SCI was excellent for this. It gave us an understanding of how the cratering was controlled on the surface. We need to understand how large craters form as a function of the mass and energy of the impactor. That allows us to turn a known impactor flux into a surface age when we study asteroids throughout the solar system to understand the evolution of the solar system and the asteroids within it. This would give us another anchor point at a larger crater size on an S-type asteroid. So it gives us a huge advance for crater scaling relationships and surface chronology of asteroids. This would also give us a chance to explore deeper into rubble pile subsurface than we've done before. Both Hayabusa 2 and OSIRIS-REx explored the subsurface of their targets, both C-type asteroids, one through the SCI cratering experiment, and then also for OSIRIS-REx through the TAG event, which explored almost a meter into the surface. So 2 C-types have been explored about a meter into the subsurface. The near subsurface was found to be nearly strengthless, low porosity, under dense compared to the rest of the bulk asteroids. But cratering, morphology, and morphometry suggested that maybe there were hints of increasing strength with depth. There was a suggestion of a layering of fines on Bennu, somewhere around a meter or 2 meters deep. So here we would punch below that depth and we'd explore up to 5 meters below the subsurface and better characterize any stratification, changes in density, or layering of material at that level of a rubble pile asteroid. And then finally, this is a chance to study a momentum enhancement via a cratering impact into a larger rubble pile asteroid with really precise pre-impact mass and long-term radio tracking to determine the delta V with high precision. So the requirement to pull this off is built around what OSIRIS-APEX could measure for a delta V with radio tracking. And so for this, we're scaling off of what it achieved as OSIRIS-REx at Bennu, which was something like the 3 sigma tracking error was around 0.01 millimeters per second, which is amazing. So that is the delta V that we set as the minimum requirement for this mission. That requires something like a 65 kilogram impactor at 7 kilometers per second. That would produce a measurable delta V, something that OSIRIS-APEX could pick up with long-term radio tracking. By definition, if we hit with that amount of energy, we make a really nice crater that would be easily resolved with the capabilities of APEX. Something like 50 meters across, 5 meters deep. Again, APEX should be achieving centimeter resolution on the surface in both imaging and shape modeling, and it has extra spectrometers as well to really explore this crater and the depth into the subsurface. Pulling this off, the technical aspect of this, getting there is not that hard. There are multiple ballistic launch windows. Advanced Space in Colorado did a search with the requirements of an impact speed of 5 kilometers per second, impacting after the end of the expected OSIRIS-APEX prime mission in November of 2030, and impacting on the sunlit side of the asteroid, optimizing for the launch energy and the launch date. There's a handful of windows that can achieve this with relatively low launch energy. These get there relatively quick. They hit at high speeds, everything that we are looking for. And then there's extra avenues that this could be optimized, some of which we looked into when we explored opportunities to possibly use the Janus spacecraft in this context. It was not what we started out thinking, but it was an interesting opportunity to explore. There you have 2 spacecraft, and so the launch windows and the ballistic trajectories are the same, but what we found were a handful of interesting resonant encounters, which would give you a chance to either have a practice run or have an encounter where one of your spacecraft hits on the first time around and the second spacecraft hits on the second time around. So you get 2 instances, 2 impacts to study with the local spacecraft. For example, one of these launches in April of 2029 with relatively low launch energy. The first encounter is in June 9th of 2030, and it comes back in August 6th of 2031, October 2nd of 2032. And there's a handful of these, which is really interesting, not just in the context of this specific mission concept, but for other mission concepts as well. It's a place for possible exploration to optimize some spacecraft technology. The targeting uncertainty, here we're almost cheating because the ephemeris of Apophis is known at the meter scale. So it was not hard to optimize the navigation strategy with nominal navigation errors to provide a 99% chance of actually hitting the target, again, with the last course maneuver 20 hours out following a normal schedule of course maneuvers. So again, the ephemeris of Apophis makes this easy, much easier, and kind of decreases the requirements on your main spacecraft to actually pull off the impact. So in conclusion, this concept is not at odds with precursor mission concepts. This is different but overlapping science and planetary defense goals, and it leverages the presence of these really, really capable spacecraft that are already there. We absolutely take advantage of what is sitting there waiting for us at Apophis. This offers a really long runway for development and launch. There are launch opportunities in 2030. So this is not a sprint to get to the launch pad right now. This is something that there is time to develop this and decide that it's the right mission for Apophis. And this, of course, the science goals and the planetary defense goals offer potentially big, big advances, again, based on the capabilities of the observers that are there and the chance to leverage all of the capabilities present at Apophis. Thank you for your time.
Thank you. Thanks, Kevin. Thanks all the speakers. So before going to the Q&A, as you may know, Rick Binzel initiated, and I joined him, the Apophis T-X workshops, starting from Apophis T-9. So the last one was Apophis T-4 years in Tokyo. And as usual, at the end of these workshops, we generate some findings and recommendations. And I offer the floor to Rick, who wants to basically summarize the findings and recommendations. Rick, are you with us?
I'm here, Patrick.
Hey, great. We hear you well. Can you upload the slides that you'd have received? Oh, no, they are there. Yeah, sorry. Go ahead, Rick. Sorry.
Okay. I'm not seeing the slides. I'm sorry. All right. So just let me tell you that this summary, assuming you're seeing the first slide, summary of our workshop held in Tokyo. You can see our conveners, myself, Patrick, and our host, Seiji Sujita at the University of Tokyo with our Science Organizing Committee. This comes as basically a long series of workshops that we began back in 2020. You can see we've typically had 100 to 200 attendees. They've been virtual. We had now combined virtual and in-person attendance, up to 250 at STEC last year, and then over 300 attendees live and virtual in Tokyo. So let me just put this eye chart up with our findings. You may just want to snap it. And then we are publishing this as an EPSC DPS abstract, and we'll be posting these on our website. So I'll just very briefly just tell you that as a group of, again, of more than 300 attendees, 31 countries, 5 continents, we recognize and appreciate the United Nations Declaration of the International Year of Asteroid Awareness and Planetary Defense. You know, the world will be watching. I think we all understand that. But I think the point is the world's going to want to know what are the scientists doing. And that's why we're here now and why we really have to make sure we have a solid response, a worldwide response to Apophis, because the world's going to expect it. And they won't be aware of it until the last minute, but now's our time. Anyway, to do that, we recognize we're going to have to do this as an international collaboration. We're seeing that here in the room today, so thank you to all. And I just want to say we, as a group, and you have the same spirit, we're all committing to international collaborations. And because planetary defense is a worldwide problem, we're committed to sharing what we find with the world. This is not going to be information held in the pocket. We want to share all of what we learn about this asteroid and planetary defense with the world. So we want to emphasize the priority of the major missions, Destiny Plus, Ramses, OSIRIS Apex. These are missions that are well underway. We want to make sure that they are fully approved and funded to accomplish their task. And we list those as the most essential and highest priority in situ investigations. But, we're also seeing this as an incredible opportunity for small sat and CubeSat experiments. And, we saw Adrian's talk. You have the other Maryland folks in the room, other graduate students in the room. This is an incredible opportunity for students. And so, you're seeing it right there. You guys are the future. And this is such a great thing to have come along as a student opportunity. And then, as we say, time is of the essence. I don't need to say any more about that because we all know it, we all feel it. And as I like to say, Apophis is coming, whether we are ready or not. And then finally, we have some specific recommendations. And that is, just we want to recommend that the observing campaigns have to be well coordinated. And Iwan and Vishnu Reddy and Christina Thomas are underway with that. But I think, going back to Joseph Durek's point, is that we really need these upcoming apparition observations to pin down the orientation of Apophis so our theoretical models can advance. And so I think that's something we'll be emphasizing with the SBAG and things like that here at NASA. And then, we just need ongoing support for the laboratory and theoretical work. And again, we not only coordinate so our spacecraft don't interact in a collisional way with one another, but that we're organizing our science measurements and science goals. And so that's already also underway, but we emphasize that importance. And then just more specific to NASA, at a previous workshop, we recognize these spacecraft are there looking for a mission. Apophis is an asteroid wanting a mission. And so the Janus spacecraft used for Apophis seems to be an awesome idea. NASA asked for a presentation and was delivered a presentation on what Janus could do, but NASA has never responded. So we're simply saying, NASA, please respond. And with that, I'll stop. And thank you for letting me join the discussion.
Thanks a lot, Rick, for this great summary. So now I invite all the speakers on stage to answer the question that hopefully will emerge on the screen, unless I have to take them on my screen. You want some? Okay, everybody has a chair. Very crowded, like around Apophis in 2029, actually. Okay, so I have first question, probably for Carol. Expected cost of the Caltech mission, by when will you need a funding decision to meet the 2028 launch date?
The cost is around 150 million life cycle, and the funding decision is needed essentially now. And
End of the month.
That's where we are. We're kind of in the final stretch, so it's do or die time.
Okay, great. Okay, so second question would be, hypothetically, there was a contact binary threat to Earth. Do any of you think we have the knowledge to accurately deflect it? Be careful what you answer. What specifically do we need to learn about them? So what about contact binaries? Yeah, Dan?
Yeah, I don't think we understand them well enough. We should do a mission to a contact binary and
Very good
actually try
answer.
to ascertain what the strength is, how they're
connected or not. So.
Okay, good answer. Okay, how do we ensure that multiple missions to Apophis don't interfere with each other? For example, with radar observations, don't interfere with each other.
Okay, so if we're using X-band, that's 85, 60 megahertz, then we are not in the usual communication of spacecrafts. They are working in C-band, so that may represent an issue with us getting our 1.75 meter resolution that we need C-band. But we can always fall back on X-band and still get 3.75 meters. So it should not be a problem.
Okay. And in fact, we need to coordinate well in advance also to make sure they don't interfere.
We can coordinate well in advance, or even do some tests. So.
Yeah. Okay. Okay. Next question is: if a satellite would collide with Apophis, could it potentially act as a kinetic impactor? Has anyone looked at the details, likelihood, relative velocity, etc.? I guess this applies even more for flyby missions, I would say. So any.
Well, it would definitely, Apophis could definitely impact on our satellites. The problem, it would almost certainly terminate the satellite itself, but the major problem would be the cascade effect on the, with debris colliding with other debris, and, well, we all know as the Kessler effect. It could potentially act as a kinetic impactor. Well, I showed that the impact on Apophis on the satellites is very small. On the other side, kinetic impactors must have, well, a relative velocity that is pretty bigger than the one that we expect on our satellites. So I wouldn't, well, it could be investigated, but I wouldn't expect much results.
Okay, I was actually thinking of a spacecraft doing a flyby of Apophis, if it, collide instead of a...
We might think of it, well, of using it to, I don't know, to go to the moon or something. It could be a nice exercise.
Okay, any other insight? No? Okay, so next question would be, much like Apophis, the Chelyabinsk impactor had an LL chondrite composition and it struck a multiple of 4 years. It struck a multiple of 4 years ago. Could these two objects, okay, I see. Could these two objects have originated from the same parent? What data would be required to prove or disprove a connection? I would say maybe if we have, from the current orbit, we could estimate the source region and see whether they are the same, and probably they are.
And there's a lot of LL chondrites floating around out there.
So
yeah,
it might be hard
the
to make
flora
any
family,
strong, unique.
Yeah, the flora family, flora family in the inner belts are rich in LL chondrites. That's a big amino source. So, in a broad sense, they're probably related.
Okay, so flora family is one of the likely origin of these bodies. Okay, the next one is CR3BP complex enough to convince people to use a cislunar ride share?
Okay, I think that's probably for me. I think I neglected to say the circular restricted three-body problem was used to find those initial dynamical families that would be candidates, but the actual trajectories that I showed in the latter half of the presentation were all full fidelity, taking into account all the planet's gravity and in the ephemeris model. So they were real trajectories.
Okay, then for Adrienne, so you mentioned that the TERP Raptor could be a great opportunity for public engagement. How so? And if any other presenters have thoughts on how their missions could contribute to public engagement, please share your ideas.
Okay, so I really love this question. This is something we've talked about a lot on our team. So we have this grand idea that after we get images back from Apophis, they all at once show up on people's phones across the world. As they're looking up, trying to figure out what's going on, it comes on their phones and they're like, oh, wow, that's Apophis. That's this big rock in our backyard. As well as that, we are also working on a trailer right now that we want to put out on a website that we are creating to share with the public on what our mission is doing. We've also been in talks with, I think it was during the T-4 workshop, we had suggested actually making a collaborative Apophis trailer across all of these teams and putting that up online for the public to see so they get an idea of what all we are doing and the science that we want to do as well. So, yeah.
Okay, thank you.
Adrian, I would just add for that.
Yeah, Rick.
If I could add that image of Apophis going by the Earth and holding up your phone, that's a selfie because everyone on Earth who's looking up is in that picture. So you could tell everyone you are in this picture too.
Yes,
Another interesting point is that Pew Research has polled Americans about what NASA should be focusing on, and almost every time planetary defense is the top response, on top of astrophysics or climate change or anything else.
Carol, you want to say something?
Yeah, I just wanted to say we're also looking at a broad strategy for public engagement and involving both education and just social media and the wow factor. It's such a draw, and then finally using VR to demonstrate the whole interaction in virtual reality.
And all this will be supported by 2029 being the International Year of Asteroid Awareness and Planetary Defense. So we can expect around the world many events, not only during the Apophis encounter, but during the whole year. So that's a way also to engage the public. So good opportunities. Anything else? No? Okay, so next, is Apophis a threat to our satellites? And in the case of collisions, what sort of damage would be expected? So I guess that's about the same.
I've pretty much already
answered.
replied. It was on top before, so well, yes, it can definitely be a collision. So
Yeah.
we have to investigate that further.
Okay. So Adrian, you say HARP will transmit at roughly 9 megahertz. That seems close to the electron frequency of the ionosphere. What amount of refraction and extinction do you expect of the transmitted signal before it reaches your satellite?
Okay, so we get this question a lot, and I'm not going to claim to be an expert on ionospheric physics, but I am friends with one who is the person that we are actually collaborating with on this. So I will say that they have done experiments like this in the past where they have illuminated other asteroids. It's been in the news. Don't ask me what year it was. I know that it was when I was little. And they were actually receiving the signal back on an observatory on Earth. We have learned that we can be, I think, 10,000 kilometers away from Apophis and still be able to receive the signal, the reflected signal. So hopefully that answers that question.
Yeah. Okay, great. Next one is, are there any space agencies you are afraid, I'm afraid of a space agency, will be non-compliant if they send something to Apophis? I think we can trust space agencies, especially because they are in the room, so I would answer, that they will be compliant. In fact, I think, as Richard was saying, Richard Moisel at SM Page, they are putting a working group to make sure with COSPAR that we coordinate well all those missions. So hopefully also the private initiative will join the effort of coordination, but for the space agency, they already talked together through SM Page. Okay, so, Carol, how have the funding, how are the funding outlook for the task mission changed since T-4? So T-4 was only 2 weeks ago. Huh?
Yeah, and yet it has improved.
Good. Okay, there is an idea to capture Apophis and put it in orbit around the, no, 340 meters, there is not an idea. I mean, maybe the idea, but... Okay, thank you for the question. What is the likelihood that increased stresses in the neck region during close encounter with the Earth might cause separation between lobes? Would this increase risk to Earth and potentially necessitate PD efforts? I guess that's for Dan.
Yeah, I mean, really all the simulations show that we're just not flying close enough to actually put the body under strong tension. So even if the neck region was very weak, we're not generating enough tidal stresses to pull the body apart. So,
okay.
If someone wants to push it closer to the Earth, then we would see something interesting.
That would be cool.
Yeah.
Joe, you want to say something, or you're okay with that too? Modelers
No,
sometimes disagree.
Full agreement.
Okay. Could there be restructuring if it's a loose contact binary? Could there be restructuring? That's my question.
That's what we were looking at, and we did not see strong evidence for that. I mean, you can tee it up to make it happen, but for a natural body, we're not getting any evidence for that.
Okay. But you know, until now, our evidence were very weak when we went to see an object. So maybe we'll be surprised. Okay, given the high costs of sending a mission to Apophis, not very high, but okay. How do you justify the investment if the data collected only confirms what we already suspect from ground-based observations? So since so far we never confirmed what we suspected, I think it's worth the money, right?
We are always surprised.
Every mission that has gone to an asteroid has found something interesting and peculiar about that asteroid.
Any?
I like to say
Rick?
this is the natural experiment that comes once per 1,000 years. We got to learn the most we can from it.
Yeah, absolutely. And you know, it's what a mission is a few €100 million, and the stadium for soccer in Nice costs 600 million. So.
Yeah.
So,
I would also.
Yeah, I have a.
Go ahead, Carol.
It's just a comment related to this, and it struck me listening to all of the talks in this session that kind of in a similar manner as YR4 gave us a sort of a real life drill. This is an interesting exercise where we're actually looking at how we would do rapid response from many different directions, both reuse of existing spacecraft or copies of missions like the Hera to Ramses, involving commercial space, just all kinds of really innovative ways to use ride shares. And I think this is really pushing us forward in the being ready to do a rapid response flyby or rendezvous mission. So in that sense, it's about more than Apophis, if there could be anything more than Apophis. Sorry, Rick.
And if we talk about business, when you have 2 billion people watching the asteroid, they will know which companies and which agencies are there. That's the best advertisement. Better than Super Bowl, actually. So, you know.
Okay, so I'd also like to address that what we learn from the ground base, right, will actually be tested by missions.
That's a ground truth.
Right, and that's really it's really an evolution. It's not separate.
Absolutely, yeah. Okay, so Dan, how would you expect the seismic signal that could be modeled using CD to compare to the signals Joe showed?
So I don't know if...
CD is contact dynamics, by the way.
Yeah, contact dynamics. I don't know if people have developed a seismic version of CD. I think you could, but you'd have to link some finite element codes along with the CD. With the soft sphere, you very easily generate seismic signals and send them through there. So there's also the worry that maybe they transmit almost too easily because they have springs modeling their response. So I think that they're at two spectrums of reality right now.
Okay,
So
which is
see what
good, so that we
reality
have the
is.
two extremes.
Yeah.
Okay. Okay, we have a question for TERP Raptor. Actually, two questions. One is, how does your mission design compare to other proposed missions, and what is the unique scientific aspect?
Sure. So I would say that I think for my slides I explained that we have a lower mission cost, a lower cost per image, and relatively high image resolution compared to other missions. I forgot what I was going to say about the next part. Let's see. Yeah, and then I think it's more streamlined. So there were a couple of missions that we saw at SciTech back in January that were a little bit more complex in nature. They had like multiple spacecrafts or even like a swarm of spacecrafts that would surround the asteroid, which for the science that they were trying to do is really incredible. And hopefully if those missions come to fruition, then they'll get wonderful data on that. But ours is a very simple flyby, relatively low cost in the grand scheme of things. So I think that kind of answers both questions in one. So.
Okay, thank you. And for Joe, what magnitude of a body wave speeds are you getting? I think I saw kilopascal elastic modulus for your particles. You have plans to test at the megapascal level or above.
Yeah, so actually, some of the simulations that we've been doing in the past with the random packing have been at the megapascal level, and so are our simulations in our 2019 paper, the megapascal or tens of megapascal. So those are the ones that we're using for the seismic propagation, and that's where we're seeing the acceleration amplitudes in the 10 to the minus 3 range. We are assuming that that's a more realistic elastic modulus based on, for example, the bounce of the Rosetta lander on Churi. But there's not a ton of data for this kind of thing. So we're hoping that Apophis can give us a little bit more.
Okay, thank you. The next is for TerpRaptor. They give you a hard time, huh? Wow. So are you concerned that both imagers won't fit a single 12U CubeSat when adding in all the other aspects of the CubeSat, so like propulsion, avionics, power, etc.?
I think I want to know if we're being picked on because this is good or bad, and nobody's told me otherwise yet. So we are not concerned that both imagers won't fit on the CubeSat. That is our main priority for our science. So we've also catted out our spacecraft. The imagers fit. If anything, we've actually been shimmying around the propulsion a little bit. So no concern there. Both imagers will fit.
Good. Excellent. Thank you. If Apophis turns out to be a structure completely unlike current completely unlike current models, how ready is the mission to adapt? And would that undermine its core assumptions? Well, first of all, until now, no asteroid have looked, like we thought, and we adapted, so I guess we can adapt, right?
Okay. I would add that the campaigns prior would help to limit the phase space of what the unexpected may be.
So yeah, I think.
But we also, I want to say that we actually really have a very good idea how near-Earth asteroids look like, because in our radar database we actually imaged more than, at this point we detected more than 1,000 of them and imaged at very high resolutions, probably several hundred of them. So we actually do know how your typical near-Earth asteroid look like. It's not something unexpected. It's either a contact binary, or it's a true binary, and this one is definitely not, or it's some kind of like KW4 shaped, so that's diamond shaped, or just a spherical. So it's not going to be something. It's not going to be starfish. So
no, it's something we can do close proximity operations around. Maybe a little different than. 2 more questions. Oh, yeah, because it's 25 seconds. So I just have the time to send a question, and you say yes or no. What is driving all of these other mission studies when we have Apex plus Ramses, most likely? Why not unite behind those 2? I cannot say.
So I'll just say, I think because we started a long time ago, and there's been a lot of uncertainty about, well, not about Apex, but about other options. And it's good to have, a lot of options, because not everything turns out. So we're placing our bets. And if we end up with a variety of missions, then the job is to work together and make, synergize them to get even better results.
And there is always complementarity between all these missions. So, okay, so we don't have time for the last question, which would deserve 30 minutes. So maybe we end there, and we thank the speakers again for this session. Rick, all the online, Shogo, Joe, thank you so much. And for Apophis, Apophis T-3 will be discussed with Rick and others, and we'll announce where and when. Thanks, and I guess, Gerhard, you want to wrap up? Thank you.
Yeah, just a very short note. I think it was an interesting day with a lot of presentations. You are now invited to go to the posters, and they promise some cheese and wine with it. So enjoy the rest of the evening.